Section 42 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 2, of the Progress of Philosophical Chemistry in Sweden, Part 4. It seems that while Scheele was in Stockholm, he had made experiments on cream of tartar, and had succeeded in separating it from tartaric acid in a state of purity. He had also determined a number of the properties of tartaric acid, and examined several of the tartrates. He drew up an account of these results and sent it to Bergman. Bergman, seeing a paper subscribed by the name of a person who was unknown to him, laid it aside without looking at it, and forgot it altogether. Scheele was very much provoked at this contemptuous and unmerited treatment. He drew up another account of his experiments and gave it to Retzius, who sent it to the Stockholm Academy of Sciences, with some additions of his own, in whose memoirs it was published in the year 1770. It cost Assessor Gahn considerable trouble to satisfy Scheele that Bergman's conduct was merely the result of inadvertence, and that he had no intention whatever of treating him either with contempt or neglect. After much entreaty, he prevailed upon Scheele to allow him to introduce him to the professor of chemistry. The introduction took place accordingly, and ever after, Bergman and Scheele continued steady friends, Bergman facilitating the researches of Scheele by every means in his power. So high did the character of Scheele speedily rise in Upsala, that when the Duke of Sudermania visited the university soon after, in company with Prince Henry of Prussia, Scheele was appointed by the university to exhibit some chemical processes before him. He fulfilled his charge, and performed in different furnaces several curious and striking experiments. Prince Henry asked him various questions, and expressed satisfaction at the answers given. He was particularly pleased when informed that he was a native of Stralsund. Those two princes afterwards stated to the professors that they would take it as a favor if Scheele could have free access to the laboratory of the university whenever he wished to make experiments. In the year 1775, on the death of Mr. Poplar, apothecary at Coping, a small place on the north side of Lake Mahler, he was appointed by the Medical College provisor of the apothecary's shop. In Sweden, all the apothecaries are under the control of the Medical College, and no one can open a shop without undergoing an examination and receiving license from that learned body. In the course of the examinations, which he was obliged to undergo, Scheele gave great proofs of his abilities, and obtained the appointment. In 1777, the widow sold him the shop and business, according to a written agreement made between them, but they still continued housekeeping at their joint expense. He had already distinguished himself by his discovery of fluoric acid, and by his admirable paper on manganese. It was said, too, that it was he who made the experiments on carbonic acid gas, which constitute the substance of Bergman's paper on the subject, and which confirmed and established Bergman's idea that it was an acid. At Coping, he continued his researches with unremitting perseverance, and made more discoveries than all the chemists of his time united together. It was here that he made the experiments on air and fire, which constitute the materials of his celebrated work on these subjects. The theory which he formed was indeed erroneous, but the numerous discoveries which the book contains must always excite the admiration of every chemist. His discovery of oxygen gas had been anticipated by Priestley, but his analysis of atmospheric air was new and satisfactory, was peculiarly his own. The processes by means of which he procured oxygen gas were also new, simple, and easy, and are still followed by chemists in general. During his residence at Coping, he published a great number of chemical papers, and every one of them contained a discovery. The whole of his time was devoted to chemical investigations. Every action of his life had a tendency to forward the advancement of his favorite science, All his thoughts were turned to the same object. All his letters were devoted to chemical observations and chemical discussions. Crell's Annals was at that time the chief periodical work on chemistry in Germany. He got the numbers regularly as they were published, and was one of Crell's most constant and most valuable correspondents. Every one of his letters published in that work either contains some new chemical fact or exposes the errors and mistakes of some one or other of Crell's numerous correspondents. Scheele's outward appearance was by no means prepossessing. He seldom joined in the usual conversations and amusements of society, having neither leisure nor inclination for them. What little time he had to spare from the hurry of his profession was always employed in making experiments. It was only when he received visits from his friends, with whom he could converse on his favorite science, that he indulged himself in a little relaxation. For such intimate friends he had a sincere affection. This regard was extended to all of the zealous cultivators of chemistry in every part of the world, whether personally known to him or not. He kept up a correspondence with several, though this correspondence was much limited by his ignorance of all languages except German, for at least he could not write fluently in any other language. His chemical papers were always written in German and translated into Swedish before they were inserted in the memoirs of the Stockholm Academy, where most of them appeared. He was kind and affable to all. Before he adopted an opinion in science, he reflected maturely on it, but after he had once embraced it, his opinions were not easily shaken. However, he did not hesitate to give up an opinion as soon as it had been proved to be erroneous. Thus he entirely renounced the notion which he once entertained that silica is a compound of water and fluoric acid, because it was demonstrated by Meyer and others that this silica was derived from the glass vessels in which the fluoric acid was prepared, and that these glass vessels were speedily corroded into holes, and that if fluoric acid was prepared in metallic vessels and not allowed to come in contact with glass or any substance containing silica, it might be mixed with water without any deposition of silica whatever. It appears also by a letter of his published in Crell's Annals that he was satisfied of the accuracy of Mr. Cavendish's experiments, showing that water was a compound of oxygen and hydrogen gases, and one of Lavoisier's repetition of them. He attempted to reconcile this fact with his own notion that heat is a compound of oxygen and hydrogen. But his arguments on that subject, though ingenious, are not satisfactory, and there is little doubt that if he had lived somewhat longer, and had been able to repeat his own experiments and compare them with those of Cavendish and Lavoisier, he would have given up his own theory and adopted that of Lavoisier, or, at any rate, the explanation of Cavendish, which, being more comfortable to his own preconceived notions, might have been embraced by him in preference. It is said by Dr. Crell that Scheele was invited over to England with an offer of an easy and advantageous situation, but that his love of quiet and retirement, and his partiality for Sweden, where he had spent the greatest part of his life, threw difficulties in the way of these overtures, and that a change in the English ministry put a stop to them for the time. The invitation, Crell says, was renewed in 1786, with the offer of a salary of 300 L a year, but Scheele's death put a final stop to it. I have very great doubts about the truth of this statement, and many years ago, during the lifetime of Sir Joseph Banks, Mr. Cavendish, and Mr. Keren, I made an inquiry about the circumstance, but none of the chemists in Great Britain, who were at that time numerous and highly respectable, had ever heard of any such negotiation. I am utterly at a loss to conceive what one individual in any of the ministries of George III was either acquainted with the science of chemistry or at all interested in its progress. They were also intent upon accomplishing their own objects, or those of their sovereign, that they had neither time nor inclination to think of science, and certainly no money to devote to any of its votaries. What minister in Great Britain ever attempted to cherish the sciences, or to reward those who cultivate them with success? If we accept Mr. Montague, who procured the place of Master of the Mint for Sir Isaac Newton, I know of no one. While in every other nation in Europe science is directly promoted, and considerable sums are appropriated for its cultivation, and for the support of a certain number of individuals who have shown themselves capable of extending its boundaries, not a single farthing has been devoted to any such purpose in Great Britain. Science has been left entirely to itself, and whatever has been done by way of promoting it has been performed by the unaided exertions of private individuals. George III himself was a patron of literature and an encourager of botany. He might have been disposed to reward the unrivaled eminence which Scheele had attained, but this he could only have done by bestowing on him a pension out of his privy purse. No situation which Scheele could fill was at his disposal. The universities and the church were both shut against a Lutheran, and no pharmaceutical places exist in this country to which Scheele could have been appointed. If any such project had ever existed, it must have been an idea which struck some man of science that such a proposal to a man of Scheele's eminence would redound to the credit of the country. But that such a project should have been broached by a British ministry, or by any man of great political influence, is an opinion that no person would adopt who has paid any attention to the history of Great Britain since the Revolution to the present time. Scheele felt at last a sacrifice to his ardent love for his science. He was unable to abstain from experimenting, and many of his experiments were unavoidably made in his shop, where he was exposed during winter, in the ungenial climate of Sweden, to cold draughts of air. He caught rheumatism in consequence, and the disease was aggravated by his ardour and perseverance in his pursuits. When he purchased the apothecary's shop in which his business was carried on, he had formed the resolution of marrying the widow of his predecessor, and he had only delayed it from the honourable principle of acquiring, in the first place, sufficient property to render such an alliance desirable on her part. At length, in the month of March, 1786, he declared his intention of marrying her, but his disease at this time increased very fast, and his hopes of recovery daily diminished. He was sensible of this, but nevertheless he performed his promise, and married her on the 19th of May, at a time when he lay on his deathbed. On the 21st he left her by his will the disposal of the whole of his property, and the same day on which he so tenderly provided for her, he died. I shall now endeavour to give the reader an idea of the principal chemical discoveries for which we are indebted to Scheele. His papers, with the exception of his book on air and fire, which was published separately by Bergman, are all to be found either in the Memoirs of the Stockholm Academy of Science or in Krell's journal. They were collected, and a Latin translation of them, made by Godfrey Henry Schaeffer, published at Leipzig in 1788, by Henstreet, the editor of the 3 last volumes of Bergman's Opuscula. A French translation of them was made in consequence of the exertions of M. Norveau, and an English translation of them in 1786 by means of Dr. Beddoes, when he was a student in Edinburgh. There are also several German translations, but I have never had an opportunity of seeing them. 1. Scheele's first paper was published by Retzius in 1770. It gives a method of obtaining pure tartaric acid. The process was to decompose cream of tartar by means of chalk. 1/2 of the tartaric acid unites to the lime, and falls down in the state of a white insoluble powder, being tartrate of lime. The cream of tartar, thus derived of half its acid, is converted into the neutral salt formerly distinguished by the name of soluble tartar, from its great solubility in water. It dissolves, and may be obtained in crystals by the usual method of crystallizing salts. The tartrate of lime is washed with water, and then mixed with a quantity of dilute sulphuric acid, just capable of saturating the lime contained in the tartrate of lime. The mixture is digested for some time. The sulphuric acid displaces the tartaric acid, and combines with the lime, and as the sulphate of lime is but very little soluble in water, the greatest part of it precipitates, and the clear liquor is drawn off. It consists of tartaric acid, held in solution by water, but not quite free from sulfate of lime. By repeated concentrations, all the sulfate of lime falls down, and at last the tartaric acid itself is obtained in large crystals. This process is still followed by the manufacturers of this country, for tartaric acid is used to a very considerable extent by the calico printers in various processes. For example, it is applied, thickened with gum, to different parts of cloth dyed turkey red. The cloth is then passed through water containing the requisite quantity of chloride of lime. The tartaric acid, uniting with the lime, sets the chlorine at liberty, which immediately destroys the red color wherever the tartaric acid has been applied, but leaves all the other parts of the cloth unchanged. 2. The paper on fluoric acid appeared in the Memoirs of the Stockholm Academy for 1771, when Scheele was in Scherenberg's apothecary's shop in Stockholm, where doubtless the experiments were made. 3 years before, Marggraf had attempted an analysis of fluor spar, but had discovered nothing. Scheele demonstrated that it is a compound of lime and a peculiar acid, to which he gave the name of fluoric acid. This acid he obtained in solution in water. It was separated from the fluor spar by sulfuric, muriatic, nitric, and phosphoric acids. When the fluoric acid came in contact with water, a white crust was formed, which proved on examination to be silica. Scheele at first thought that this silica was a compound of fluoric acid and water, but it was afterwards proved by Weigleb and by Meyer that this notion is inaccurate, and that the silica was corroded from the retort into which the fluor spar and sulfuric acid were put. Bergman, who had adopted Scheele's theory of the nature of silica, was so satisfied by these experiments that he gave it up, as Scheele himself did soon after. Scheele did not obtain fluoric acid in a state of purity, but only flausilicic acid, nor were chemists acquainted with the properties of fluoric acid till Gay-Lussac and Thenard published their Recherches physico-chimiques in 1811. End of section 42. Recording by Lawrence Trask. InterfaceAudio.com. Section 43 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 2. On the Progress of Philosophical Chemistry in Sweden. Part 5. 3. Scheele's experiments on manganese were undertaken at the request of Bergman, and occupied him 3 years. They were published in the Memoirs of the Stockholm Academy for 1774, and constitute the most memorable and important of all his essays, since they continue the discovery of 2 new bodies, which have since acted so conspicuous a part, both in promoting the progress of the science and in improving the manufactures of Europe. These 2 substances are chlorine and barytes, the first account of both of which occur in this paper. The ore of manganese employed in these experiments was the black oxide, or deutoxide of manganese, as it is now called. Scheele's method of proceeding was to try the effect of all the different reagents on it. It dissolved in sulphurous and nitrous acids, and the solution was colorless. Dilute sulfuric acid did not act upon it, nor nitric acid, but concentrated sulfuric acid dissolved it by the assistance of heat. The solution of sulfate of manganese in water was colorless and crystallized in very oblique rhomboidal prisms, having a bitter taste. Muriatic acid effervesced with it, when assisted by heat, and the elastic fluid that passed off had a yellowish color, and the smell of aqua regia. He collected quantities of this elastic fluid, chlorine, in bladders, and determined some of its most remarkable properties. It destroyed colors, and tinged the bladder yellow, as nitric acid does. This elastic fluid, in Scheele's opinion, was muriatic acid deprived of phlogiston. By phlogiston Scheele meant, in this place, hydrogen gas. He considered muriatic acid as a compound of chlorine and hydrogen. Now, this is the very theory that was established by Davy in consequence of his own experiments, and those of Gay-Lussac and Thenard. Scheele's mode of collecting chlorine gas in a bladder did not enable him to determine its characters with so much precision as was afterwards done. But his accuracy was so great that everything which he stated respecting it was correct so far as it went. Most of the specimens of manganese ore which Scheele examined contained more or less barytes, as has since been determined in combination with the oxide. He separated these barytes and determined its peculiar properties. It dissolved in nitric and muriatic acids, and formed salts capable of crystallizing and permanent in the air. Neither potash, soda, nor lime, nor any base whatever, was capable of precipitating it from these acids. But the alkaline carbonates threw it down in the state of a white powder, which dissolved with effervescence in acids. Sulfuric acids and all the sulfates threw it down in the state of a white powder, which was insoluble in water and in acids. This sulfate cannot be decomposed by any acid or base whatever. The only practicable mode of proceeding is to convert the sulfuric acid into sulfur by heating the salt with charcoal powder, along with a sufficient quantity of potash, to bring the whole into fusion. The fused mass, adulterated, is soluble in nitric or muriatic acid, and thus may be freed from charcoal, and the barytes obtained in a state of purity. Scheele detected barytes also in the potash made from trees or other smaller vegetables, but at that time he was unacquainted with sulfate of barytes, which is so common in various parts of the earth, especially in lead mines. To point out all the new facts contained in this admirable essay, it would be necessary to transcribe the whole of it. He shows the remarkable analogy between manganese and metallic oxides. Bergman, in an appendix affixed to Scheele's paper, states his reasons for being satisfied that it is really a metallic oxide. Some years afterwards, Assessor Gahn succeeded in reducing it to the metallic state, and thus dissipating all remaining doubts on the subject. 4. In 1775, he gave a new method of obtaining benzoic acid from benzoin. His method was to digest the benzoin with pounded chalk and water, till the whole of the acid had combined with lime, and dissolved in the water. It is requisite to take care to prevent the benzoin from running into clots. The liquid thus containing benzoate of lime in solution is filtered, and muriatic acid added in sufficient quantity to saturate the lime. The benzoic acid is separated in white flocks, which may be easily collected and washed. This method, though sufficiently easy, is not followed by practical chemists, at least in this country. The acid, when procured by precipitation, is not so beautiful as what is procured by sublimation, nor is the process so cheap or so rapid. For these reasons, Scheele's process has not come into general use. 5. During the same year, 1775, his essay on arsenic and its acid was also published in the Memoirs of the Stockholm Academy. In this essay he shows various processes by means of which white arsenic may be converted into an acid, having a very sour taste and very soluble in water. This is the acid to which the name of arsenic acid has been since given. Scheele describes the properties of this acid, and the salts which it forms, with the different bases. He examines also the action of white arsenic upon different bodies, and throws light upon the arsenical salt of Macquer. 6. The object of the little paper on silica clay and alum, published in the Memoirs of the Stockholm Academy for 1776, is to prove that alumina and silica are two perfectly distinct bodies, possessed of different properties. This he does with his usual felicity of experiment. He shows also that alumina and lime are capable of combining together. 7. The same year, and in the same volume of the Stockholm Memoirs, he published his experiments on a urinary calculus. The calculus upon which his experiments were made happened to be composed of uric acid. He determined the properties of this new acid, particularly the characteristic one of dissolving in nitric acid, and leaving a beautiful pink sediment when the solution is gently evaporated to dryness. 8. In 1778 appeared his experiments on molybdena. What is now called molybdena is a soft foliated material, having the metallic luster and composed of 2 atoms sulfur united to 1 atom of metallic molybdenum. It was known before, from the experiments of Quest, that this substance contains sulfur. Scheele extracted from it a white powder, which he showed to possess acid properties, though it was insoluble in water. He examined the characters of this acid, called molybdic acid, and the nature of the salts which it is capable of forming by uniting with bases. 9. In the year 1777 was published the experiments of Scheele on air and fire, with an introduction by the way of preface from Bergman, who seems to have superintended the publication. This work is undoubtedly the most extraordinary production that Scheele has left us, and is really wonderful if we consider the circumstances under which it was produced. Scheele ascertained that common air is a mixture of 2 distinct elastic fluids, one of which alone is capable of supporting combustion, and which therefore he calls imperial air. The other, being neither capable of maintaining combustion nor of being breathed, he called foul air. These are the oxygen and azote of modern chemists. Oxygen he showed to be heavier than common air. Bodies burnt in it with much greater splendor than in common air. Azote he found lighter than common air. Bodies would not burn in it at all. He showed that metallic calces, or metallic oxides as they are now called, contain oxygen as a constituent, and that when they are reduced to the metallic state, oxygen gas is disengaged. In his experiments on fulminating gold, he shows that during the fulmination a quantity of azotic gas is disengaged, and he deduces from a great many curious facts, which are stated at length, that ammonia is a compound of azote and hydrogen. His apparatus was not nice enough to enable him to determine the proportions of the various ingredients of the bodies which he analyzed. Accordingly, that is seldom attempted, and when it is, as was the case with common air, the results are very unsatisfactory. He deduces from his experiments that the volume of oxygen gas in common air is between 1/3 and 1/4. We now know that it is exactly 1/5. In this book also we have the first account of sulphuretted hydrogen gas, and of its properties. He gives it the name of stinking sulphureous air. The observations and new views respecting heat and light in this work are so numerous that I am obliged to omit them, nor do I think it necessary to advert his theory, which, when his book was published, was exceedingly plausible and undoubtedly constituted a great step towards the improvements which soon after followed. His own experiments, had he attended a little more closely to the weights and the alterations of them, would have been sufficient to have overturned the whole doctrine of phlogiston. Upon the whole, it may be said, with confidence, that there is no chemical book in existence which contains a greater number of new and important facts than this work of Scheele at the time it was published. Yet most of his discoveries were made also by others. Priestley and Lavoisier, from the superiority of their situations and their greater means of making their labors speedily known to the public, derived him of much of that reputation to which, in common circumstances, he would have been entitled. Priestley has been blamed for the rapidity of his publications, and the crude manner in which he ushered his discoveries to the world. But had he kept them by him till he had brought them to a sufficient degree of maturity, it is obvious that he would have been anticipated in the most important of them by Scheele. 10. In the Memoirs of the Stockholm Academy for 1779, there is a short but curious paper of Scheele, giving an account of some of the results which he had obtained. If a plate of iron be moistened by a solution of common salt, or of sulphate of soda, and left for some weeks in a moist cellar, an efflorescence of carbonate of soda covers the surface of the plate. The same decomposition of common salt and evolution of soda takes place when unslacked quicklime is moistened with a solution of common salt and left in a similar situation. These experiments led afterwards to various methods of decomposing common salt, and obtaining from it carbonate of soda. The phenomena themselves are still wrapped up in considerable obscurity. Berthollet attempted an explanation afterwards in his Chemical Statics, but founded on principles not easily admissible. 11. During the same year, his experiments on plumbago were published. This substance had been long employed for making black lead pencils, but nothing was known concerning its nature. Scheele, with his usual perseverance, tried the effect of all the different reagents, and showed that it consisted chiefly of carbon, but was mixed with a certain quantity of iron. It was concluded from these experiments that plumbago is a carburet of iron, but the quantity of iron differs so enormously in different specimens that this opinion cannot be admitted. Sometimes the iron amounts to only 0.5%, and sometimes to 30%. Plumbago, then, is a carbon mixed with a variable proportion of iron, or carburet of iron. 12. In 1780, Scheele published his experiments on milk, and showed that sour milk contains a peculiar acid, to which the name of lactic acid has been given. He found that when sugar of milk is dissolved in nitric acid, and the solution allowed to cool, small crystalline grains were deposited. These grains have an acid taste, and combine with bases. They have peculiar properties, and therefore constitute a particular acid, to which the name of saclactic was given. It is formed also when gum is dissolved in nitric acid. On this account it has been called mucic acid. 13. In 1781, his experiments on a heavy mineral called by the Swedes tungsten were published. This substance had been much noticed on account of its great weight, but nothing was known respecting its nature. Scheele, with his usual skill and perseverance, succeeded in proving that it was a compound of lime and a peculiar acid, to which the name of tungstic acid was given. Tungsten was, therefore, a tungstate of lime. Bergman, from its great weight, suspected that tungstic acid was in reality the oxide of a metal, and this conjecture was afterwards confirmed by the Alliards, who extracted the same acid from wolfram, and succeeded in reducing it to the metallic state. 14. In 1782 and 1783 appeared his experiments on Prussian blue, in order to discover the nature of the coloring matter. These experiments were exceedingly numerous, and display uncommon ingenuity and sagacity. He succeeded in demonstrating that prussic acid, the name at that time given to the coloring principle, was a compound of carbon and azote. He pointed out a process for obtaining prussic acid in a separate state, and then determined its properties. This paper threw at once a ray of light on one of the obscurest parts of chemistry. If he did not succeed in elucidating this difficult department completely, the fault must not be ascribed to him, but to the state of chemistry when his experiments were made. In fact, it would have been impossible to have gone further till the nature of the different elastic fluids at that time under investigation had been thoroughly established. Perhaps in 1783 there was scarcely any other individual who could have carried out this very difficult investigation, so far as it was carried by Scheele. 15. In 1783 appeared his observations on the sweet principle of oils. He observed that when olive oil and litharge are combined together, a sweet substance separates from the oil and floats on the surface. This substance, when treated with nitric acid, yields oxalic acid. It was therefore closely connected with sugar in its nature. He obtained the same sweet matter from linseed oil, oil of almonds, of rapeseed, from hog's lard, and from butter. He therefore concluded that it was a principle contained in all the expressed or fixed oils. 16. In 1784, he pointed out a method by which citric acid may be obtained in a state of purity from lemon juice. He likewise determined its characters, and showed that it was entitled to rank as a peculiar acid. It was during the same year that he observed a white earthy matter which may be obtained by washing rhubarb in fine powder with a sufficient quantity of water. This earthy matter he decomposed and ascertained that it was a neutral salt, composed of oxalic acid combined with lime. In a subsequent paper, he showed that the same oxalic of lime exists in a great number of roots of various plants. 17. In 1786, he showed that apples contain a peculiar acid, the properties of which he determined, and to which the name of malic acid has been given. In the same paper he examined all the common acid fruits of this country, gooseberries, currants, cherries, bilberries, etc., and determined the peculiar acids which they contain. Some owe their acidity to malic acid, some to citric acid, and some to tartaric acid, and not a few hold 2 or even 3 of these acids at the same time. The same year he showed that the siderum of Bergman was phosphuret of iron, and the acidum perlatum of Proust biphosphate of soda. The only other publications of Scheele during 1785 was a short notice respecting a new mode of preparing magnesia alba. If sulphate of magnesia and common salt, both in solution, be mixed in the requisite proportions, a double decomposition takes place, and there will be formed sulphate of soda and muriate of magnesia. The greatest part of the former salt may be obtained out of the mixed ley by crystallization, and then the magnesia alba may be thrown down from the muriate of magnesia by means of an alkaline carbonate. The advantage of this new process is the procuring of a considerable quantity of sulphate of soda in exchange for a common salt, which is a much cheaper substance. 18. The last paper which Scheele published appeared in the Memoirs of the Stockholm Academy for 1786. In it he gave an account of the characters of gallic acid and the method of obtaining that acid from nut galls. Such is an imperfect sketch of the principal discoveries of Scheele. I have left out of view his controversial papers, which have now lost their interest, and a few others of minor importance that this notice might not be extended beyond its due length. It will be seen that Scheele extended greatly the number of acids. Indeed, he more than doubled the number of these bodies known when he began his chemical labors. The following acids were discovered by him, or at least it was he that first accurately pointed out their characters: fluoric acid, molybdic acid, tungstic acid, arsenic acid, lactic acid, gallic acid, tartaric acid, oxalic acid, citric acid, malic acid, cyclactic, chlorine. To him also we owe the first knowledge of barytes and of the characters of manganese. He determined the nature of the constituents of ammonia and prussic acid. He first determined the compound nature of common air, and the properties of the 2 elastic fluids of which it is composed. What other chemist, either a contemporary or predecessor of Scheele, can be brought in competition with him as a discoverer? And all was performed under the most unpropitious circumstances, and during the continuance of a very short life, for he died in the 44th year of his age. End of section 43 of The History of Chemistry. Recording by Lawrence Trask. InterfaceAudio.com. Section 44 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 3, Progress of Scientific Chemistry in France, Part 1. Chapter 3, Progress of Scientific Chemistry in France. I have already given an account of the state of chemistry in France during the earlier part of the 18th century, as it was cultivated by the Stahlian school. But the new aspect which chemistry put on in Britain in consequence of the discoveries of Black, Cavendish, and Priestley, and the conspicuous part which the gases newly made known was likely to take in the future progress of the science, drew to the study of chemistry some time after the middle of the 18th century, a man who was destined to produce a complete revolution and to introduce the same precision and the same accuracy of deductive reasoning which distinguishes the other branches of natural science. This man was Lavoisier. Antoine Laurent Lavoisier was born in Paris on the 26th of August, 1743. His father, being a man of opulence, shared no expense on his education. His taste for the physical sciences was early displayed, and the progress which he made in them was uncommonly rapid. In the year 1764, a prize was offered by the French government for the best and most economical method of lighting the streets of an extensive city. Young Lavoisier, though at that time only 21 years of age, drew up a memoir on the subject which obtained the gold medal. This essay was inserted in the Memoirs of the French Academy of Sciences for 1768. It was during that year, when he was only 25 years of age, that he became a member of that scientific body. By this time he was fully conscious of his own strength, but he hesitated for some time to which of the sciences he should devote his attention. He tried pretty early to determine, experimentally, some chemical questions which at that time drew the attention of practical chemists. For example, an elaborate paper of his appeared in the Memoirs of the French Academy for 1768 on the composition of gypsum. A point at that time was not settled, but which Lavoisier proved, as Marggraf had done before him, to be a compound of sulphuric acid and lime. In the Memoirs of the Academy for 1770, two papers of his appeared, the object which was to determine whether water could, as Marggraf had pretended, be converted into C-issue by long-continued digestion in glass vessels. Lavoisier found, as Marggraf stated, that when water is digested for a long time in a glass retort, a little silica makes its appearance. But he showed that this silica was wholly derived from the retort. Glass, it is well known, is a compound of silica and a fixed alkali. When water is long digested on it, the glass is slightly corroded, a little alkali is dissolved in the water, and a little silica separated in the form of a powder. He turned a good deal of his attention also to geology, and made repeated journeys with Guettard into almost every part of France. The object in view was an accurate description of the mineralogical structure of France, an object accomplished to a considerable extent by the indefatigable exertions of Guettard, who published different papers on the subject in the Memoirs of the French Academy, accompanied with geological maps, which were at that time rare. The mathematical sciences also engrossed a considerable share of his attention. In short, he displayed no great predilection for one study more than another, but seemed to grasp at every branch of science with equal avidity. While in this state of suspension, he became acquainted with the new and unexpected discoveries of Black, Cavendish, and Priestley respecting the gases. This opened a new creation to his view, and finally determined him to devote himself to scientific chemistry. In the year 1774, he published a volume under the title of Essays, Physical and Chemical. It was divided into two parts. The first part contained an historical detail of everything that had been done on the subject of airs, from the time of Paracelsus down to the year 1774. We have the opinions and experiments of von Helmont, Boyle, Hales, Boerhaave, Stahl, Venel, Seleucus, Black, McBride, Cavendish, and Priestley. We have the history of Meyer's acidum pingue, and the controversy carried on in Germany between Jacquin on one hand and Kranz and Smeth on the other. In the second part, Lavoisier relates his own experiments upon gaseous substances. In the first 4 chapters he shows the truth of Dr. Black's theory of fixed air. In the 4th and 5th chapters he proves that when metallic calces are reduced by heating them with charcoal, an elastic fluid is evolved, precisely of the same nature with carbonic acid gas. In the 6th chapter he shows that when metals are calcined their weight increases, and that a portion of air equal to their increase in weight is absorbed from the surrounding atmosphere. He observed that in a given bulk of air calcination goes on to a certain point and then stops altogether, and that air in which metals have been calcined does not support combustion so well as it did before any such process was performed in it. He also burned phosphorus in a given volume of air, observed the diminution of volume of the air, and the increase in the weight of the phosphorus. Nothing in these essays indicates the smallest suspicion that air was a mixture of 2 distinct fluids, and that only one of them was concerned in combustion and calcination, although this had been already deduced by Scheele from his own experiments, and though Priestley had already discovered the existence and peculiar properties of oxygen gas. It is obvious, however, that Lavoisier was on the way to make these discoveries, and had neither Scheele nor Priestley been fortunate enough to hit upon oxygen gas, it is exceedingly likely that he would himself have been able to have made that discovery. Dr. Priestley, however, happened to be in Paris towards the end of 1774, and exhibited to Lavoisier, in his own laboratory in Paris, the method of procuring oxygen gas from red oxide of mercury. This discovery altered all his views, and speedily suggested not only the nature of atmospheric air, but also what happens during the calcination of metals and the combustion of burning bodies in general. These opinions, when once formed, he prosecuted with unwearied industry for more than 12 years, and after a vast number of experiments, conducted with a degree of precision hitherto unattempted in chemical investigations, he boldly undertook to disprove the existence of phlogiston altogether, and to explain all the phenomena hitherto supposed to depend upon that principle by the simple combination or separation of oxygen from bodies. In these opinions he had for some years no coadjutors or followers, till in 1785 Berthollet, at a meeting of the Academy of Sciences, declared himself a convert. He was followed by M. Fourcroy, and soon after Guyton de Morveau, who was at that time the editor of the chemical department of the Encyclopædia Méthodique, was invited to Paris by Lavoisier, and prevailed upon to join the same party. This was followed by a pretty vigorous controversy in which Lavoisier and his associates gained a signal victory. Lavoisier, after Buffon and Tillet, was treasurer to the Academy, into the accounts of which he introduced both economy and order. He was consulted by the National Convention on the most eligible means of improving the manufacture of assignats, and of augmenting the difficulty of forging them. He turned his attention also to political economy, and between 1778 and 1785 he allotted 240 arpents in the Vendumois to experimental agriculture, and increased the ordinary produce by 1/2. In 1791 the Constituent Assembly invited him to draw up a plan for rendering more simple the collection of the taxes, which produced an excellent report, printed under the title of Territorial Riches of France. In 1776 he was employed by Turgot to inspect the manufactory of gunpowder, which he made to carry 120 toises instead of 90. It is pretty generally known that during the War of the American Revolution the French gunpowder was much superior to the British, but it is perhaps not so generally understood that for this superiority the French government were indebted to the abilities of Lavoisier. During the War of the French Revolution, the quality of the powder of the two nations was reversed, the English being considerably superior to that of the French and capable of carrying further. This was put to the test in a very remarkable way at Cadiz. During the horrors of the dictatorship of Robespierre, Lavoisier began to suspect that he would be stripped of his property, and informed Lalande that he was extremely willing to work for his subsistence. It was supposed that he meant to pursue the profession of an apothecary, as most congenial to his studies, but he was accused, along with the other farmers general, of defrauding the revenue, and thrown into prison. During that sanguinary period, imprisonment and condemnation were synonymous terms. Accordingly, on the 8th of May, 1794, he suffered on the scaffold with 28 farmers general, at the early age of 51. It has been alleged that Fourcroy, who at that time possessed considerable influence, might have saved him had he been disposed to have exerted himself, but this accusation has never been supported by any evidence. Lavoisier was a man of too much eminence to be overlooked, and no accused person at that time could be saved unless he was forgotten. A paper was presented to the tribunal, drawn up by M. Halley, giving a catalogue of the works and a recapitulation of the merits of Lavoisier, but it was thrown aside without even being read, and M. Halley had reason to congratulate himself that his useless attempts to save Lavoisier did not terminate in his own destruction. Lavoisier was tall, and possessed a countenance full of benignity, through which his genius shone forth conspicuous. He was mild, humane, sociable, obliging, and he displayed an incredible degree of activity. His influence was great on account of his fortune, his reputation, and the place which he held in the treasury, but all the use which he made of it was to do good. His wife, whom he married in 1771, was Marie Anna Pierrette Pauls, the daughter of a farmer general, who was put to death at the same time with her husband. She herself was imprisoned, but saved by the fortunate destruction of the dictator himself, together with his abettors. It would appear that she was able to save a considerable part of her husband's fortune. She afterward married Count Rumford, whom she survived. Besides his volume of physical and chemical essays, and his element of chemistry, published in 1789, Lavoisier was the author of no fewer than 60 memoirs, which were published in the volume of the Academy of Sciences from 1772 to 1788, or in other periodical works of the time. I shall take a short review of the most important of these memoirs, dividing them into two parts. 1. Those that are not connected with his peculiar chemical theory, and 2. Those which were intended to disprove the existence of phlogiston and establish the anti-phlogistic theory. 1. I have already mentioned his paper on gypsum, published in the Memoirs of the Academy for 1768. He proves by very decisive experiments that this salt is a compound of sulphuric acid, lime, and water. But this had been already done by Marggraf in a paper inserted into the Memoirs of the Berlin Academy for 1750, entitled An Examination of the Constituent Parts of the Stones that Become Luminous. The most remarkable circumstance attending to this paper is, that an interval of 18 years should elapse without Lavoisier's having any knowledge of this important paper of Marggraf. Yet he quotes Pott and Cronstedt, who had written on the same subject later than Marggraf, at least Cronstedt. What makes this still more singular and unaccountable is that a French translation of Marggraf's Opuscula had been published in Paris in the year 1762. That a man in Lavoisier's circumstances, who, as appears from his paper, had paid considerable attention to chemistry, should not have perused the writings of one of the most eminent chemists that had ever existed, when they were completely within his power, constitutes, I think, one of the most extraordinary phenomena in the history of science. 2. If a want of historical knowledge appears conspicuous in Lavoisier's first chemical paper, the same remark cannot be applied to his second paper, on the nature of water, and the experiments by which it has been attempted to prove the possibility of changing it into earth, which was inserted in the Memoirs of the French Academy for 1770. This memoir is divided into two parts. In the first he gives a history of the progress of opinions on the subject, beginning with Van Helmont's celebrated experiment on the willow, then relating those of Boyle, Trewald, Miller, Eller, Gleditch, Bonnet, Kraft, Alston, Wallerius, Hales, Duhamel, Stahl, Boerhaave, Geoffroy, Marggraf, and Leroy. The first part is interesting in a historical point of view, and gives a very complete account of the progress of opinions upon the subject from the very first dawn of scientific chemistry down to his own time. There is, it is true, a remarkable difference between the opinions of his predecessors respecting the conversion of water into earth, and the experiments of Marggraf on the composition of selenite. The former were inaccurate, and were recorded by him that they might be refuted. But the experiments of Marggraf were accurate, and of the same nature with his own. The second part of this memoir contains his own experiments, made with much precision, which went to show that the earth was derived from the retort in which the experiments of Marggraf were made, and that we have no proof whatever that water may be converted into earth. But these experiments of Lavoisier, though they completely disprove the inferences that Marggraf drew from his observations, by no means demonstrated that water might not be converted into different animal and vegetable substances by the processes of digestion. Indeed, there can be no doubt that this is the case, and that the oxygen and hydrogen of which it is composed enter into the composition of by far the greater number of animal and vegetable bodies produced by the action of the functions of living animals and vegetables. We have no evidence that the carbon, another great constituent of vegetable bodies, and the carbon and azote, which constitute so great a proportion of animal substances, have their origin from water. They are probably derived from the food of plants and animals, and from the atmosphere which surrounds them, which contains both of these principles in abundance. Whether the silica, lime, alumina, magnesia, and iron that exist in small quantity in plants be derived from water and the atmosphere is a question which we are still unable to answer. But the experiments of Schrader, which gained the prize offered by the Berlin Academy in the year 1800 for the best essay on the following subject, to determine the earthy constituents of the different kinds of corn, and to ascertain whether these earthy parts are formed by the processes of vegetation, show at least that we cannot account for their production in any other way. Schrader analyzed the seeds of wheat, rye, barley, and oats, and ascertained the quantity of earthy matter which each contained. He then planted these different seeds in flowers of sulphur, and in oxides of antimony and zinc, watering them regularly with distilled water. They vegetated very well. He then dried the plants and analyzed what had been the produce of a given weight of seed, and he found that the earthy matter in each was greater than it had been in the seeds from which they sprung. Now, as the sulphur and oxides of zinc and antimony could furnish no earthy matter, no other source remains but the water with which the plants were fed, and the atmosphere with which they were surrounded. It may be said, indeed, that earthy matter is always floating about in the atmosphere, and that in this way they may have obtained all the addition of these principles which they contained. This is an objection not easily obviated, and yet it would require to be obviated before the question can be considered as answered. 3. Lavoisier's next paper, inserted in the Memoirs of the Academy for 1771, was entitled Calculations and Observations on the Project of the Establishment of a Steam Engine to Supply Paris with Water. This memoir, though long and valuable, not being strictly speaking chemical, I shall pass over. Mr. Watt's improvements seem to have been unknown to Lavoisier. Indeed, as his patent was only taken out in 1769, and as several years elapsed before the merits of his new steam engine became generally known, Lavoisier's acquaintance with it in 1771 could hardly be expected. 4. In 1772, we find a paper by Lavoisier in the Memoirs of the Academy on the use of spirit of wine in the analysis of mineral waters. He shows how the earthy muriates may be separated from the sulfates by digesting the mixed mass in alcohol. This process no doubt facilitates the separation of the salts from each other, but it is doubtful whether the method does not occasion new inaccuracies that more than compensate for the facility of such separations. When different salts are dissolved in water in small quantities, it may very well happen that they do not decompose each other, being at too great a distance from each other to come within the sphere of mutual action. Thus it is possible that sulfate of soda and muriate of lime may exist together in the same water. But if we concentrate this water very much, and still more if we evaporate to dryness, the two salts will gradually come into the sphere of mutual action. A double decomposition will take place, and there will be formed sulfate of lime and common salt. If upon the dry residue we pour as much distilled water as was driven off by the evaporation, we shall not be able to dissolve all the saline matter deposited. A portion of sulfate of lime will remain in the state of a powder. Yet before the evaporation, all the saline contents of the water were in solution, and they continued in solution till the water was very much concentrated. This is sufficient to show that the nature of the salts was altered by the evaporation. If we digest the dry residue and spirit of wine, we may dissolve a portion of muriate of lime, if the quantity of that salt in the original water was greater than the sulfate of soda was capable of decomposing. But if the quantity was just what the sulfate of soda could decompose, the alcohol will dissolve nothing, if it be strong enough, or nothing but a little common salt, if its specific gravity was above 0.820. We cannot, therefore, depend upon the salts which we obtain after evaporating a mineral water to dryness, being the same as those which existed in the mineral water itself. The nature of the salts must always be determined some other way. End of section 44. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 45 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 3. The Progress of Scientific Chemistry in France, Part 2. 5. In the Memoirs of the Academy for 1772, published in 1776, are inserted two elaborate papers of Lavoisier on the combustion of the diamond. The combustibility of the diamond was suspected by Newton from its great refractive power. His suspicion was confirmed in 1694 by Cosmo III, Grand Duke of Tuscany, who employed Averroni and Targioni to try the effect of powerful burning glasses upon diamonds. They were completely dissipated by the heat. Many years after, the Emperor Francis I caused various diamonds to be exposed to the heat of furnaces. They also were dissipated, without leaving any trace behind them. M. Darcet, professor of chemistry at the Royal College of Paris, being employed with Count Lorgia in a set of experiments on the manufacture of porcelain, took the opportunity of trying what effect the intense heat of the porcelain furnaces produced upon various bodies. Diamonds were not forgotten. He found that they were completely dissipated by the heat of the furnace, without leaving any traces behind them. Darcet found that a violent heat was not necessary to volatilize diamonds. The heat of an ordinary furnace was quite sufficient. In 1771, a diamond belonging to M. Godefroy Villetaneuse was exposed to a strong heat by Marquet. It was placed upon a cupel and raised to a temperature high enough to melt copper. It was observed to be surrounded with a low red flame, and to be more intensely red than the cupel. In short, it exhibited unequivocal marks of undergoing real combustion. These experiments were soon after repeated by Lavoisier before a large company of men of rank and science. The real combustion of the diamond was established beyond doubt, and it was ascertained also that if to be completely excluded from the air, it may be exposed to any temperature that can be raised in a furnace without undergoing any alteration. Hence it is clear that the diamond is not a volatile substance, and that it is dissipated by heat, not by being volatilized, but by being burnt. The object of Lavoisier in his experiments was to determine the nature of the substance into which the diamond was converted by burning. In the first part he gives as usual a history of everything which had been done previous to his own experiments on the combustion of the diamond. In the second part we have the result of his own experiments upon the same subject. He placed diamonds on porcelain supports in glass jars, standing inverted over water and over mercury, and filled with common air and with oxygen gas. The diamonds were consumed by means of burning glasses. No water or smoke or soot made their appearance, and no alteration took place on the bulk of the air when the experiments were made over mercury. When they were made over water, the bulk of the air was somewhat diminished. It was obvious from this that diamond, when burnt in air or oxygen gas, is converted into a gaseous substance, which is absorbed by water. On exposing air in which the diamond had been burnt to lime water, a portion of it was absorbed, and the lime water was rendered milky. From this it became evident that when diamond is burnt, carbonic acid is formed, and this was the only product of the combustion that could be discovered. Lavoisier made similar experiments with charcoal, burning it in air and oxygen gas by means of a burning glass. The results were the same. Carbonic acid gas was formed in abundance, and nothing else. These experiments might have been employed to support and confirm Lavoisier's peculiar theory, and they were employed by him for that purpose afterwards. But when they were originally published, no such intention appeared evident, though doubtless he entertained it. 6. In the second volume of the Journal de Physique for 1772, there is a short paper by Lavoisier on the conversion of water into ice. M. Desmarais had given the Academy an account of Dr. Black's experiments to determine the latent heat of water. This induced Lavoisier to relate his experiments on the same subject. He does not inform us whether they were made in consequence of his having become acquainted with Dr. Black's theory, though there can be no doubt that this must have been the case. The experiments related in this short paper are not of much consequence, but I have thought it worth while to notice it because it authenticates a date at which Lavoisier was acquainted with Dr. Black's theory of latent heat. 7. In the third volume of the Journal de Physique, there is an account of a set of experiments made by Bourdelin, Moulouin, Macquer, Cadet, Lavoisier, and Baume on the white lead ore of Palouin. The report is drawn up by Baume. The nature of the ore is not made out by these experiments. They were mostly made out in the dry way, and were chiefly intended to show that the ore was not a chloride of lead. It was most likely a phosphate of lead. 8. In the Memoirs of the Academy for 1774, we have the experiments of Turton de Montigny, Maquet, Cadet, Lavoisier, and Brisson, with the great burning glass of M. Trudin. The results obtained cannot be easily abridged, and are not of sufficient importance to be given in detail. 9. Analysis of some waters brought from Italy by M. Cassini, Jr. This short paper appeared in the Memoirs of the Academy for 1777. The waters in question were brought from alum pits, and were found to contain alum and sulphate of iron. 10. In the same volume of the Memoirs of the Academy appeared his paper on the ash employed by the saltpetre makers of Paris, and on its use in the manufacture of saltpetre. This is a curious and valuable paper, but not sufficiently important to induce me to give an abstract of it here. 11. In the Memoirs of the Academy for 1777 appeared an elaborate paper by Lavoisier on the combination of the matter of fire with evaporable fluids and the formation of elastic aeriform fluids. In this paper he adopts precisely the same theory as Dr. Black had long before established. It is remarkable that the name of Dr. Black never occurs in the whole paper, though we have seen that Lavoisier had become acquainted with the doctrine of latent heat, at least as early as the year 1772, as he mentioned the circumstance in a short paper inserted that year in the Journal de Physique, and previously read to the Academy. 12. In the same volume of the Memoirs of the Academy, we have a paper entitled Experiments Made by Order of the Academy on the Cold of the year 1775, by Messrs. Bazou, Lavoisier, and Vandermonde. It is sufficiently known that the beginning of the year 1776 was distinguished in most parts of Europe by the weather. The object of this paper, however, is rather to determine the accuracy of the different thermometers at that time used in France than to record the lowest temperature which had been observed. It has some resemblance to a paper drawn up about the same time by Mr. Cavendish, and published in the Philosophical Transactions. 13. In the Memoirs of the Academy for 1778 appeared a paper entitled Analysis of the Waters of the Lake Asphaltes, by Messrs. Mercure, Lavoisier, and Sage. This water is known to be saturated with salt. It is needless to state the result of the analysis contained in this paper, because it is quite inaccurate. Chemical analysis had not at that time made sufficient progress to enable chemists to analyze mineral waters with precision. The observation of Lavoisier and Guettard, which appeared at the same time on a species of steatite, which is converted by the fire into a fine biscuit of porcelain, and on two coal mines, the one in Franche-Comté and the other in Alsace, do not require to be particularly noticed. 14. In the Memoire de l'Académie for 1780, published in 1784, we have a paper by Lavoisier on certain fluids which may be obtained in an aeriform state at a degree of heat not much higher than the mean temperature of the earth. These fluids are sulphuric ether, alcohol, and water. He points out the boiling temperature of these liquids, and shows that at that temperature the vapor of these bodies possess the elasticity of common air, and is permanent as long as the high temperature continues. He burnt a mixture of vapor of ether and oxygen gas, and showed that during the combustion carbonic acid gas is formed. Lavoisier's notions respecting these vapors, and what hindered the liquids at the boiling temperature from being all converted into vapor, were not quite correct. Our opinions respecting steam and vapors in general were first rectified by Mr. Dalton. 15. In the Memoire de l'Académie for 1780 appeared also the celebrated paper on heat by Lavoisier and Laplace. The object of this paper was to determine the specific heat of various bodies, and to investigate the proposals that had been made by Dr. Irvine for determining the point at which a thermometer would stand if plunged into a body destitute of heat. This point is usually called the real zero. They begin by describing an instrument they had contrived to measure the quantity of heat which leaves a body while it is cooling a certain number of degrees. To this instrument they gave the name of calorimeter. It consisted of a kind of a hollow, surrounded on every side by ice. The hot body was put into the center. The heat which it gave out while cooling was all expanded in melting the ice, which was of the temperature of 32 degrees, and the quantity of heat was proportional to the quantity of ice melted. Hence the quantity of ice melted, while equal weights of hot bodies were cooling, A certain number of degrees gave the direct ratios of the specific heats of each. In this way they obtained the following specific heats. Water, 1. Sheet iron, 0.109985. Glass without lead, crystal, 0.1929. Mercury, 0.029. Quicklime, 0.21689. Mixture of 9 water with 16 lime, 0.439116. Sulfuric acid of 1.87058, 0.334597. 4 sulfuric acid, 3 water, 0.603162. 4 sulfuric acid, 5 water, 0.663102. Nitric acid of 1.29895, 0.661391. 9 1/3 nitric acid, 1 lime, 0.61895. 1 saltpeter, 8 water, 0.8167. Their experiments were inconsistent with the conclusions drawn by Dr. Irvin respecting the real zero from the diminution of the specific heat, and the heat evolved when sulfuric acid was mixed with various proportions of water, etc. If the experiments of Lavoisier and Laplace approached nearly to accuracy, or indeed unless they were quite inaccurate, it is obvious that the conclusions of Irvin must be quite erroneous. It is remarkable that though the experiments of Crawford and likewise those of Wilkie and of several others on specific heat had been published before this paper made its appearance, no allusion whatever is made to these publications. Were we to trust to the information communicated in the paper, and the doctrine of specific heat originated with Lavoisier and Laplace, it is true that in the 4th part of the paper, which treats of combustion and respiration, Dr. Crawford's theory of animal heat is mentioned, showing clearly that our authors were acquainted with his book on the subject. And as this theory is found on the different specific heats of bodies, there could be no doubt that he was acquainted with that doctrine. 16. In the Memoire de l'Académie for 1780, occur the 2 following memoirs. Report made to the Royal Academy of Sciences on the prisons, by Messrs. de Hamel, de Montigny, Leroy, Tenon, Tillet, and Lavoisier. Report on the process for separating gold and silver, by Messrs. Macquer, Cadet, Lavoisier, Baume, Cornet, and Berthollet. 17. In the Memoire de l'Académie for 1781, we find a memoir by Lavoisier and Laplace on the electricity evolved when bodies are evaporated or sublimed. The result of these experiments was that when water was evaporated, electricity was always evolved. They concluded from these observations that whenever a body changes, its state electricity is always evolved. But when Saussure attempted to repeat these observations, he could not succeed. And from the recent experiments of Pouillet, it seems to follow that electricity is evolved only when bodies undergo chemical decomposition or combination. Such experiments depend so much upon very minute circumstances, which are apt to escape the attention of the observer, that implicit confidence cannot be put in them till they have been often repeated and varied in every possible manner. 18. In the Memoires de l'Académie for 1781, there is a paper by Lavoisier on the comparative value of different substances employed as articles of fuel. The substances compared to each other are pit coal, coke, charcoal, and wood. It would serve no purpose to state the comparison here, as it would not apply to this country, nor indeed would it at present apply even to France. We have, in the same volume, his paper on the mode of illuminating theatres. 19. In the Memoires de l'Académie for 1782, printed in 1785, we have a paper by Lavoisier on a method of augmenting considerably the action of fire and heat. The method which he proposes is a jet of oxygen gas, striking against red-hot charcoal. He gives the result of some trials made in this way. Platinum readily melted. Pieces of ruby or sapphire were softened sufficiently to run together into one stone. Hyacinth lost its color, and was also softened. Topaz lost its color, and melted into an opaque enamel. Emeralds and garnets lost their color, and melted into opaque colored glasses. Gold and silver were volatilized, and all the other metals, and even the metallic oxides, were found to burn. Barytes also burns when exposed to this violent heat. This led Lavoisier to conclude, as Bergman had done before him, that barytes is a metallic oxide. This opinion has been fully verified by modern chemists. Both silica and alumina were melted, but he could not fuse lime nor magnesia. We are now in possession of a still more powerful source of heat in the oxygen and hydrogen blowpipe, which is capable of fusing both lime and magnesia, and indeed every substance which can be raised to the requisite heat without burning or being volatilized. This subject was prosecuted still further by Lavoisier in another paper inserted in a subsequent volume of the Memoires de l'Académie. He describes the effect on rock crystal, quartz, sandstone, and phosphorescent quartz, milk quartz, agate, chalcedony, cornelian, flint, pras, nephrite, jasper, feldspar, etc. 20. In the same volume is inserted a memoir on the nature of the aeriform elastic fluids, which are disengaged from certain animal substances in a state of fermentation. He found that a quantity of recent human feces, amounting to about 5 cubic inches, when kept at a temperature approaching to 60 degrees, emitted every day for a month about half a cubic inch of gas. This gas was a mixture of 11 parts carbonic acid gas and 1 part of an inflammable gas, which burnt with a blue flame, and was therefore probably carbonic oxide. 5 cubic inches of old human feces from a necessary kept in the same temperature during the first 15 days emitted about a third of a cubic inch of gas each day, and during each of the second 15 days about 1/4 of a cubic inch. This gas was a mixture of 38 volumes of carbonic acid gas and 62 volumes of a combustible gas, burning with a blue flame, and probably carbonic oxide. Fresh feces do not effervesce with dilute sulfuric acid, but old moist feces do, and emit about 8 times their volume of carbonic acid gas. Quicklime, or caustic potash, mixed with feces, puts a stop to the evolution of gas, doubtless by preventing all fermentation. During effervescence of fecal matter, the air surrounding it is deprived of a little of its oxygen, probably in consequence of its combining with the nascent inflammable gas, which is slowly disengaged. 2. We come now to the new theory of combustion of which Lavoisier was the author, and upon which his reputation with posterity will ultimately depend. Upon this subject, or at least upon matters more or less intimately connected with it, no fewer than 27 memoirs of him, many of them of a very elaborate nature, and detailing expensive and difficult experiments, appeared in the different volumes of the Academy between 1774 and 1788. The analogy between the combustion of bodies and the calcination of metals had been already observed by chemists, and all admitted that both processes were owing to the same cause, namely the emission of phlogiston by the burning or calcining body. The opinion adopted by Lavoisier was that during burning and calcination nothing whatever left the bodies, but that they simply united with a portion of the air of the atmosphere. When he first conceived this opinion, he was ignorant of the nature of atmospheric air, and of the existence of oxygen gas. But after that principle had been discovered, and shown to be a constituent of atmospherical air, he soon recognized that it was the union of oxygen with the burning and calcining body that occasioned the phenomena Such is the outline of the Lavoisierian theory stated in the simplest and fewest words. It will be requisite to make a few observations on the much agitated question whether this theory originated with him. It is now well known that John Ray, a physician at Bugue, in Perigord, established a book in 1630 in order to explain the cause of the increase of weight which lead and tin experience during their calcination. After refuting in succession all the different explanations of this increase of weight which had been advanced, he adds, "To this question, then, supported on the grounds already mentioned, I answer, and maintain with confidence, that the increase of weight arises from the air, which is condensed, rendered heavy and adhesive by the violent and long-continued heat of the furnace. This air mixes itself with the calx, frequent agitation conducing, and attaches itself to the minutest molecules, in the same manner as water renders heavy sand which is agitated with it, and moistens and adheres to the smallest grains. There cannot be the least doubt from this passage that Ray's opinion was precisely the same as the original one of Lavoisier, and had Lavoisier done nothing more than merely state in general terms that during calcination air unites with the calcining bodies, it might have been suspected that he had borrowed his notions from those of Ray. But the discovery of oxygen, and the numerous and decisive proofs which he brought forward that during burning and calcination, oxygen unites with the burning and calcining body, and that this oxygen may be again separated and exhibited in its original elastic state, oblige us to alter our opinion. And whether we admit that he borrowed his original notion from Ray, or that it suggested itself to his own mind, the case will not be materially altered. For it is not the man who forms the first vague notion of a thing that really adds to the stock of our knowledge, but he who demonstrates its truth and accurately determines its nature. Ray's book and his opinions were little known. He had not brought over a single convert to his doctrine, a sufficient proof that he had not established it by satisfactory evidence. We may therefore believe Lavoisier's statement, when he assures us that when he first formed his theory, he was ignorant of Ray, and never had heard that any such book had been published. We may therefore believe Lavoisier's statement that when he assures us that when he first formed his theory, he was ignorant of Ray, and never had heard that any such book had been published. The theory of combustion advanced by Dr. Hooke in 1665 in his Micrographia approaches still nearer to that of Lavoisier than the theory of Ray, and indeed, so far as he explained it, the coincidence is exact. End of section 45. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. Section 46 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 3, Progress of Scientific Chemistry in France, Part 3. The theory of combustion advanced by Dr. Hooke in 1665 in his Micrographia approaches still nearer to that of Lavoisier than the theory of Ray, and indeed, so far as he has explained it, the coincidence is exact. According to Hooke, there exists in common air a certain substance which is like, if not the very same, with that which is fixed in saltpeter. This substance has the property of dissolving all combustibles, but only when air temperature is sufficiently raised. The solution takes place with such rapidity that it occasions fire, which in his opinion is mere motion. The dissolved substance may be in the state of air, or coagulated in a liquid or solid form. The quantity of this solvent in a given bulk of air is incomparably less than in the same bulk of saltpeter. Hence the reason why a combustible continues burning but a short time in a given bulk of air. The solvent is soon saturated, and then, of course, the combustion is at an end. This explains why combustion requires a constant supply of fresh air, and why it is promoted by forcing in air with bellows. Hooke promised to develop this theory at greater length in a subsequent work, but he never fulfilled his promise. Though in his Lampus, published about 12 years afterwards, he gives a beautiful chemical explanation of flame, founded on the very same theory. From the very general terms in which Hooke expresses himself, we cannot judge correctly of the extent of his knowledge. This theory, so far as it goes, coincides exactly with our present notions on the subject. His solvent is oxygen gas, which constitutes 1/5 part of the volume of the air, but exists in much greater quantity in saltpeter. It combines with the burning body, and the compound formed may either be a gas, a liquid, or a solid, according to the nature of the body subjected to combustion. Lavoisier nowhere alludes to this theory of Hooke, nor gives the least hint that he had ever heard of it. This is the more surprising, because Hooke was a man of great celebrity, and his Micrographia, as containing the original figures and descriptions of many natural objects, is well known, not merely in Great Britain, but on the continent. At the same time, it must be recollected that Hooke's theory is supported by no evidence, that it is a mere assertion, and that nobody adopted it. Even then, if we were to admit that Lavoisier was acquainted with this theory, it would derogate very little from his merit, which consisted in investigating the phenomena of combustion and calcination, and in showing that oxygen became a constituent of the burnt and calcined bodies. About 10 years after the publication of the Micrographia, Dr. Mayau, of Oxford, published his essays, in the first of which, De Sal Nitro et Spiritu Nitro Aero, he obviously adopts Dr. Hooke's theory of combustion, and he applies it with great ingenuity to explain the nature of respiration. Dr. Mayau's book had been forgotten when the attention of men of science was attracted to it by Dr. Beddoes. Dr. Yeats of Bedford published a very interesting work on the merits of Mayau in 1798. It will be admitted at once by every person who takes the trouble of perusing Mayau's tract that he was not satisfied with mere theory, but proved by actual experiment that air was absorbed during combustion and altered during respiration. He has given figures of his apparatus, and they are very much of the same nature with those afterwards made use of by Lavoisier. It would be wrong, therefore, to deprive Mayau of the reputation to which he is entitled for his ingeniously contrived and well-executed experiments. It must be admitted that he proved both the absorption of air during combustion and respiration, but even this does not take much from the fair fame of Lavoisier. The analysis of air and the discovery of oxygen gas really diminished the analogy between the theories of Mayau and Lavoisier, or at any rate the full investigation of the subject and the generalization of it belong exclusively to Lavoisier. Attempts were made by the other French chemists about the beginning of the Revolution to associate themselves with Lavoisier, as equally entitled with himself to the merit of antiphlogistic theory. But Lavoisier himself has disclaimed the partnership. Some years before his death, he had formed the plan of collecting together all his papers relating to the antiphlogistic theory, and publishing them in one work, but his death interrupted the project. However, his widow afterwards published the first 2 volumes of the book, which were complete at the time of his death. In one of these volumes, Lavoisier claims for himself the exclusive discovery of the cause of the augmentation of weight, which bodies undergo during combustion and calcination. He informs us that a set of experiments, which he made in 1772, upon the different kinds of air which are disengaged in effervescence, and a great number of other chemical operations discovered to him demonstratively the cause of the augmentation of weight which metals experience when exposed to heat. I was young, says he. I had newly entered the lists of science. I was desirous of fame, and I thought it necessary to take some steps to secure to myself the property of my discovery. At that time there existed a habitual correspondence between the men of science of France and those of England. There was a kind of rivalry between the two nations, which gave importance to new experiments, and which sometimes was the cause that the writers of one or the other of the nations disputed the discovery with the real author. Consequently, I thought it proper to deposit on the 1st of November, 1772, the following note in the hands of the Secretary of the Academy. This note was opened on the 1st of May following, and mention of these circumstances marked at the top of the note. It was in the following terms. About 8 days ago I discovered that sulphur in burning, far from losing, augments in weight. That is to say, that from 1 pound of sulphur, much more than 1 pound of vitriolic acid is obtained, without reckoning the humidity of the air. Phosphorus presents the same phenomenon. This augmentation of weight arises from a great quantity of air, which becomes fixed during the combustion, and which combines with the vapors. This discovery, which I confirmed by experiments which I regard as decisive, led me to think that what is observed in the combustion of sulphur and phosphorus might likewise take place with respect to all the bodies which augment in weight by combustion and calcination. And I was persuaded that the augmentation of weight in the calces of metals proceeded from the same cause. The experiment fully confirmed my conjectures. I operated the reduction of litharge in close vessels with Hale's apparatus, and I discovered that at the moment of the passage of the calx into the metallic state, there was a disengagement of air in considerable quantity, and that this air formed a volume at least 1,000 times greater than that of the litharge employed. As this discovery appears to me one of the most interesting which has been made since Stahl, I thought it expedient to secure to myself the property by depositing the present note in the hands of the Secretary of the Academy, to remain secret till the period when I shall publish my experiments. Lavoisier, Paris, November 11th, 1772. This note leaves no doubt that Lavoisier had conceived his theory, and confirmed it by experiment, at least as early as November, 1772. But at that time the nature of air and the existence of oxygen were unknown. The theory, therefore, as he understood it at that time, was precisely the same as that of John Ray. It was not till the end of 1774 that his views became more precise, and that he was aware that oxygen is the portion of the air which unites with bodies during combustion and calcination. Nothing can be more evident from the whole history of the Academy and of the French chemists during this eventful period, for the progress of the science, that none of them participated in the views of Lavoisier, or had the least intention of giving up the phlogistic theory. It was not till 1785, after all the difficulties had been removed by the two great discoveries of Mr. Cavendish, that Berthollet declared himself a convert to the Lavoisierian opinions. This was soon followed by others, and within a very few years almost all the chemists and men of science in France enlisted themselves on the same side. Lavoisier's objection, then, to the phrase la chimie française is not without reason. The term Lavoisierian chemistry should undoubtedly be substituted for it. The term la chimie française was introduced by Fourcroy. Was Fourcroy anxious to clothe himself with the reputation of Lavoisier, and had this any connection with the violent death of that illustrious man? The first set of experiments which Lavoisier published on his peculiar views was entitled A Memoir on the Calcination of Tin in Close Vessels, and on the cause of the increase of weight which the metal acquires during this process. It appeared in the Memoirs of the Academy for 1774. In this paper he gives an account of several experiments which he had made on the calcination of tin in glass retorts, hermetically sealed. He put a quantity of tin, about half a pound, into a glass retort, sometimes of a larger and sometimes of a smaller size, and then drew out the beak into a capillary tube. The retort was now placed upon the sand bath, and heated till the tin just melted. The extremity of the capillary beak of the retort was now fused so as to seal it hermetically. The object of this heating was to prevent the retort from bursting by the expansion of the air during the process. The retort with its contents was now carefully weighed and the weight noted. It was put again on the sand bath and kept melted till the process of calcination refused to advance any further. He observed that if the retort was small, the calcination always stopped sooner than it did if the retort was large, or in other words, the quantity of tin calcined was always proportional to the size of the retort. After the process was finished, the retort, still hermetically sealed, was again weighed, and was always found to have the same weight exactly as at first. The beak of the retort was now broken off, and a quantity of air entered with a hissing noise. The increase in weight was now noted. It was obviously owing to the air that had rushed in. The weight of the air that had been at first driven out by the fusion of the tin had been noted, and it was now found that a considerably greater quantity had entered than had been driven out at first. In some experiments, as much as 10.06 grains, in others 9.87 grains, and in some less than this, when the size of the retort was small. The tin in the retort was mostly unaltered, but a portion of it had been converted into a black powder, weighing in some cases above 2 ounces. Now it was found in all cases that the weight of the tin had increased, and the increase in weight was always exactly equal to the diminution of weight which the air in the retort had undergone, measured by the quantity of new air which rushed in when the beak of the retort was broken, minus the air that had been driven out when the tin was originally melted before the retort was hermetically sealed. Thus Lavoisier proved by the first experiments that when tin is calcined in close vessels, a portion of the air of the vessel disappears, and that the tin increases in weight just as much as is equivalent to the loss of weight which the air has sustained. He therefore inferred that this portion of air had united with the tin, and that calx of tin is a compound of tin and air. In this first paper there is nothing said about oxygen, nor any allusion to lead to the suspicion that air is a compound of different elastic fluids. These, therefore, were probably the experiments to which Lavoisier alludes in the note which he lodged with the Secretary of the Academy in November 1772. He mentions toward the end of the memoir that he had made similar experiments with lead, but he does not communicate any of the numerical results, probably because the results were not so striking as those with tin. The heat necessary to melt lead is so high that satisfactory experiments on its calcination could not be easily made in a glass retort. Lavoisier's next memoir appeared in the Memoirs of the Academy for 1775, which were published in 1778. It is entitled On the Nature of the Principle which combines with the Metals during their calcination, and which augments their weight. He observes that when the metallic calces are reduced to the metallic state, it is found necessary to heat them along with charcoal. In such cases a quantity of carbonic acid gas is driven off, which he assures us is the charcoal united to the elastic fluid contained in the calx. He tried to reduce the calx of iron by means of burning glasses, while placed under large glass receivers standing over mercury. But as the gas thus evolved was mixed with a great deal of common air which was necessarily left in the receiver, he was unable to determine its nature. This induced him to have recourse to red oxide of mercury. He showed in the first place that this substance, mercurius precipitatus per se, was a true calx, by mixing it with charcoal powder in a retort and heating it. The mercury was reduced, and abundance of carbonic acid gas was collected in an inverted glass jar standing in a water cistern into which the beak of the retort was plunged. On heating the red oxide of mercury by itself, it was reduced to the metallic state, though not so easily, and at the same time a gas was evolved which possessed the following properties. It did not combine with water by agitation. It did not precipitate lime water. It did not unite with fixed or volatile alkalis. It did not at all diminish their caustic quality. It would serve again for the calcination of metals. It was diminished like common air by addition of 1/3 of nitrous gas. It had none of the properties of carbonic acid gas. Far from being fatal, like that gas, to animals, it seemed on the contrary more proper for the purposes of respiration. Candles and burning bodies were not only extinguished by it, but burned with an enlarged flame in a very remarkable manner. The light they gave was much greater and clearer than in common air. He expresses his opinion that the same kind of air would be obtained by heating niter without addition, and this opinion is founded on the fact that when niter is detonated with charcoal, it gives out abundance of carbonic acid gas. Thus Lavoisier shows in this paper that the kind of air which unites with metals during their calcination is purer and fitter for combustion than common air. In short, it is the gas which Dr. Priestley had discovered in 1774, and which is now known by the name of oxygen gas. This memoir deserves a few animadversions. Dr. Priestley discovered oxygen gas in August 1774, and he informs us in his life that in the autumn of that year he went to Paris and exhibited to Lavoisier in his own laboratory the mode of obtaining oxygen gas by heating red oxide of mercury in a gun barrel, and the properties by which this gas is distinguished. Indeed, the very properties which Lavoisier himself enumerates in his paper. There can therefore be no doubt that Lavoisier was acquainted with oxygen gas in 1774, and that he owed his knowledge of it to Dr. Priestley. There is some uncertainty about the date of Lavoisier's paper. In the History of the Academy for 1775, it merely said about it, read at the Assumption rentrée of the Academy on the 26th of April by M. Lavoisier, without naming the year. But it could not have been before 1775, because that is the year upon the volume of the Memoirs. And besides, we know from the Journal de Physique, version 429, that 1775 was the year on which the paper of Lavoisier was read. Yet in the whole of this paper the name of Dr. Priestley never occurs, nor is the last hint given that he had already obtained oxygen gas by heating red oxide of mercury. So far from it that it is obviously the intention of the author of the paper to induce his readers to infer that he himself was the discoverer of oxygen gas. For after describing the process by which oxygen gas was obtained by him, he says nothing further remained but to determine its nature. And I discovered with much surprise that it was not capable of combination with water by agitation, etc. Now, why the expression of surprise in describing phenomena which had been already shown? And why the omission of all mention of Dr. Priestley's name? I confess that this seems to me capable of no other explanation than a wish to claim for himself the discovery of oxygen gas, though he knew well that that discovery had been previously made by another. The next set of experiments made by Lavoisier to confirm or extend his theory was on the combustion of phosphorus and the nature of the acid which results from that combustion. It appeared in the Memoirs of the Academy for 1777. The result of these experiments was very striking. When phosphorus is burnt in a given bulk of air in sufficient quantity, about 4/5 of the volume of the air disappears and unites itself with the phosphorus. The residual portion of the air is incapable of supporting combustion or maintaining animal life. Lavoisier gave it the name of mouffet atmosphérique, and he describes several of its properties. The phosphorus, by combining with the portion of air which has disappeared, is converted into phosphoric acid, which is deposited on the inside of the receiver in which the combustion is performed, in the state of fine white flakes. 1 grain by this process is converted into 2½ grains of phosphoric acid. These observations led to the conclusion that atmospheric air is a mixture or compound of two distinct gases. The one, oxygen, is absorbed by burning phosphorus; the other, azote, not acted on by that principle, and not capable of uniting with or calcining metals. These conclusions had already been drawn by Scheele from similar experiments, but Lavoisier was ignorant of them. In the second part of this paper, Lavoisier describes the properties of phosphoric acid, and gives an account of the salts which it forms with the different bases. The account of these salts is exceedingly imperfect, and it is remarkable that Lavoisier makes no distinction between phosphate of potash and phosphate of soda, though the different properties of these two salts are not a little striking. But these were not the investigations in which Lavoisier excelled. End of section 46. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 47 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 3, Progress of Scientific Chemistry in France, Part 4. The next paper, in which the doctrines of the antiphlogistic theory were still further developed, was inserted in the Memoirs of the Academy for 1777. It is entitled On the Combustion of Candles in Atmospherical Air, and in Air Eminently Respirable. This paper is remarkable because in it he first notices Dr. Priestley's discovery of oxygen gas, but without any reference to the preceding paper, or any apology for not having alluded in it to the information which he had received from Dr. Priestley. He begins by saying that it is necessary to distinguish four different kinds of air. 1. Atmospherical air, in which we live and in which we breathe. 2. Pure air, oxygen, alone fit for breathing, constituting about the fourth of the volume of atmospherical air, and called by Dr. Priestley dephlogisticated air. 3. Azotic gas, which constitutes about 3/4 of the volume of atmospherical air, and whose properties are still unknown. 4. Fixed air, which he proposed to call, as Buquet had done, acid crayeux, acid of chalk. In this paper Lavoisier gives an account of a great many trials that he made by burning candles in given volumes of atmospherical air and oxygen gas enclosed in glass receivers, standing over mercury. The general conclusion which he deduces from these experiments are that the azotic gas of the air contributes nothing to the burning of the candle, but the whole depends upon the oxygen gas of the air, constituting, in his opinion, 1/4 of its volume; that during the combustion of a candle in a given volume of air only 2/5 of the oxygen are converted into carbonic acid gas, while the remaining 3/5 remain unaltered. But when the combustion goes on in oxygen gas, a much greater proportion, almost the whole of this gas, is converted into carbonic acid gas. Finally, that phosphorus, when burnt in air, acts much more powerfully on the oxygen of the air than a lighted candle, absorbing 4/5 of the oxygen and converting it into phosphoric acid. It is evident that at the time this paper was written, Lavoisier's theory was nearly complete. He considered air as a mixture of the 3 volumes of azotic gas and 1 volume of oxygen gas. The last alone was concerned in combustion and calcination. During these processes, a portion of the oxygen united with the burning body, and the compound formed constituted the acid or the calx. Thus he was able to account for combustion and calcination without having recourse to phlogiston. It is true that several difficulties still lay in his way, which he was not yet able to obviate, and which prevented any other person from adopting his opinions. One of the greatest of these was the fact that hydrogen gas was evolved during the solution of several metals in dilute sulfuric or muriatic acid; that by this solution these metals were converted into calces, and that calces, when heated in hydrogen gas, were reduced to the metallic state while the hydrogen disappeared. The simplest explanation of these phenomena was the one adopted by chemists at the time. Hydrogen was considered as phlogiston. By dissolving metals in acids, the phlogiston was driven off and the calx remained. By heating the calx in hydrogen, the phlogiston was again absorbed and the calx reduced to the metallic state. This explanation was so simple and appeared so satisfactory that it was universally adopted by chemists, with the exception of Lavoisier himself. There was a circumstance, however, which satisfied him that this explanation, however plausible, was not correct. The calx was heavier than the metal from which it had been produced, and hydrogen, though a light body, was still possessed of weight. It was obviously impossible, then, that the metal could be a combination of the calx and hydrogen. Besides, he had ascertained by direct experiment that the calces of mercury, tin, and lead are compounds of the respective metals and oxygen, and it was known when the other calces were heated with charcoal, they were reduced to the metallic state, and at the same time carbonic acid gas is evolved. The very same evolution takes place when calces of mercury, tin, and lead are heated with charcoal powder. Hence the inference was obvious that carbonic acid is a compound of charcoal and oxygen, and therefore that all calces are compounds of their respective metals and oxygen. Thus, although Lavoisier was unable to account for the phenomena connected with the evolution and absorption of hydrogen gas, he had conclusive evidence that the orthodox explanation was not the true one. He wisely, therefore, left it to time to throw light upon those parts of the theory that were still obscure. His next paper, which was likewise inserted in the Memoirs of the Academy for 1777, had some tendency to throw light on this subject, or at least it elucidated the constitution of sulfuric acid, which bore directly upon the antiphlogistic theory. It was entitled On the Solution of Mercury in Vitriolic Acid, and on the resolution of that acid into aeriform sulphurous acid, and into air eminently respirable. He had already proved that sulphuric acid is a compound of sulphur and oxygen, and had even shown how the oxygen which the acid contained might be again separated from it, and exhibited in a separate state. Dr. Priestley had by this time made known the method of procuring sulphurous acid gas, by heating a mixture of mercury and sulphuric acid in a phial. This was the process which Lavoisier analyzed in the present paper. He put into a retort a mixture of 4 ounces mercury and 6 ounces concentrated sulphuric acid. The beak of the retort was plunged into a mercurial cistern to collect the sulphurous acid gas as it was evolved, and heat being applied to the belly of the retort, sulphurous acid gas passed over in abundance, and sulphate of mercury was formed. The process was continued till the whole liquid contents of the retort had disappeared. Then a strong heat was applied to the salt. In the first place, a quantity of sulphurous acid gas passed over, and lastly a portion of oxygen gas. The quicksilver was reduced to the metallic state. Thus he resolved sulphuric acid into sulphurous acid and oxygen. Hence it followed as a consequence that sulphurous acid differs from sulphuric merely by containing a smaller quantity of oxygen. The object of his next paper, published at the same time, was to throw light upon the pyrophorus of Homburg, which was made by kneading alum into a cake with flour, or some substance containing abundance of carbon, and then exposing the mixture to a strong heat in close vessels, till it ceased to give out smoke. It was known that a pyrophorus thus formed takes fire of its own accord, and burns when it comes in contact with common air. It will not be necessary to enter into a minute analysis of this paper, because though the experiments were very carefully made, yet it was impossible, at the time when the paper was drawn, to elucidate the phenomena of this pyrophorus in a satisfactory manner. There can be little doubt that pyrophorus owes its property of catching fire, when in contact with air or oxygen, to a little potassium, which has been reduced to the metallic state by the action of the charcoal and sulfur on the potash in the alum. This substance taking fire, heat enough is produced to set fire to the carbon and sulfur which the pyrophorus contains. Lavoisier ascertained that during its combustion a good deal of carbonic acid was generated. There appeared likewise another paper by Lavoisier in the same volume of the Academy, which may be mentioned, as it served still further to demonstrate the truth of the antiphlogistic theory. It is entitled, On the Vitriolization of Martial Pyrites. Iron pyrites is known to be a compound of iron and sulfur. Sometimes this mineral may be left exposed to the air without undergoing any alteration, while at other times it speedily splits, effervesces, swells, and is converted into sulfate of iron. There are two species of pyrites, the one composed of 2 atoms of sulfur and 1 atom of iron, the other of 1 atom of sulfur and 1 atom of iron. The first of these is called bisulfurate of iron, the second protosulfurate, or simply sulfurate of iron. The variety of pyrites which undergoes spontaneous decomposition in the air is known to be a compound, or rather mixture, of the 2 species of pyrites. Lavoisier put a quantity of the decomposing pyrites under a glass jar, and found that the process went on just as well as in the open air. He found that the air was deprived of the whole of its oxygen by the process, and that nothing was left but azotic gas. Hence the nature of the change became evident. The sulfur, by uniting with oxygen, was converted into sulfuric acid, while the iron became oxide of iron, and both uniting formed sulfate of iron. There are still some difficulties connected with this change that require to be elucidated. We have still another paper by Lavoisier bearing on the antiphlogistic theory, published in the same volume of the Memoirs of the Academy, for 1778, entitled On Combustion in General. He establishes that the only air capable of supporting combustion is oxygen gas, that during the burning of bodies in common air, a portion of the oxygen of the atmosphere disappears and unites with the burning body, and that the new compound formed is either an acid or metallic calx. When sulfur is burnt, sulfuric acid is formed. When phosphorus, phosphoric acid, and when charcoal, carbonic acid. The calcination of metals is a process analogous to combustion, differing chiefly by the slowness of the process. Indeed, when it takes place rapidly, actual combustion is produced. After establishing these general principles, which are deduced from his preceding papers, he proceeds to examine the Stahlian theory of phlogiston, and shows that no evidence of the existence of any such principle can be adduced, and that the phenomena can all be explained without having recourse to it. Powerful as these arguments were, they produced no immediate effects. Nobody chose to give up the phlogistic theory to which he had been so long accustomed. The next 2 papers of Lavoisier require merely to be mentioned, as they do not bear immediately upon the antiphlogistic theory. They appeared in the Memoirs of the Academy for 1780. These memoirs were: 1. Second memoir on the different combinations of phosphoric acid. 2. On a particular process by means of which phosphorus may be converted into phosphoric acid without combustion. The process here described consisted in throwing phosphorus, by a few grains at a time, into warm nitric acid of the specific gravity 1.29895. It falls to the bottom like melted wax, and dissolves pretty rapidly with effervescence. Then another portion is thrown in, and the process is continued till as much phosphorus has been employed as is wanted. Then the phosphoric acid may be obtained pure by distilling off the remaining nitric acid, with which it is still mixed. Hitherto Lavoisier had been unable to explain the anomalies respecting hydrogen gas, or to answer the objections urged against his theory in consequence of these anomalies. He had made several attempts to discover what peculiar substance was formed during the combustion of hydrogen, but always without success. At last, in 1783, he resolved to make the experiment upon so large a scale that whatever the product might be, it should not escape him. But Sir Charles Blagden, who had just gone to Paris, informed him that the experiment which he was preparing had already been made by Mr. Cavendish, who had ascertained that the product of the combustion of hydrogen was water. Lavoisier saw at a glance the vast importance of this discovery for the establishment of the antiphlogistic theory, and with what ease it would enable him to answer all the plausible objections which had been brought forward against his opinions in consequence of the evolution of hydrogen, when metals were calcined by solution in acids, and the absorption of it when metals were reduced in an atmosphere of this gas. He therefore resolved to repeat the experiment of Cavendish with every possible care, and upon a scale sufficiently large to prevent ambiguity. The experiment was made on the 24th of June, 1783, by Lavoisier and Laplace, in the presence of M. Leroy, M. Verdemond, and Sir Charles Blagden, who was at that time Secretary of the Royal Society. The quantity of water formed was considerable, and they found that water was a compound of 1 volume oxygen and 1.91 volume hydrogen. Not satisfied with this, he soon after made another experiment, along with M. Meusnier, to decompose water. For this purpose, a porcelain tube, filled with iron water, was heated red hot by being passed through a furnace, and then the steam of water was made to traverse the red-hot wire. To the further extremity of the porcelain tube, a glass tube was luted, which terminated in a water trough under an inverted glass receiver placed to collect the gas. The steam was decomposed by the red-hot iron wire, its oxygen united to the wire, while the hydrogen passed on and was collected in the water cistern. Both of these experiments, though not made till 1783, and though the latter of them was not read to the Academy till 1784, were published in the volume of the Memoirs for 1781. It is easy to see how this important discovery enabled Lavoisier to obviate all the objections to his theory from hydrogen. He showed that it was evolved when zinc or iron was dissolved in dilute sulfuric acid, because the water underwent decomposition, its oxygen uniting to the zinc or iron, and converting it into an oxide, while its hydrogen made its escape in the state of gas. Oxide of iron was reduced when heated in contact with hydrogen gas, because the hydrogen united to the oxygen of the acid and formed water. And of course the iron was reduced to the state of a metal. I consider it unnecessary to enter into a minute detail of these experiments, because in fact they added very little to what had been already established by Cavendish. But it was this discovery that contributed more than anything else to establish the antiphlogistic theory. Accordingly, the great object of Dr. Priestley and other advocates of the phlogistic theory was to disprove the fact that water is a compound of oxygen and hydrogen. Scheele admitted the fact that water is a compound of oxygen and hydrogen, and doubtless, had he lived, would have been a convert to the antiphlogistic theory, as Dr. Black actually did. In short, it was the discovery of the compound nature of water that gave the Lavoisierian theory the superiority over that of Stahl. Till the time of this discovery, every body opposed the doctrine of Lavoisier, but within a very few years after it, hardly any supporters of phlogiston remained. Nothing could be more fortunate for Lavoisier than this discovery, or afford him greater reason for self-congratulation. We see the effect of this discovery upon his next paper, on the formation of carbonic acid, which appeared in the Memoirs of the Academy for 1781. There, for the first time, he introduces new terms, showing by that he considered his opinions as fully established. To the dephlogisticated air of Priestley, or his own pure air, he now gives the name of oxygen. The fixed air of Black he designates carbonic acid, because he considered it as a compound of carbon, the pure part of charcoal, and oxygen. The object of this paper is to determine the proportions of the constituents. He details a great many experiments, and deduces from them all that carbonic acid gas is a compound of carbon, 0.75, and oxygen, 1.93. Now, this is a tolerably near approximation to the truth, the true constituents as determined by modern chemists being carbon, 0.75, and oxygen, 2. The next paper of M. Lavoisier, which appeared in the Memoirs of the Academy for 1782, published in 1785, shows how well he appreciated the importance of the discovery of the composition of water. It is entitled General Considerations on the Solution of the Metals in Acids. He shows that when metals are dissolved in acids, they are converted into oxides, and that the acid does not combine with the metal, but only with its oxide. When nitric acid is the solvent, the oxidizement takes place at the expense of the acid, which is resolved into nitrous gas and oxygen. The nitrous gas makes it escape, and may be collected, but the oxygen unites with the metal, and renders it an oxide. He shows this with respect to the solution of mercury in nitric acid. He collected the nitrous gas given out during the solution of the metal in the acid, then evaporated the solution to dryness, and urged the fire till the mercury was converted into red oxide. The fire being still further urged, the red oxide was reduced, and the oxygen gas given off was collected and measured. He showed that the nitrous gas and the oxygen gas thus obtained, added together, formed just the quantity of nitric acid which had disappeared during the process. A similar experiment was made by dissolving iron in nitric acid, and then urging the fire till the iron was freed from every foreign body, and obtained in the state of black oxide. End of section 47. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 48 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 3. Progress of Scientific Chemistry in France, Part 5. It is well known that many metals held in solution by acids may be precipitated in the metallic state by inserting into the solution a plate of some other metal. A portion of that new metal dissolves and takes the place of the metal originally in solution. Suppose, for example, that we have a neutral solution of copper in sulfuric acid. If we put into the solution a plate of iron, the copper is thrown down in the metallic state, while a certain portion of the iron enters into the solution, combining with the acid instead of the copper. But the copper, while in solution, was in the state of an oxide, and it is precipitated in the metallic state. The iron was in the metallic state, but it enters into the solution in the state of an oxide. It is clear from this that the oxygen, during these precipitations, shifts its place, leaving the copper and entering into combination with the iron. If, therefore, in such a case we determine the exact quantity of copper thrown down and the exact quantity of iron dissolved at the same time, it is clear that we shall have the relative weight of each combined with the same weight of oxygen. If, for example, 4 of copper be thrown down by the solution of 3 to 5 of iron, then it is clear that 3 to 5 of iron requires just as much oxygen as 4 of copper to turn both into the oxide that exists in the solution, which is the black oxide of each. Bergman had made a set of experiments to determine the proportional quantities of phlogiston contained in the different metals by a relative quantity of each necessary to precipitate a given weight of another form its acid solution. It was the opinion at the time that metals were compounds of their respective calces and phlogiston. When a metal dissolved in an acid, it was known to be in the state of calx, and therefore had parted with its phlogiston. When another metal was put into the solution, it became a calx, and the dissolved metal was precipitated in the metallic state. It had therefore united with the phlogiston of the precipitating metal. It is obvious that by determining the quantities of the two metals precipitated and dissolved, the relative proportion of phlogiston in each could be determined. Lavoisier saw that these experiments of Bergman would serve equally to determine the relative quantity of oxygen in the different oxides. Accordingly, in a paper inserted in the Memoirs of the Academy for 1782, he enters into an elaborate examination of Bergman's experiments, with a view to determine this point. But it is unnecessary to state the deductions which he drew, because Bergman's experiments were not sufficiently accurate for the object in view. Indeed, as the mutual precipitation of the metals is a galvanic phenomenon, and as the precipitated metal is seldom quite pure, but an alloy of the precipitating and precipitated metal, and as it is very difficult to dry the more oxidizable metals, as copper and tin, without their absorbing oxygen when they are in the state of very minute division, this mode of experimenting is not precise enough for the object which Lavoisier had in view. Accordingly, the table of the composition of the metallic oxides which Lavoisier has drawn up is so very defective that it is not worth while to transcribe it. The same remark applies to the table of the affinities of oxygen which Lavoisier drew up and inserted in the Memoirs of the Academy for the same year. His data were too imperfect, and his knowledge too limited, to put in his power to draw up any such table without any approach to accuracy. I shall have occasion to resume the subject in a subsequent chapter. In the same volume of the Memoirs of the Academy, this indefatigable man inserted a paper in order to determine the quantity of oxygen which combines with iron. His method of proceeding was to burn a given weight of iron in oxygen gas. It is well known that iron wire, under such circumstances, burns with considerable splendor, and that the oxide, by the heat, is fused into a black brittle matter, having somewhat of the metallic luster. He burnt 145.6 grains of iron in this way, and found that, after combustion, the weight became 192 grains, and 97 French cubic inches of oxygen gas had been absorbed. From this experiment it follows that the oxide of iron formed by burning iron in oxygen gas is a compound of iron 3.5, oxygen 1.11. This forms a tolerable approximation to the truth. It is now known that the quantity of oxygen in the oxide of iron formed by the combustion of iron in oxygen gas is not quite uniform in its composition. Sometimes it is a compound of iron 3.5 and oxygen 1 1/3, while at other times it consists very nearly of iron 3.5, oxygen 1. And probably it may exist in all the intermediate proportions between these two extremes. The last of these compounds constitutes what is now known by the name of protoxide, or black oxide of iron. The first is the composition of the ore of iron so abundant, which is distinguished by the name of magnetic iron ore. Lavoisier was aware that iron combines with more oxygen than exists in the protoxide. Indeed, his analysis of peroxide of iron forms a tolerable approximation to the truth. But there is no reason for believing that he was aware that iron is capable of forming only two oxides, and that all intermediate degrees of oxidation are impossible. This was first demonstrated by Proust. I think it unnecessary to enter into any details respecting two papers of Lavoisier that made their appearance in the Memoirs of the Academy for 1783, as they add very little to what he had already done. The first of these describes the experiments which he made to determine the quantity of oxygen which unites with sulfur and phosphorus when they are burnt. It contains no fact which had not been stated in his former papers, unless we are to consider his remark that the heat given out during the burning of these bodies has no sensible weight as new. The other paper is on phlogiston. It is very elaborate, but contains nothing which had not been already advanced in his preceding memoirs. Chemists were so wedded to the phlogistic theory, their prejudices were so strong, and their understandings so fortified against everything that was likely to change their opinions, that Lavoisier found it necessary to lay the same facts before them again and again, and to place them in every point of view. In this paper he gives a statement of his own theory of combustion, which he had previously done in several preceding papers. He examines the phlogistic theory of Stahl at great length and refutes it. In the Memoirs of the Academy for 1784, Lavoisier published a very elaborate set of experiments on the combustion of alcohol, oil, and different combustible bodies, which gave a beginning to the analysis of vegetable substances, and served as a foundation upon which this most difficult part of chemistry might be reared. He showed that during the combustion of alcohol, the oxygen of the air united to the vapor of the alcohol, which underwent decomposition, and was converted into water and carbonic acid. From these experiments, he deduced as a consequence that the constituents of alcohol are carbon, hydrogen, and oxygen, and nothing else. And he endeavored, from his experiments, to determine the relative proportions of these different constituents. From these experiments he concluded that the alcohol which he used in his experiments was a compound of carbon, 2,629.5 part, hydrogen, 725.5, water, 5,861. It would serve no purpose to attempt to draw any consequences from these experiments, as Lavoisier does not mention the specific gravity of the alcohol. Of course, we cannot say how much of the water was found merely united with the alcohol, and how much entered into its composition. The proportion between the carbon and hydrogen constitutes an approximation to the truth, though not a very near one. Olive oil he showed to be a compound of hydrogen and carbon, and beeswax to be a compound of the same constituents, though in a different proportion. This subject was continued, and his views further extended, in a paper inserted in the Memoirs of the Academy for 1786, entitled Reflections on the Decomposition of Water by Vegetable and Animal Substances. He begins by stating that when charcoal is exposed to a strong heat, it gives out a little carbonic acid gas and a little inflammable air, and after this nothing more can be driven off, however high the temperature be to which it is exposed. But if the charcoal be left for some time in contact with the atmosphere, it will again give out a little carbonic acid gas and inflammable gas when heated, and this process may be repeated till the whole charcoal disappears. This is owing to the presence of a little moisture which the charcoal imbibes from the air. The water is decomposed when the charcoal is heated and converted into carbonic acid and inflammable gas. When vegetable substances are heated in a retort, the water which they contain undergoes a similar decomposition. The carbon, which forms one of their constituents, combines with the oxygen and produces carbonic acid, while the hydrogen, the other constituent of the water, flies off in a state of gas combined with a certain quantity of carbon. Hence, the substances obtained when vegetable or animal substances are distilled did not exist ready-formed in the body operated on, but proceeded from the double decompositions which took place by the mutual action of the constituents of the water, sugar, mucus, etc., which the vegetable body contains. The oil, the acid, etc., extracted by distilling vegetable bodies did not exist in them, but are formed during the mutual action of the constituents upon each other, promoted as their action is by the heat. These views were quite new and perfectly just, and threw a new light on the nature of vegetable substances and on the products obtained by distilling them. It showed the futility of all the pretended analysis of vegetable substances which chemists had performed by simply subjecting them to distillation, and the error of drawing any conclusions respecting the constituents of vegetable substances from the results of their distillation, except indeed with respect to their elementary constituents. Thus, when by distilling a vegetable substance we obtain water, oil, acetic acid, carbonic acid, and carburetted hydrogen, we must not conclude that these principles existed in the substance, but merely that it contained carbon, hydrogen, and oxygen, in such proportions as to yield all these principles by decompositions. As nitric acid acts upon metals in a very different way from sulfuric and muriatic acids, and as it is a much better solvent of metals in general than any other, it was an object of great importance towards completing the antiphlogistic theory to obtain an accurate knowledge of its constituents. Though Lavoisier did not succeed in this, yet he made at least a certain progress, which enabled him to explain the phenomena, at that time known, with considerable clearness, and to answer all the objections of the antiphlogistic theory from the action of nitric acid on metals. His first paper on the subject was published in the Memoirs of the Academy for 1776. He put a quantity of nitric acid and mercury into a retort with a long beak, which he plunged into the water trough. An effervescence took place, and gas passed over in abundance, and was collected in a glass jar. The mercury being dissolved, the retort was still further heated, till everything liquid passed over into the receiver, and a dry yellow salt remained. The beak of the retort was now again plunged into the water trough, and the salt heated till all the nitric acid which it contained was decomposed, and nothing remained in the retort but a red oxide of mercury. During this last process, much more gas was collected. All the gas obtained during the solution of the mercury and the decomposition of the salt was nitrous gas. The red oxide of mercury was now heated to redness. Oxygen gas was emitted in abundance, and the mercury was reduced to the metallic state. Its weight was found the very same as at first. It is clear, therefore, that the nitrous gas and the oxygen gas were derived, not from the mercury, but from the nitric acid, and that the nitric acid had been decomposed into nitrous gas and oxygen. The nitrous gas had made its escape in the form of gas, and the oxygen had remained united to the metal. From these experiments it follows clearly that nitric acid is a compound of nitrous gas and oxygen. The nature of nitrous gas itself Lavoisier did not succeed in ascertaining. It passed with him for a simple substance, but what he did ascertain enabled him to explain the action of nitric acid on metals. When nitric acid is poured upon a metal, which it is capable of dissolving, copper, for example, or mercury, the oxygen of the acid unites to the metal and converts into an oxide, while the nitrous gas, the other constituent of the acid, makes its escape in the gaseous form. The oxide combines with and is dissolved by another portion of the acid, which escapes decomposition. It was discovered by Dr. Priestley that when nitrous gas and oxygen gas are mixed together in certain proportions, they instantly unite, and are converted into nitrous acid. If this mixture be made over water, the volume of the gases is instantly diminished, because the nitrous acid formed loses its elasticity and is absorbed by the water. When nitrous gas is mixed with air containing oxygen gas, the diminution of volume after mixture is greater the more oxygen gas is present in the air. This induced Dr. Priestley to employ nitrous gas as a test of the purity of common air. He mixed together equal volumes of the nitrous gas and air to be examined, and he judged of the purity of the air by the degree of condensation. The greater the diminution of bulk, the greater did he consider the proportion of oxygen in the air under examination to be. This method of proceeding was immediately adopted by chemists and physicians, but there was a want of uniformity in the mode of proceeding, and a considerable diversity in the results. M. Lavoisier endeavored to improve the process in a paper inserted in the Memoirs of the Academy for 1782. But his method did not answer the purpose intended. It was Mr. Cavendish that first pointed out an accurate mode of testing air by means of nitrous gas, and who showed that the proportions of oxygen and azotic gas in common air are invariable. Lavoisier, in the course of his investigations, had proved that carbonic acid is a compound of carbon and oxygen, sulfuric acid of sulfur and oxygen, phosphoric acid of phosphorus and oxygen, and nitric acid of nitrous gas and oxygen. Neither the carbon, the sulfur, the phosphorus, nor the nitrous gas possessed any acid properties when uncombined, but they acquired these properties when they were united to oxygen. He observed further that all the acids known in his time which had been decomposed were found to contain oxygen, and when they were deprived of oxygen, they lost their acid properties. These facts led him to conclude that oxygen is an essential constituent in all acids, and that it is the principle which bestows acidity, or the true acidifying principle. This was the reason why he distinguished it by the name of oxygen. These views were fully developed by Lavoisier in a paper inserted in the Memoirs of the Academy for 1778, entitled General Considerations on the Nature of Acids, and on the Principles of which they are composed. When this paper was published, Lavoisier's views were exceedingly plausible. They were gradually adopted by chemists in general, and for a number of years may be considered to have constituted a part of the generally received doctrines. But the discovery of the nature of chlorine, and the subsequent facts brought to light respecting iodine, bromine, and cyanogen, have demonstrated that it is inaccurate, that many powerful acids exist which contain no oxygen, and that there is no one substance to which the name of acidifying principle can with justice be given. To this subject we shall again revert, when we come to treat of the more modern discoveries. Long as the account is which we have given of the labors of Lavoisier, the subject is not yet exhausted. Two other papers of his remain to be noticed, which throw considerable light on some important functions of the living body. We allude to his experiments on respiration and perspiration. It was known that if an animal was confined beyond a certain limited time in a given volume of atmospherical air, it died of suffocation, in consequence of the air becoming unfit for breathing, and that if another animal was put into this air, thus rendered noxious by breathing, its life was destroyed almost in an instant. Dr. Priestley had thrown some light upon this subject by showing that air in which an animal had breathed for some time possessed the property of rendering lime water turbid, and therefore contained carbonic acid gas. He considered the process of breathing as exactly analogous to the calcination of metals, or the combustion of burning bodies. Both, in his opinion, acted by giving out phlogiston, which, uniting with the air of the atmosphere, converted it into phlogisticated air. Priestley found that if plants were made to vegetate for some time in air that had been rendered unfit for supporting animal life by respiration, it lost the property of extinguishing a candle, and animals could breathe it again without injury. He concluded from this that animals, by breathing, phlogisticated air, but that plants, by vegetating, dephlogisticated air. The former communicated phlogiston to it. The latter took phlogiston from it. End of section 48. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 49 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by THOMSON. Volume 2, Chapter 3. Progress of Scientific Chemistry in France, Part 6. After Lavoisier had satisfied himself that air is a mixture of oxygen and azote, and that oxygen alone is concerned in the process of calcination and combustion, being absorbed and combined with the substances undergoing calcination and combustion, it was impossible for him to avoid drawing similar conclusions with respect to the breathing of animals. Accordingly, he made experiments on the subject, and the result was published in the Memoirs of the Academy for 1777. From these experiments, he drew the following conclusions. 1. The only portion of atmospherical air which is useful in breathing is the oxygen. The azote is drawn into the lungs along with the oxygen, but it is thrown out again unaltered. 2. The oxygen gas, on the contrary, is gradually, by breathing, converted into carbonic acid, and air becomes unfit for respiration when a certain portion of its oxygen is converted into carbonic acid gas. 3. Respiration is therefore exactly analogous to calcination. When air is rendered unfit for supporting life by respiration, if the carbonic acid gas formed be withdrawn by means of lime water or caustic alkali, the azote remaining is precisely the same in its nature as what remains after air is exhausted of its oxygen by being employed for calcining metals. In this first paper, Lavoisier went no further than establishing these general principles, but he afterwards made experiments to determine the exact amount of the changes which were produced in air by breathing, and endeavored to establish an accurate theory of respiration. To this subject we shall have occasion to revert again, when we give an account of the attempts made to determine the phenomena of respiration by more modern experimenters. Lavoisier's experiments on perspiration were made during the frenzy of the French Revolution, when Robespierre had usurped the supreme power, and when it was the object of those at the head of affairs to destroy all marks of civilization and science which remained in the country. His experiments were scarcely completed when he was thrown into prison, and though he requested a prolongation of his life for a short time, till he could have the means of drawing up a statement of their results, the request was barbarously refused. He has therefore left no account of them whatever behind him. But Seguin, who was associated with him in making these experiments, was fortunately overlooked, and escaped the dreadful times of the Reign of Terror. He afterwards drew up an account of the results, which has prevented them from being wholly lost to chemists and physiologists. Seguin was usually the person experimented on. A varnished silk bag, perfectly airtight, was procured, within which he was enclosed, except a slit over against the mouth, which was left open for breathing, and the edges of the bag were accurately cemented round the mouth by means of a mixture of turpentine and pitch. Thus everything emitted by the body was retained in the bag, except what made its escape from the lungs by respiration. By weighing himself in a delicate balance at the commencement of the experiment, and again after he had continued for some time in the bag, the quantity of matter carried off by respiration was determined. By weighing himself without this varnished covering, and repeating the operation after the same interval of time had elapsed as in the former experiment, he determined the loss of weight occasioned by perspiration and respiration together. The loss of weight indicated by the first experiment being subtracted from that given by the second, the quantity of matter lost by perspiration through the pores of the skin was determined. The following facts were ascertained by these experiments. The maximum of matter perspired in a minute amounted to 26.25 grains troy, the minimum to 9 grains, which gives 17.63 grains at a medium in the minute, or 52.89 ounces in 24 hours. The amount of perspiration is increased by drink, but not by solid food. 3. Perspiration is at its minimum immediately after a repast. It reaches its maximum during digestion. Such is an epitome of the chemical labors of M. Lavoisier. When we consider that this prodigious number of experiments and memoirs were all performed and drawn up within the short period of 20 years, we shall be able to form some idea of the almost incredible activity of this extraordinary man, the steadiness with which he kept his own peculiar opinions in view, and the good temper which he knew how to maintain in all his publications, though his opinions were not only not supported, but actually opposed by the whole body of chemists in existence, does him infinite credit, and was undoubtedly the wisest line of conduct which he could possibly have adopted. The difficulties connected with the evolution and absorption of hydrogen constituted the stronghold of the phlogistians. But Mr. Cavendish's discovery that water is a compound of oxygen and hydrogen was a death blow to the doctrine of Stahl. Soon after this discovery was fully established, or during the year 1785, M. Berthollet, a member of the Academy, and fast rising to the eminence which he afterwards acquired, declared himself a convert to the Lavoisierian theory. His example was immediately followed by M. Fourcroy, also a member of the Academy, who had succeeded Macquer as professor of chemistry in the Jardin du Roi. M. Fourcroy, who was perfectly aware of the strong feeling of patriotism which at that time actuated almost every man of science in France, hit upon a most infallible way of giving currency to new opinions. To the theory of Lavoisier he gave the name La Chimie Française, French chemistry. This name was not much relished by Lavoisier, as in his opinion it deprived him of the credit which was his due, but it certainly contributed, more than anything else, to give new opinions currency, at least in France. They became at once a national concern, and those who still adhered to the old opinions were hooted and stigmatized as enemies to the glory of their country. One of the most eminent of those who still adhered to the phlogistic theory was M. Gaeton de Morveau, a nobleman of Burgundy, who had been educated as a lawyer, and who filled a conspicuous situation in the Parliament of Dijon. He had cultivated chemistry with great zeal, and was at that time the editor of the chemical part of the Encyclopédie Méthodique. In the first half volume of the chemical part of this dictionary, which had just appeared, Morveau had supported the doctrine of phlogiston, and opposed the opinions of Lavoisier with much zeal and considerable skill. On this account it became an object of considerable consequence to satisfy Morveau that his opinions were inaccurate, and to make him a convert to the anti-phlogistic theory, for the whole matter was managed as if it had been a political intrigue rather than a philosophical inquiry. Morveau was accordingly invited to Paris, and Lavoisier succeeded without difficulty in bringing him over to his own opinions. We are ignorant of the means which he took. No doubt friendly discussion and the repetition of the requisite experiments would be sufficient to satisfy a man so well acquainted with the subject, and whose mode of thinking was so liberal as Morveau. Into the middle of the second half volume of the chemical part of the Encyclopædia Méthodique, he introduced a long advertisement announcing this change in his opinions, and assigning his reasons for it. The chemical nomenclature at that time in use had originated with the medical chemists, and contained a multiplicity of unwieldy and unmeaning and even absurd terms. It had answered the purposes of chemists tolerably well while the science was in its infancy, but the number of new substances brought into view had of late years become so great that the old names could not be applied to them without the utmost straining, and the chemical terms in use were so little systematic that it required a considerable stretch of memory to retain them. These evils were generally acknowledged and lamented, and various attempts had been made to correct them. Bergman, for instance, had contrived a new nomenclature confined chiefly to the salts, and adapted to the Latin language. Dr. Black had done the same thing. His nomenclature possessed both elegance and neatness, and was in several respects superior to the terms ultimately adopted. But with his usual indolence and disregard of reputation, he satisfied himself merely with drawing it up in the form of a table, and exhibiting it to his class. Morveau contrived a new nomenclature of the salts, and published it in 1783, and it appears to have been seen and approved of by Bergman. The old chemical phraseology, as far as it had any meaning, was entirely conformable to the phlogistic theory. This was so much the case that it was with difficulty that Lavoisier was able to render his opinions intelligible by means of it. Indeed, it would have been out of his power to have conveyed his meaning to his readers, had he not invented and employed a certain number of new terms. Lavoisier, aware of the defects of the chemical nomenclature, and sensible of the advantage which his own doctrine would acquire when dressed up in a language exactly suited to his views, was easily prevailed upon by Morveau to join with him in forming a new nomenclature to be henceforth employed exclusively by the antiphlogistians, as they called themselves. For this purpose they associated with themselves Berthollet and Fourcroy. We do not know what part each took in this important undertaking, but if we are to judge from appearances, the new nomenclature was almost exclusively the work of Lavoisier and Morveau. Lavoisier undoubtedly contrived the general phrases, and the names applied to the simple substances, so far as they were new, because he had employed the greater number of them in his writings before the new nomenclature was concocted. That the mode of naming the salts originated with Morveau is obvious, for it differs but little from the nomenclature of the salts published by him 4 years before. The new nomenclature was published by Lavoisier and his associates in 1787, and it was ever after employed by them in all their writings. Aware of the importance of having a periodical work in which they could register and make known their opinions, they established the Annales de Chimie as a sort of a counterpoise to the Journal de Physique, the editor of which, M. de la Metherie, continued a zealous votary of phlogiston to the end of his life. This new nomenclature very soon made its way into every part of Europe, and became the common language of chemists, in spite of the prejudices entertained against it, and the opposition which it everywhere met with. In the year 1796, or 9 years after the appearance of the new nomenclature, when I attended the chemistry class in the College of Edinburgh, it was not only in common use among the students, but was employed by Dr. Black, the professor of chemistry himself, and I have no doubt that he had introduced it into his lectures several years before. This extraordinary rapidity with which the new chemical language came into use was doubtless owing to two circumstances. First, the very defective, vague, and barbarous state of the old chemical nomenclature. For although in consequence of the prodigious process which the science of chemistry has made since the time of Lavoisier, his nomenclature is now nearly as inadequate to express our ideas as that of Stahl was to express his. Yet at the time of its appearance, its superiority over the old nomenclature was so great that it was immediately felt and acknowledged by all those who were acquiring the science, who are the most likely to be free from prejudices, and who in the course of a few years must constitute the great body of those who are interested in the science. 2. The second circumstance to which the rapid triumph of new nomenclature was owing is the superiority of Lavoisier's theory over that of Stahl. The subsequent progress of the science has betrayed many weak points in Lavoisier's opinions, yet its superiority over that of Stahl was so obvious, and the mode of interrogating nature introduced by him was so good and so well calculated to advance the science, that no unprejudiced person who was at sufficient pains to examine both could hesitate about preferring that of Lavoisier. It was therefore generally embraced by all the young chemists in every country, and they became at the same time partial to the new nomenclature, by which only that theory could be explained in an intelligible manner. When the new nomenclature was published, there were only 3 nations in Europe who could be considered as holding a distinguished place as cultivators of chemistry: France, Germany, and Great Britain. For Sweden had just lost her 2 great chemists, Bergman and Scheele, and had been obliged, in consequence, to descend from the high chemical rank which she had formerly occupied. In France, the fashion, and of course almost the whole nation, were on the side of the new chemistry. Macquer, who had been a staunch phlogistian to the last, was just dead. Monet was closing his laborious career. Baume continued to adhere to the old opinions, but he was old, and his chemical skill, which had never been accurate, was totally eclipsed by the more elaborate researches of Lavoisier and his friends. De la Mettrie was a keen phlogistian, a man of some abilities, of remarkable honesty and integrity, and editor of the Journal de Physique, at that time a popular and widely circulating scientific journal. But his habits, disposition, and conduct were by no means suited to the taste of his countrymen, or conformable to the practice of his contemporaries. The consequence was that he was shut out of all the scientific coteries of Paris, and that his opinions, however strongly or rather violently expressed, failed to produce the intended effect. Indeed, as his views were generally inaccurate, and expressed without any regard to the rules of good manners, they in all probability rather served to promote them to injure the cause of his opponents. Lavoisier and his friends appear to have considered the subject in this light. They never answered any of his attacks, or indeed took any notice of them. France, then, from the date of publication of the new nomenclature, might be considered as enlisted on the side of the antiphlogistic theory. The case was very different in Germany. The national prejudices of the Germans were naturally enlisted on the side of Stahl, who was their countryman, and whose reputation would be materially injured by the refutation of his theory. The cause of phlogiston, accordingly, was taken up by several German chemists, and supported with a good deal of vigour, and a controversy was carried on for some years in Germany between the old chemists who adhered to the doctrine of Stahl, and the young chemists who had embraced the theory of Lavoisier. Keren, who was at that time the editor of a chemical journal, deservedly held in high estimation, and whose reputation as a chemist stood rather high in Germany, finding it impossible to defend the Stahlian theory as it had been originally laid down, introduced a new modification of phlogiston, and attempted to maintain it against the antiphlogistians. The death of Keren and of Wegeler, who were the great champions of phlogiston, left the field open to the antiphlogistians, who soon took possession of all the universities and scientific journals in Germany. The most eminent chemist in Germany, or perhaps in Europe at that time, was Martin Henry Klaproth, professor of chemistry at Berlin, to whom analytical chemistry lies under the greatest obligations. In the year 1792, he proposed to the Academy of Sciences of Berlin, of which he was a member, to repeat all the requisite experiments before them, that the members of the Academy might be able to determine for themselves which of the two theories deserved the preference. This proposal was acceded to. All the fundamental experiments were repeated by Klaproth with the most scrupulous attention to accuracy. The result was a full conviction, on the part of Klaproth and the Academy, that the Lavoisierian theory was the true one. Thus the Berlin Academy became anti-phlogistians in 1792, and as Berlin has always been the focus of chemistry in Germany, the determination of such a learned body must have had a powerful effect in accelerating the propagation of the new theory through that vast country. In Great Britain, the investigations of gaseous bodies, to which the new doctrines were owing, had originated. Dr. Black had begun the inquiry. Mr. Cavendish had prosecuted it with unparalleled accuracy, and Dr. Priestley had made known a great number of new gaseous bodies, which had hitherto escaped the attention of chemists. As the British chemists had contributed more than those of any other nation to the production of the new facts on which Lavoisier's theory was founded, it was natural to expect that they would have embraced that theory more readily than the chemists of any other nation. But the matter of fact was somewhat different. Dr. Black, indeed, with his characteristic candor, speedily embraced the opinions, and even adopted the new nomenclature. But Mr. Cavendish new-modelled the phlogistic theory, and published a defence of phlogiston, which it was impossible at that time to refute. The French chemists had the good sense not to attempt to overturn it. Mr. Cavendish, after this, laid aside the cultivation of chemistry altogether, and never acknowledged himself a convert to the new doctrines. Dr. Priestley continued a zealous advocate for phlogiston till the very last, and published what he called a refutation of the anti-phlogistic theory about the beginning of the present century. But Dr. Priestley, notwithstanding his merit as a discoverer and a man of genius, was never, strictly speaking, entitled to the name of chemist, as he was never able to make a chemical analysis. In his famous experiments, for example, on the composition of water, he was obliged to procure the assistance of Mr. Keir to determine the nature of the blue-colored liquid which he had obtained, and which Mr. Keir showed to be nitrate of copper. Besides, Dr. Priestley, though perfectly honest and candid, was so hasty in his decisions, and so apt to form his opinions without duly considering the subject, that his chemical theories were almost all erroneous, and sometimes quite absurd. End of section 49. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. Section 50 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 3. The Progress of Scientific Chemistry in France. Part 7. Mr. Keren, who had acquired a high reputation, partly by his mineralogy and partly by his experiments on the composition of the salts, undertook the task of refuting the anti-phlogistic theory, and with that view published a work to which he gave the name An Essay on Phlogiston and the Composition of Acids. In that book he maintained an opinion which seems to have been pretty generally adopted by the most eminent chemists of the time, namely that phlogiston is the same thing with what is at present called hydrogen, and which, when Keren wrote, was called light inflammable air. Of course, Mr. Keren undertook to prove that every combustible substance and every metal contains hydrogen as a constituent, and that hydrogen escapes in every case of combustion and calcination. On the other hand, when calces are reduced to the metallic state, hydrogen is absorbed. The book was divided into 13 sections. In the first, the specific gravity of the gases was stated according to the best data then existing. The second section treats of the composition of acids, and the composition and decomposition of water. The third section treats of sulfuric acid, the fourth of nitric acid, the fifth of muriatic acid, the sixth of aqua regia, the seventh of phosphoric acid, the eighth of oxalic acid, the ninth of the calcination and reduction of metals and the formation of fixed air, the 10th of the dissolution of metals, the 11th of the precipitation of metals by each other, the 12th of the properties of iron and steel, while the 13th sums up the whole argument by way of conclusion. In this work, Mr. Keren admitted the truth of M. Lavoisier's theory that during combustion and calcination, oxygen united with the burning and calcining body. He admitted also that water is a compound of oxygen and hydrogen. Now these admissions, which, however, it was scarcely possible for a man of candor to refuse, rendered the whole of his arguments in favor of the identity of hydrogen and phlogiston, and of the existence of hydrogen in all combustible bodies, exceedingly inconclusive. Keren's book was laid hold of by the French chemists, as affording them an excellent opportunity of showing the superiority of the new opinions over the old. Keren's view of the subject was that which had been taken by Bergman and Scheele, and indeed by every chemist of eminence who still adhered to the phlogistic system. A satisfactory refutation of it, therefore, would be a death blow to phlogiston, and would place the antiphlogistic theory upon a basis so secure that it would be henceforth impossible to shake it. Keren's work on phlogiston was accordingly translated into French, and published in Paris. At the end of each section was placed an examination and refutation of the argument contained in it by some one of the French chemists, who had now associated themselves in order to support the antiphlogistic theory. The introduction, together with the second, third, and 11th sections, were examined and refuted by M. Lavoisier. The fourth, the fifth, and sixth sections fell to the share of M. Berthollet. The 7th and 13th sections were undertaken by M. de Morveau, the 8th, 9th, and 10th by M. de Fourcroy, while the 12th section, on iron and steel, was animadverted on by M. Monge. These refutations were conducted with so much urbanity of manner, and were at the same time so complete, that they produced all the effects expected from them. Mr. Keren, with a degree of candor and liberality of which, unfortunately, very few examples can be produced, renounced his old opinions, abandoned phlogiston, and adopted the antiphlogistic doctrines of his opponents. But his advanced age, and a different mode of experimenting from what he had been accustomed to, induced him to withdraw himself entirely from experimental science, and to devote the evening of his life to metaphysical and logical and moral investigations. Thus, soon after the year 1790, a kind of interregnum took place in British chemistry. Almost all the old British chemists had relinquished the science, or been driven out of the field by the superior prowess of their antagonists. Dr. Austin and Dr. Pearson will perhaps be pointed out as exceptions. They undoubtedly contributed somewhat to the progress of the science, but they were arranged on the side of the antiphlogistians. Dr. Crawford, who had done so much for the theory of heat, was about this time ruined in his circumstances by the bankruptcy of a house to which he had entrusted his property. This circumstance preyed upon a mind which had a natural tendency to morbid sensibility, and induced this amiable and excellent man to put an end to his existence. Dr. Higgins had acquired some celebrity as an experimenter and teacher, but his disputes with Dr. Priestley, and his laying claim to discoveries which certainly did not belong to him, had injured his reputation, and led him to desert the field of science. Dr. Black was an invalid. Mr. Cavendish had renounced the cultivation of chemistry, and Dr. Priestley had been obliged to escape from the iron hand of theological and political bigotry by leaving the country. He did little as an experimenter after he went to America, and perhaps had he remained in England, his reputation would rather have diminished than increased. He was an admirable pioneer, and as such contributed more than anyone to the revolution which chemistry underwent, though he was himself utterly unable to rear a permanent structure capable, like the Newtonian theory, of withstanding all manner of attacks, and becoming only the firmer and stronger the more it is examined. Mr. Keir of Birmingham was a man of great eloquence, and possessed all the chemical knowledge which characterized the votaries of phlogiston. In the year 1789, he attempted to stem the current of the new opinions by publishing a dictionary of chemistry, in which all the controversial points were to be fully discussed, and the antiphlogistic theory examined and refuted. Of this dictionary only one part appeared, constituting a very thin volume of 208 quarto pages, and treating almost entirely of acids. Finding that the sale of this work did not answer his expectations, and probably feeling as he proceeded that the task of refuting the antiphlogistic opinions was much more difficult and much more hopeless than he expected, he renounced the undertaking and abandoned altogether the pursuit of chemistry. It will be proper in this place to introduce some account of the most eminent of those French chemists who embraced the theory of Lavoisier and assisted him in establishing his opinions. Claude Louis Berthollet was born at Talloires, near Annecy, in Savoy, on the 9th of December, 1748. He finished his school education at Chambéry, and afterwards studied at the College of Turin, a celebrated establishment, where many men of great scientific celebrity had been educated. Here he attached himself to medicine, and after obtaining a degree he repaired to Paris, which was destined to be the future theatre of his speculations and pursuits. In Paris he had not a single acquaintance, nor did he bring with him a single introductory letter. But understanding that M. Tronchin, at that time a distinguished medical practitioner in Paris, was a native of Geneva, he thought he might consider him as in some measure a countryman. On this slender ground he waited on M. Tronchin, and what is rather surprising, and reflects great credit on both, this acquaintance, begun in so uncommon a way, soon ripened into friendship. Tronchin interested himself for his young protégé, and soon got him into the situation of physician in ordinary to the Duke of Orleans, father of him who cut so conspicuous a figure in the French Revolution, under the name of Monsieur Égalité. In this situation he devoted himself to the study of chemistry, and soon made himself known by his publications on the subject. In 1781 he was elected a member of the Academy of the Sciences of Paris. One of his competitors was Monsieur Fourcroy. No doubt Berthollet owed his election to the influence of the Duke of Orleans. In the year of 1784 he was again a competitor with Monsieur de Fourcroy for the chemical chair at the Jardin du Roi, left vacant by the death of Macquer. The chair was in the gift of M. Buffon, whose vanity is said to have been piqued because of the Duke of Orleans, who supported Berthollet's interest, did not pay him sufficient court. This induced him to give the chair to Fourcroy, and the choice was a fortunate one, as his uncommon vivacity and rapid elocution particularly fitted him for addressing a Parisian audience. The chemistry class at the Jardin du Roi immediately became celebrated and attracted immense crowds of admiring auditors. But the influence of the Duke of Orleans was sufficient to procure for Berthollet another situation which Macquer had held. This was government commissary and superintendent of the dyeing processes. It was this situation which naturally turned his attention to the phenomena of dyeing, and occasioned afterwards his book on dyeing, which at the time of its publication was excellent, and exhibited a much better theory of dyeing and a better account of the practical part of the art than any work which had previously appeared. The art of dyeing and calico printing have been very much improved since the time that Berthollet's book was written. Yet if we accept Bancroft's work on the permanent colors, nothing very important has been published on the subject since that period. We are at present almost as much in want of a good work on dyeing as we were when Berthollet's book appeared. In the year 1785, Berthollet, at a meeting of the Academy of Sciences, informed that learned body that he had become a convert to the antiphlogistic doctrines of Lavoisier. There was one point, however, upon which he entertained a different opinion from Lavoisier, and this difference of opinion continued to the last. Berthollet did not consider oxygen as the acidifying principle. On the contrary, he was of opinion that acids existed which contained no oxygen whatever. As an example, he mentioned sulphuretted hydrogen, which possessed the properties of an acid, reddening vegetable blues, and combining with and neutralizing bases. And yet it was a compound of sulfur and hydrogen, and contained no oxygen whatever. It is now admitted that Berthollet was accurate in his opinion, and that oxygen is not of itself an acidifying principle. Berthollet continued in the uninterrupted prosecution of his studies, and had raised himself a very high reputation when the French Revolution burst upon the world in all its magnificence. It is not our business here to enter into any historical details, but merely to remind the reader that all the great powers of Europe combined to attack France, assisted by a formidable army of French emigrants assembled at Coblentz. The Austrian and Prussian armies hemmed her in by land, while the British fleet surrounded her by sea, and thus shut her out from all communication with other nations. Thus France was thrown at once upon her own resources. She had been in the habit of importing her saltpetre and her iron, and many other necessary implements of war. These supplies were suddenly withdrawn, and it was expected that France, thus deprived of all her resources, would be obliged to submit to any terms imposed upon her by her adversaries. At this time she summoned her men of science to her assistance, and the call was speedily answered. Berthollet and Monge were particularly active, and saved the French nation from destruction by their activity, intelligence, and zeal. Berthollet traversed France from one extremity to the other, pointed out the mode of extracting saltpetre from the soil and of purifying it. Saltpetre works were instantly established in every part of France, and gunpowder made of it in prodigious quantity and with incredible activity. Berthollet even attempted to manufacture a new species of gunpowder, still more powerful than the old, by substituting chlorate of potash for saltpetre, but it was found too formidable a substance to be made with safety. The demand for cannon, muskets, sabres, etc., was equally urgent and equally difficult to be supplied. A committee of men of science, of which Berthollet and Monge were the leading members, was established, and by them the mode of smelting iron and of converting it into steel was instantly communicated, and numerous manufactories of these indispensable articles rose like magic in every part of France. This was the most important period of the life of Berthollet. It was in all probability his zeal, activity, sagacity, and honesty which saved France from being overrun by foreign troops. But perhaps the moral conduct of Berthollet was not less conspicuous than his other qualities. During the Reign of Terror, a short time before the 9th Thermidor, when it was the system to raise up pretended plots to give pretext for putting to death those that were obnoxious to Robespierre and his friends, a hasty notice was given at a sitting of the Committee of Public Safety, that a conspiracy had just been discovered to destroy the soldiers, by poisoning the brandy which was just going to be served out to them previous to an engagement. It was said that the sick in the hospitals who had tasted this brandy all perished in consequence of it. Immediate orders were issued to arrest those previously marked for execution. A quantity of the brandy was sent to Berthollet to be examined. He was informed at the same time that Robespierre wanted a conspiracy to be established, and all knew that opposition to his will was certain destruction. Having finished his analysis, Berthollet drew up his results in a report, which he accompanied with a written explanation of his views, and he there stated in the plainest language that nothing poisonous was mixed with the brandy, but that it had been diluted with water holding small particles of slate in suspension, an ingredient which filtration would remove. This report deranged the plans of the Committee of Public Safety. They sent for the author to convince him of the inaccuracy of his analysis, and to persuade him to alter its results. Finding that he remained unshaken in his opinion, Robespierre exclaimed, "What, sir, darest thou affirm that the muddy brandy is free from poison?" Berthollet immediately filtered a glass of it in his presence, and drank it off. "Thou art daring, sir, to drink that liquor," exclaimed the ferocious president of the committee. "I dared much more," replied Berthollet, "when I signed my name to that report." There can be no doubt that he would have paid the penalty of this undaunted honesty with his life, but that fortunately the Committee of Public Safety could not at that time dispense with his services. In the year 1792, Berthollet was named one of the commissioners of the Mint, into the processes of which he introduced considerable improvements. In 1794 he was appointed a member of the Commission of Agriculture and the Arts, and in the course of the same year he was chosen professor of chemistry at the Polytechnic School, and also in the Normal School. But his turn of mind did not fit him for a public teacher. He expected too much information to be possessed by his hearers, and did not therefore dwell sufficiently upon the elementary details. His pupils were not able to follow his metaphysical disquisitions on subjects totally new to them. Hence, instead of inspiring them with a love for chemistry, he filled them with languor and disgust. In 1795, at the organization of the Institute, which was intended to include all men of talent or celebrity in France, we find Berthollet taking a most active lead, and the records of the Institute afford abundant evidence of the perseverance and assiduity with which he labored for its interests. Of the committees to which all original memoirs are in the first place referred, we find Berthollet, oftener than any other person, a member, and his signature to the report of each work stands generally first. In the year 1796, after the subjugation of Italy by Bonaparte, Berthollet and Monge were selected by the Directory to proceed to that country, in order to select those works of science and art with which the Louvre was to be filled and adorned. While engaged in the prosecution of that duty, they became acquainted with the victorious general. He easily saw the importance of their friendship, and therefore cultivated it with care, and was happy afterwards to possess them, along with nearly 100 other philosophers, as his companions, in his celebrated expedition to Egypt, expecting, no doubt, an éclat from such a halo of surrounding science as might favor the development of his schemes of future greatness. On this expedition, which promised so favorably for the French nation, and which was intended to inflict a mortal stab upon the commercial greatness of Great Britain, Bonaparte set out in the year 1798, accompanied by a crowd of the most eminent men of science that France could boast of. That they might cooperate more effectually in the cause of knowledge, these gentlemen formed themselves into a society, named the Institute of Egypt, which was constituted on the same plan as the National Institute of France. Their first meeting was on the 6th Fructidor, 24th of August, 1798, and after that they continued to assemble at stated intervals. At these meetings papers were read by the respective members on the climate, the inhabitants, and the natural and artificial productions of the country to which they had gone. These memoirs were published in 1800, in Paris, in a single volume entitled Memoirs of the Institute of Egypt. End of section 50. Recording by Lawrence Trask. Mount Vernon, Ohio. InterfaceAudio.com. Section 51 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, InterfaceAudio.com. The History of Chemistry by THOMSON, Volume 2, Chapter 3, The Progress of Scientific Chemistry in France, Part 8. The history of the Institute of Egypt, as related by Cuvier, is not a little singular, and deserves to be stated. Bonaparte, during his occasional intercourse with Berthollet in Italy, was delighted with the simplicity of his manners, joined to a force and depth of thinking which he soon perceived to characterize our chemist. When he returned to Paris, where he enjoyed some months of comparative leisure, he resolved to employ his spare time in studying chemistry under Berthollet. It was at this period that his illustrious pupil imparted to our philosopher his intended expedition to Egypt, of which no whisper was to be spread abroad till the blow was ready to fall, and he begged of him not merely to accompany the army himself, but to choose such men of talent and experience as he conceived fitted to find there an employment worthy of the country which they visited, and of that which sent them forth. To invite men to a hazardous expedition, the nature and destination of which he was not permitted to disclose, was rather a delicate task, yet Berthollet undertook it. He could simply inform them that he would himself accompany them. Yet such was the universal esteem in which he was held, such was the confidence universally placed in his honesty and integrity, that all the men of science agreed at once, and without hesitation, to embark on an unknown expedition, the dangers of which he was to share along with them. Had it not been for the link which Berthollet supplied between the commander-in-chief and the men of science, it would have been impossible to have united, as was done on this occasion, the advancement of knowledge with the progress of the French arms. During the whole of this expedition, Berthollet and Monge distinguished themselves by their firm friendship, and by their mutually braving every danger to which any of the common soldiers could be exposed. Indeed, so intimate was their association, that many of the army conceived Berthollet and Monge to be one individual, and it is no small proof of the intimacy of these philosophers with Bonaparte, that the soldiers had a dislike at this double personage, from a persuasion that it had been at his suggestion that they were led into a country which they detested. It happened on one occasion that a boat in which Berthollet and some others were conveyed up the Nile was assailed by a troop of Mamelukes, who poured their small shot into it from the banks. In the midst of this perilous voyage, Monsieur Berthollet began very coolly to pick up stones and stuff his pockets with them. When his motive from this conduct was asked, "I am desirous," said he, "that in case of my being shot, my body may sink at once to the bottom of the river, and may escape the insults of these barbarians." In a conjuncture where a courage of rarer kind was required, Berthollet was not found wanting. The plague broke out in the French army, and this added to the many fatigues they had previously endured. The diseases under which they were already laboring would, it was feared, lead to insurrection on the one hand, or totally sink the spirits of the men on the other. Acre had been besieged for many weeks in vain. Bonaparte and his army had been able to accomplish nothing against it. He was anxious to conceal from his army this disastrous intelligence. When the opinion of Berthollet was asked in council, he spoke at once the plain though unwelcome truth. He was instantly assailed by the most violent reproaches. "In a week," said he, "my opinion will be unfortunately but too well vindicated." It was as he foretold, and when nothing but a hasty retreat could save the wretched remains of the army of Egypt, the carriage of Berthollet was seized for the convenience of some wounded officers. On this he travelled on foot, and without the smallest discomposure, across 20 leagues of the desert. When Napoleon abandoned the army of Egypt, and traversed half the Mediterranean in a single vessel, Berthollet was his companion. After he had put himself at the head of the French government, and had acquired an extent of power which no modern European potentate had ever before realized, he never forgot his associate. He was in the habit of placing all chemical discoveries to his account, to the frequent annoyance of our chemist, and when an unsatisfactory answer was given him upon any scientific subject, he was in the habit of saying, "Well, I shall ask this of Berthollet." But he did not limit his affection to these proofs of regard. Having been informed that Berthollet's earnest pursuits of science had led him into expenses which had considerably deranged his fortune, he sent for him, and said in a tone of affectionate reproach, "Monsieur Berthollet, I have always 100,000 crowns at the service of my friends," and in fact this sum was immediately presented to him. Upon his return from Egypt, Berthollet was nominated as senator by the first consul, and afterwards received the distinction of Grand Officer of the Legion of Honor, Grand Cross of the Order of Reunion, titulary of the Senatory of Montpellier, and under the Emperor he was created a peer of France, receiving the title of Count. The advancement of these offices produced no change in the manners of Berthollet. Of this he gave a striking proof by adopting his armorial bearing, at the time that others eagerly blazoned some exploit, the plain unadorned figure of his faithful and affectionate dog. He was no courtier before he received these honours, and he remained equally simple and unassuming, and not less devoted to science after they were conferred. As we advance toward the latter period of his life, we find the same ardent zeal in the cause of science which he had glowed in his early youth, accompanied by the same generous warmth of heart that he ever possessed, and which displayed itself in his many intimate friendships still subsisting, though mellowed by the hand of time. At this period Laplace lived at Arcueil, a small village about 3 miles from Paris. Between him and Berthollet there had long subsisted a warm affection, founded on mutual esteem. To be near this illustrious man, Berthollet purchased a county seat in the village. There he established a very complete laboratory, fit for conducting all kinds of experiments in every branch of natural philosophy. Here he collected round him a number of distinguished young men, who knew that in his house their ardour would at once receive fresh impulse and direction from the example of Berthollet. These youthful philosophers were organized by him into a society, to which the name Société d'Arcueil was given. M. Berthollet was himself the president, and the other members were Laplace, Biot, Gay-Lussac, Thenard, Collet d'Escotils, de Candolle, Humboldt, and A.B. Berthollet. This society published 3 volumes of very valuable memoirs. The energy of this society was unfortunately paralyzed by an untoward event, which embittered the latter days of this amiable man. His only son, M.A.B. Berthollet, in whom his happiness was wrapped up, was unfortunately afflicted with a lowness of spirits which rendered his life wholly insupportable to him. Retiring to a small room, he locked the door, closed up every chink and crevice which might admit the air, carried writing materials to a table on which he placed a second watch, and then seated himself before it. He now marked precisely the hour, and lighted a brazier of charcoal beside him. He continued to note down the series of sensations he then experienced in succession, detailing the approach and rapid progress of delirium, until, as time went on, the writing became confused and illegible, and the young victim, dropped dead upon the floor. After this event, the spirits of the old man never again rose. Occasionally, some discovery extending the limits of his favorite science engrossed his interest and attention for a short time, but such intervals were rare and short-lived. The restoration of the Bourbons and the downfall of his friend and patron Napoleon added to his sufferings by diminishing his income and reducing him from a state of affluence to comparative embarrassment. But he was now old, and the end of his life was approaching. In 1822 he was attacked by a slight fever, which left behind it a number of boils. These were soon followed by a gangrenous ulcer of uncommon size. Under this he suffered for several months with surprising fortitude. He himself, as a physician, knew the extent of his danger, felt the inevitable progress of the malady, and calmly regarded the slow approach of death. At length, after a tedious period of suffering, in which his equanimity had never once been shaken, he died on the 6th of November, when he had nearly completed the 74th year of his age. His papers are exceedingly numerous, and of a very miscellaneous nature, accounting to more than 80. The earlier were chiefly inserted into the various volumes of the Memoirs of the Academy. He furnished many papers to the Annales de Chimie and the Journal de Physique, and was also a frequent contributor to the Society of Arcueil, in the different volumes of whose transactions several memoirs of his are to be found. He was the author likewise of 2 separate works, comprising each 2 octavo volumes. These were his Elements of the Art of Dying, first published in 1791, in a single volume. But the new and enlarged edition of 1814 was in 2 volumes, and his Essay on Chemical Statics, published about the beginning of the present century. I shall notice his most important papers. His earlier memoirs on sulphurous acid, on volatile alkali, and on the decomposition of nitre were encumbered by the phlogistic theory, which at that time he defended with great zeal, though he afterwards retracted these his first opinions upon all these subjects. Except his paper on soaps, in which he shows that they are chemical compounds of an oil, acting the part of an acid, and an alkaline base, and his proof that phosphoric acid exists ready formed in the body, and a fact long before demonstrated by Gahn and Scheele. His papers published before he became an anti-phlogistian are of inferior merit. In 1785 he demonstrated the nature and proportion of the constituents of ammonia, or volatile alkali. This substance had been collected in the gaseous form by the indefatigable Priestley, who had shown also that when electric sparks are made to pass for some time through a given volume of this gas, its bulk nearly doubled. Berthollet merely repeated this experiment of Priestley, and analyzed the new gases evolved by the action of electricity. This gas he found a mixture of 3 volumes hydrogen and 1 volume azotic gas. Hence it was evident that ammoniacal gas is a compound of 3 volumes of hydrogen and 1 volume of azotic gas united together, and condensed into 2 volumes. The same discovery was made about the same time by Dr. Austin, and published in the Philosophical Transactions. Both sets of experiments were made without any knowledge of what was done by the other, but it is admitted on all hands that Berthollet had the priority in point of time. It was about this time, likewise, that he published his first paper on chlorine. He observed that when water impregnated with chlorine is exposed to the light of the sun, the water loses its color, while at the same time a quantity of oxygen gas is given out. If we now examine the water, we find that it contains no chlorine, but merely a little muriatic acid. This fact, which is undoubted, led him to conclude that chlorine is decomposed by the action of solar light, and that its 2 elements are muriatic acid and oxygen. This led to the notion that the basis of muriatic acid is capable of combining with various doses of oxygen, and of forming various acids, one of which is chlorine. On that account it is called oxygenized muriatic acid by the French chemists, which unwieldy appellation was afterward shortened by Keren into oxymuriatic acid. Berthollet observed that when a current of chlorine gas is passed through a solution of carbonate of potash, an effervescence takes place owing to the disengagement of carbonic acid gas. By and by, crystals are deposited in fine silky scales, which possess the property of detonating with combustible bodies still more violently than saltpeter. Berthollet examined these crystals and showed that they were compounds of potash with an acid containing much more oxygen than oxymuriatic acid. He considered its basis as muriatic acid and distinguished it by the name of hyperoxymuriatic acid. It was not till the year 1810 that the inaccuracy of these opinions was established. Gay-Lussac and Thenard attempted in vain to extract oxygen from chlorine. They showed that not a trace of that principle could be detected. Next year, Davy took up the subject, and concluded from his experiments that chlorine is a simple substance, that muriatic acid is a compound of chlorine and hydrogen, and that hyperoxymuriatic acid of chlorine and oxygen. Gay-Lussac obtained this acid in a separate state, and gave it the name of chloric acid, by which it is now known. Scheele, in his original experiments on chlorine, had noticed the property which it has of destroying vegetable colors. Berthollet examined the property with care, and found it so remarkable that he proposed it as a substitute for exposure to the sun in bleaching. This suggestion alone would have immortalized Berthollet had he done nothing else, since its effect upon some of the most important of the manufactures of Great Britain has been scarcely inferior to that of the steam engine itself. Mr. Watt happened to be in Paris when the idea suggested itself to Berthollet. He not only communicated it to Mr. Watt, but showed him the process in all its simplicity. It consisted in nothing else than in steeping the cloth to be bleached in water impregnated with chlorine gas. Mr. Watt, on his return to Great Britain, prepared a quantity of this liquor and sent it to his father-in-law, Mr. McGregor, who was a bleacher in the neighbourhood of Glasgow. He employed it successfully, and thus was the first individual who tried the new process of bleaching in Great Britain. For a number of years, the bleachers in Lancashire and the neighbourhood of Glasgow were occupied in bringing the process to perfection. The disagreeable smell of the chlorine was a great annoyance. This was attempted to be got rid of by dissolving potash in the water to be impregnated with chlorine, but it was found to injure considerably the bleaching powers of the gas. The next method tried was to mix the water with quicklime, and then to pass a current of chlorine through it. The quicklime was dissolved, and the liquor thus constituted was found to answer very well. The last improvement was to combine the chlorine with dry lime. At first, 2 atoms of lime were united to 1 atom of chlorine, but of late years it is a compound of 1 atom of lime and 1 of chlorine. This chloride is simply dissolved in water, and the cloth to be bleached is steeped in it. For all these improvements, which have brought the method of bleaching by means of chlorine to great simplicity and perfection, the bleachers are indebted to Knox, Tennant, and Mackintosh of Glasgow, by whose indefatigable exertions the mode of manufacturing chloride of lime has been brought to the state of perfection. Berthollet's experiments on prussic acid and the prussiates deserves also to be mentioned as having a tendency to rectify some of the ideas at that time entertained by chemists, and to advance their knowledge of one of the most difficult departments of chemical investigation. In consequence of his experiments on the nature and constituents of sulphuretted hydrogen, he had already concluded that it was an acid, and that it was destitute of oxygen. This had induced him to refuse his assent to the hypothesis of Lavoisier that oxygen is the acidifying principle. Scheele, in his celebrated experiments on prussic acid, had succeeded in ascertaining that its constituents were carbon and azote, but he had not been able to make a rigid analysis of that acid, and consequently to demonstrate that oxygen did not enter into it as a constituent. Berthollet took up the subject, and though his analysis was also incomplete, he satisfied himself, and rendered it exceedingly probable, that the only constituents of this acid were carbon, azote, and hydrogen, and that oxygen did not enter into it as a constituent. This was another reason for rejecting the notion of oxygen as an acidifying principle. Here were two acids capable of neutralizing bases, namely sulfuretted hydrogen and prussic acid, and yet neither of them contained oxygen. He found that when prussic acid was treated with chlorine, its properties were altered. It acquired a different smell and taste, and no longer precipitated iron blue, but green. From his opinion respecting the nature of chlorine, that it was a compound of muriatic acid and oxygen, he naturally concluded that by this process he had formed a new prussic acid by adding oxygen to the old constituents. He therefore called this new substance oxyprussic acid. It has been proved by the more recent experiments of Gay-Lussac that the new acid of Berthollet is a compound of cyanogen, the prussic acid deprived of hydrogen, and chlorine. It is now called chlorocyanic acid, and is known to possess the characters assigned it by Berthollet. It constitutes, therefore, a new example of an acid destitute of oxygen. Berthollet was the first person who obtained prussiate of potash in regular crystals. The salt was known long before, but had always been used in a state of solution. Berthollet's discovery of fulminating silver, and his method of obtaining pure hydrated potash and soda by means of alcohol, deserve to be mentioned. This last process was of considerable importance to analytical chemistry. Before he published his process, these substances in a state of purity were not known. I think it unnecessary to enter into any details respecting his experiments on sulfuretted hydrogen, and the hydrosulfurates and sulfurates. They contributed essentially to elucidate that obscure part of chemistry. But his success was not perfect, nor did we understand completely the nature of these compounds, till the nature of the alkaline bases had been explained by the discoveries of Davy. End of section 51. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 52 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 3. Progress of Scientific Chemistry in France. Part 9. The only other work of Berthollet which I think it is necessary to notice here is his book entitled Chemical Statics, which he published in 1803. He had previously drawn up some interesting papers on the subject, which were published in the Memoirs of the Institute. Though chemical affinity constitutes confessedly the basis of the science, it had been almost completely overlooked by Lavoisier, who had done nothing more on the subject than drawn up some tables of affinity, founded on very imperfect data. Morveau had attempted a more profound investigation of the subject in the article Affinité, inserted in the chemical part of the Encyclopédie Méthodique. His object was, in imitation of Buffon, who had preceded him in the same investigation, to prove that chemical affinity is merely a case of the attraction of gravitation. But it is beyond our reach in the present state of our knowledge to determine the amount of attraction which the atoms of bodies exert with respect to each other. This was seen by Newton, and also by Bergman, who satisfied themselves with considering it as an attraction, without attempting to determine its amount. though Newton, with his usual sagacity, was inclined, from the phenomena of light, to consider the attraction of affinity as much stronger than that of gravitation, or at least as increasing much more rapidly as the distances between the attracting particles diminished. Bergman, who had paid great attention to the subject, considered affinity as a certain determinate attraction, which the atoms of different bodies exerted towards each other. This attraction varies in intensity between every two bodies, though it is constant between each pair. The consequence is that these intensities may be denoted by numbers. Thus, suppose a body, M, and the atoms of 6 other bodies, A, B, C, D, E, and F, to have an affinity for M. The forces by which they are attracted towards each other may be represented by the numbers x, x plus 1, x plus 2, x plus 3, x plus 4, x plus 5. And the attractions may be represented thus. Attraction between M and A equal x, M and B equal x plus 1, M and C equal x plus 2, M and D equals x plus 3, M and E equals x plus 4, M and F equals x plus 5. Suppose we have the compound Ma. If we present B, it will unite with M and displace A, because the attraction between M and A is only x, while that between M and B is x plus 1. C will displace B, D will displace C, and so on for the same reason. On this account, Bergman considered affinity as an elective attraction, and in his opinion, the intensity may always be estimated by decomposition. That substance which displaces another from a third has a greater affinity than the body which is displaced. If B displace A from the compound AM, then B has a greater affinity for M than A has. The object of Berthollet in his chemical statics was to combat this opinion of Bergman, which had been embraced without examination by chemists in general. If affinity be an attraction, Berthollet considered it as evident that it never could occasion decomposition. Suppose A to have an affinity for M and B to have an affinity for the same substances. Let the affinity between B and M be greater between AM. Let B mixed with a solution of the compound AM, then in that case B would unite with AM and form the triple compound AMB. Both A and B would at once unite with M. No reason can be assigned why A should separate from M, and B take its place. Berthollet admitted that in fact such decompositions often happened, but he accounted for them from other causes, and not from the superior affinity of one body over another. Suppose we have a solution of sulfate of soda in water. This salt is a compound of sulfuric acid and soda, two substances between which a strong affinity subsists, and which therefore always unites whenever they come in contact. Suppose we have dissolved in another portion of water a quantity of barytes, just sufficient to saturate the sulfuric acid in the sulfate of soda. If we mix these two solutions together, the barytes will combine with the sulfuric acid, and the compound, sulfate of barytes, will fall to the bottom, leaving a pure solution of soda in the water. In this case, the barytes has seized all the sulfuric acid and displaced the soda. The reason of this, according to Berthollet, is not that barytes has a stronger affinity for sulfuric acid than soda does, but because sulfate of barytes is insoluble in water. It therefore falls down, and of course the sulfuric acid is withdrawn from the soda. But if we add to a solution of sulfate of soda as much potash as will saturate all the sulfuric acid, no such decomposition will take place. At least we have no evidence that it does. Both the alkalis in this case will unite to the acid and form a triple compound, consisting of potash, sulfuric acid, and soda. Let us now concentrate the solution by evaporation, and crystals of sulfate of potash will fall down. The reason is that sulfate of potash is not nearly so soluble in water as sulfate of soda. Hence it separates, not because sulfuric acid has a greater affinity for potash than for soda, but because sulfate of potash is a much less soluble salt than sulfate of soda. This mode of reasoning of Berthollet is plausible but not convincing. It is merely an argumentum ad ignorantium. We can only prove the decomposition by separating the salts from each other, and this can only be done by their difference of solubility. But cases occur in which we can judge that decomposition has taken place from some other phenomena than precipitation. For example, nitrate of copper is a blue salt, while muriate of copper is green. If into a solution of nitrate of copper we pour muriatic acid, no precipitation appears, but the color changes from blue to green. Is not this an evidence that the muriatic acid has displaced the nitric, and that the salt held in solution is not nitrate of copper, as it was at first, but muriate of copper? Berthollet accounts for all decompositions which take place when a third body is added, either by insolubility or by elasticity, as, for example, when sulfuric acid is poured into a solution of carbonate of ammonia. The carbonic acid all flies off in consequence of its elasticity, and the sulfuric acid combines with the ammonia in its place. I confess that this explanation of the reason why the carbonic acid flies off appears to me very defective. The ammonia and carbonic acid are united by a force quite sufficient to overcome the elasticity of the carbonic acid. Accordingly, it exhibits no tendency to escape. Now, why should the elasticity of the acid cause it to escape when sulfuric acid is added? It certainly could not do so unless it has weakened the affinity by which it is kept united to the ammonia. Now, this is the very point for which Bergman contends. The subject will claim our attention afterwards when we come to the electrochemical discoveries, which distinguished the first 10 years of the present century. Another opinion supported by Berthollet in his chemical statics is that quantity may be made to overcome force, or, in other words, that if we mix a great quantity of a substance which has a weaker affinity with a small quantity of a substance which has a stronger affinity, the body having the weaker affinity will be able to overcome the other, and combine with a third body in place of it. He gave a number of instances of this. Particularly, he showed that a large quantity of potash, when mixed with a small quantity of sulfate of barytes, is able to deprive the barytes of a portion of its sulfuric acid. In this way he accounted for the decomposition of the common salt by carbonate of lime in the soda lakes in Egypt, and the decomposition of the same salt by iron, as noticed by Scheele. I must acknowledge myself not quite satisfied with Berthollet's reasoning on this subject. No doubt if two atoms of a body having a weaker affinity, and one atom of a body having a stronger affinity, were placed at equal distance from an atom of a third body, the force of the two atoms might overcome that of the one atom. And it is possible that such cases may occasionally occur, but such a balance of distances must be rare and accidental. I cannot think that all the cases adduced by Berthollet are of a complicated nature, and admit of an explanation independent of the efficacy of mass. And at any rate, abundance of instances might be stated in which mass appears to have no preponderating effect whatever. Chemical decomposition is a phenomenon of so complicated a nature that it is more than doubtful whether we are yet in possession of data sufficient to enable us to analyze the process with accuracy. Another opinion brought forward by Berthollet in his work was of a startling nature, and occasioned a controversy between him and Proust, which was carried on for some years with great spirit, but with perfect decorum and good manners on both sides. Berthollet affirmed that bodies were capable of uniting with each other in all possible proportions, and that there is no such thing as a definite compound, unless it has been produced by some accidental circumstances, as insolubility, volatility, etc. Thus, every metal is capable of uniting with all possible doses of oxygen, so that instead of 1 or 2 oxides of every metal, an infinite number of oxides of each metal exist. Proust affirmed that all compounds are definite. Iron, says he, unites with oxygen only in 2 proportions. We have either a compound of 3.5 iron and 1 oxygen, or of 3.5 iron and 1 to 5 oxygen. The first constitutes the black, and the second the red oxide of iron, and besides these there is no other. Everyone is now satisfied that Proust's view of the subject was correct, and Berthollet's erroneous. But a better opportunity will occur hereafter to explain this subject, or at least give the information respecting it, which we at present possess. Berthollet in this book points out the quantity of each base necessary to neutralize a given weight of acid, and he considers the strength of affinity as inversely that quantity. Now, of all the bases known when Berthollet wrote, ammonia is capable of saturating the greatest quantity of acid. Hence he considered its affinity for acids as stronger than that of any other base. Barytes, on the contrary, saturates the smallest quantity of acid. Therefore, its affinity for acids is smallest. Now, ammonia is separated from acids by all the other bases, while there is not one capable of separating barytes. It is surprising that the notoriety of this fact did not induce him to hesitate before he came to so problematical a conclusion. Mr. Keren had already considered the force of affinity as directly proportional to the quantity of base necessary to saturate a given weight of acid. When we consider the subject metaphysically, Berthollet's opinion is most plausible, for it is surely natural to consider that body as the strongest which produces the greatest effect. Now, when we deprive an acid of its properties, or neutralize it by adding a base, one would be disposed to consider that base as acting with most energy, which with the smallest quantity of matter is capable of producing a given effect. This was the way Berthollet reasoned. But if we attend to the power which one base has of displacing another, we shall find it nearly proportional to the weight of it necessary to saturate a given weight of acid, or at least those bases act most powerfully in displacing others, of which the greatest quantity is necessary to saturate a given weight of acid. Keren's opinion, therefore, was more conformable to the order of decomposition. These 2 opposite views of the subject show clearly that neither Keren nor Berthollet had the smallest conception of the atomic theory, and consequently that the allegation of Mr. Higgins that he had explained the atomic theory in his book on phlogiston, published in the year 1789, was not well founded. Whether Berthollet had read that book I do not know, but there can be no doubt that it was perused by Keren, who, however, did not receive from it the smallest notions respecting the atomic theory. Had he imbibed any such notions, he never would have considered chemical affinity as capable of being measured by the weight of base capable of neutralizing a given weight of acid. Berthollet was not only a man of great energy of character, but of the most liberal feelings and benevolence. The only exception to this is his treatment of M. Clement. This gentleman, in company with M. Desaulniers, had examined the carbonic acid of Priestley, and had shown, as Cruikshanks had done before him, that it is a compound of carbon and oxygen, and that it contains no hydrogen whatever. Berthollet examined that same gas, and he published a paper to prove that it was a triple compound of oxygen, carbon, and hydrogen. This occasioned a controversy, which chemists have finally determined in favor of the opinion of Clement and Desaulniers. Berthollet, during this discussion, did not on every occasion treat his opponents with his accustomed temper and liberality, and ever after he opposed all attempts on the part of Clement to be admitted a member of the Institute. Whether there was any other reason for this conduct on the part of Berthollet, besides a difference of opinion respecting the composition of carbonic oxide, I do not know, nor would it be right to condemn him without a more exact knowledge of all the circumstances that I can pretend to. Antoine Francois de Fourcroy was born at Paris on the 15th of June, 1755. His family had long resided in the capital, and several of his ancestors had distinguished themselves at the bar. But the branch from which he sprung had gradually sunk into poverty. His father exercised in Paris the trade of an apothecary, in consequence of a charge which he held in the house of the Duke of Orleans. The corporation of apothecaries having obtained the general suppression of all such charges, M. de Fourcroy, the father, was obliged to renounce his mode of livelihood, and his son grew up in the midst of the poverty produced by the monopoly of the privileged bodies in Paris. He felt the situation the more keenly, because he possessed from nature an extreme sensibility of temper. When he lost his mother at the age of 7 years, he attempted to throw himself into her grave. The care of an elder sister preserved him with difficulty till he reached the age at which it was usual to be sent to college. There he was unlucky enough to meet with a brutal master, who conceived an aversion for him and treated him with cruelty. The consequence was a dislike to study, and he quitted the college at the age of 14, somewhat less informed than when he went to it. His poverty now was such that he was obliged to endeavor to support himself by becoming writing master. He had even some thoughts of going on the stage, but was prevented by the hisses bestowed on a friend of his who had unadvisedly entered upon that perilous career, and was treated in consequence without mercy by the audience. While uncertain what plan to follow, the advice of Vicar d'Azur induced him to commence the study of medicine. This great anatomist was an acquaintance of M. de Fourcroy the father. Struck with the appearance of his son, and the courage with which he struggled with his bad fortune, he conceived an affection for him, and promised to direct his studies, and even to assist him during their progress. The study of medicine to a man in his situation was by no means an easy task. He was obliged to lodge in a garret, so low in the roof that he could only stand upright in the middle of the room. Beside him lodged a water-carrier with 12 children. Fourcroy acted as physician to this numerous family, and in recompense was always supplied with an abundance of water. He contrived to support himself by giving lessons to other students, by facilitating the researches of richer writers, and by some translations which he sold to a bookseller. For these he was only half paid, but the conscientious bookseller offered 30 years afterwards to make up the deficiency, when his creditor was become Director General of Public Instruction. Fourcroy studied with so much zeal and ardor that he soon became well acquainted with the subject of medicine. But this was not sufficient. It was necessary to get a doctor's degree, and all the expenses at that time amounted to 250 lire. An old physician, Dr. Deist, had left funds to the faculty to give a gratuitous degree and license, once every 2 years, to the poor student who should best deserve them. Fourcroy was the most conspicuous student at that time in Paris. He would therefore have reaped the benefit of this benevolent institution had it not been for the unlucky situation in which he was placed. There happened to exist a quarrel between the faculty charged with the education of medical men and the granting of degrees, and a society recently formed by government for the improvement of the medical art. This dispute had been carried to a great length, and had attracted the attention of all the frivolous and idle inhabitants of Paris. Vicar d'Azur was secretary to the society, and of course one of its most active champions, and was in consequence particularly obnoxious to the faculty of medicine at Paris. Fourcroy was unluckily the acknowledged protégé of this eminent anatomist. This was sufficient to induce the faculty of medicine to refuse him a gratuitous degree. He would have been excluded in consequence of this from entering on the career of a practitioner, had not the society, enraged at this treatment, and influenced by a violent party spirit, formed a subscription and contributed the necessary expenses. It was no longer possible to refuse M. de Fourcroy the degree of doctor, when he was thus enabled to pay for it. But above the simple degree of doctor, there was another, entitled Docteur Regent, which depended entirely on the votes of the faculty. It was unanimously refused to M. de Fourcroy. This refusal put it out of his power afterwards to commence teacher in the medical school, and gave the medical faculty the melancholy satisfaction of not being able to enroll among their number the most celebrated professor in Paris. This violent and unjust conduct of the faculty of medicine made a deep impression on the mind of Fourcroy, and contributed not a little to the subsequent downfall of that powerful body. End of section 52. Recording by Lawrence Trask. InterfaceAudio.com. Section 53 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, InterfaceAudio.com, Mount Vernon, Ohio. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 3, Progress of Scientific Chemistry in France, Part 10. Fourcroy being thus entitled to practice in Paris, his success depended entirely on the reputation which he could contrive to establish. For this purpose he devoted himself to the sciences connected with medicine, as the shortest and most certain road by which he could reach his object. His first writings showed no predilection for any particular branch of science. He wrote upon chemistry, anatomy, and natural history. He published an abridgment of the history of insects, and a description of the bursa mucosa of the tendons. This last piece seems to have given him the greatest celebrity, for in 1785 he was admitted, in consequence of it, into the Academy as an anatomist. But the reputation of Buquet, at this time very high, gradually drew his particular attention to chemistry, and he retained this predilection during the rest of his life. Buquet was at that time professor of chemistry in the medical school of Paris, and was greatly celebrated and followed on account of his eloquence and the elegance of his language. Fourcroy became in the first place his pupil, and afterwards his particular friend. One day, when a sudden attack of disease prevented him from lecturing as usual, he entreated Fourcroy to supply his place. Our young chemist at first declined, and alleged his ignorance of the method of addressing a public audience. But, overcome by the persuasions of Buquet, he at last consented, and in this, his first essay, he spoke 2 hours without disorder or hesitation, and acquitted himself to the satisfaction of his whole audience. Buquet soon after substituted him in his place, and it was in his laboratory and in his classroom that he first made himself acquainted with chemistry. He was enabled, at the death of Buquet, in consequence of an advantageous marriage that he had made, to purchase the apparatus and cabinet of his master. And although the faculty of medicine would not allow him to succeed to the chair of Buquet, they could not prevent him from succeeding to his reputation. There was a kind of college which had been established in the Jardin du Roi, which at that time was under the superintendence of Buffon, and Marquer was the professor of chemistry in this institution. On the death of this chemist in 1784, both Berthollet and Fourcroy offered themselves as candidates for the vacant chair. The voice of the public was so loud in favor of Fourcroy that he was appointed to the situation in spite of the high character of his antagonist, and the political influence which was exerted in his favor. He filled this chair for 25 years, with a reputation for eloquence continually on the increase. Such were the crowds, both of men and women, who flocked to hear him, that it was twice necessary to enlarge the size of the lecture room. After the Revolution had made some progress, he was named a member of the National Convention in the autumn of the memorable year 1793. It was during the Reign of Terror, when the Convention itself, and with it all France, was under the absolute dominion of one of the most sanguinary monsters that ever existed. It was almost equally dangerous for the members of the Convention to remain silent, or to take an active part in the business of that assembly. Fourcroy never opened his mouth in the Convention till after the death of Robespierre. At this period he had influence enough to save the lives of some men of merit, among others of Darcy, who did not know the obligation under which he lay to him till long after. At last his own life was threatened, and his influence, of course, completely annihilated. It was during this unfortunate and disgraceful period that many eminent men lost their lives, among others Lavoisier, and Fourcroy is accused of having contributed to the death of this illustrious chemist. But Cuvier entirely acquits him of this atrocious charge, and assures us that it was urged against him merely out of envy at his subsequent elevation. If in rigorous researches which we have made, says Cuvier in his Eloge of Fourcroy, we had found the smallest proof of an atrocity so horrible, no human power could have induced us to sully our mouths with his Eloge, or to have pronounced it within the walls of this temple, which ought to be no less sacred to honor than to genius. Fourcroy began to acquire influence only after the 9th Thermidor, when the nation was wearied with destruction, and when efforts were making to restore those monuments of science, and those public institutions for education, which during the wantonness and folly of the Revolution had been overturned and destroyed. Fourcroy began to acquire influence only after the 9th Thermidor, when the nation was wearied with destruction, and when efforts were making to restore those monuments of science, and those public institutions for education, which during the wantonness and folly of the Revolution had been overturned and destroyed. Fourcroy was particularly active in this renovation, and it was to him chiefly that the schools established in France for the education of youth are to be ascribed. The Convention had destroyed all the colleges, universities, and academies throughout France. The effects of this absurd abolition soon became visible. The army stood in need of surgeons and physicians, and there were none educated to supply the vacant places. 3 new schools were founded for educating medical men. They were nobly endowed. The term schools of medicine was prescribed as too aristocratical. They were distinguished by the ridiculous appellation of schools of health. The Polytechnic School was next instituted, as a kind of preparation for the exercise of the military profession, where young men could be instructed in mathematics and natural philosophy, to make them fit for entering the schools of the artillery, of engineers, and of the marine. The Central Schools was another institution for which France was indebted to the efforts of Fourcroy. The idea was good, though it was very imperfectly executed. It was to establish a kind of university in every department, for which the young men were to be prepared by a sufficient number of inferior schools scattered throughout the department. But unfortunately, these inferior schools were never properly established or endowed, and even the central schools themselves were never supplied with the proper masters. Indeed, it was found impossible to furnish such a number of masters at once. On that account, an institution was established in Paris, called the Normal School, for the express purpose of educating a sufficient number of masters to supply the different central schools. Fourcroy, either as a member of the Convention or of the Council of the Ancients, took an active part in all these institutions, as far as regarded the plan and the establishment. He was equally concerned in the establishment of the Institute and of the Musée d'Histoire Naturelle. This last was endowed with the utmost liberality, and Fourcroy was one of the first professors, as he was also in the School of Medicine and the Polytechnic School. He was equally concerned in the restoration of the university, which constituted one of the most useful parts of Bonaparte's reign. The violent exertions which he made in the numerous situations which he filled, and the prodigious activity which he displayed, gradually undermined his constitution. He himself was sensible of his approaching death, and announced it to his friends as an event which would speedily take place. On the 16th of December, 1809, after signing some dispatches, he suddenly cried out, "Je suis mort," I am dead, and dropped lifeless on the ground. He was twice married, first to Mademoiselle Bettinger, by whom he had 2 children, a son and a daughter who survived him. He was married for the second time to Madame Belleville, the widow of Availle, by whom he had no family. He left but little fortune behind him, and 2 maiden sisters who lived with him, depended afterwards for their support on his friend, M. Vauquelin. Notwithstanding the vast quantity of papers which he published, it will be admitted without dispute that the prodigious reputation which he enjoyed during his lifetime was more owing to his eloquence than to his eminence as a chemist, though even as a chemist he was far above mediocrity. He must have possessed an uncommon facility of writing. 5 successive editions of his System of Chemistry appeared, each of them gradually increasing in size and value, the first being in 2 volumes, and the last in 10. This last edition he wrote in 16 months. It contains much valuable information, and doubtless contributed considerably to the general diffusion of chemical knowledge. Its style is perhaps too diffuse, and the spirit of generalizing from particular and often ill-authenticated facts is carried to a vicious length. Perhaps the best of all his productions is his Philosophy of Chemistry. It is remarkable for its conciseness, its perspicuity, and the neatness of its arrangement. Besides these works, and the periodical publication entitled La Médecine Éclairée, of which he was the editor, there are above 160 papers on chemical subjects, with his name attached to them, which appeared in the Memoir of the Academy and of the Institute, and in the Annales de Chimie, or the Annales du Musée d'Histoire Naturelle, of which last work he was the original projector. Many of these papers contain analysis, both animal, vegetable, and mineral, of very considerable value. In most of them the name of Vauquelin is associated with his own as the author, and the general opinion is that the experiments were all made by Vauquelin, but that the papers themselves were drawn up by Fourcroy. It would serve little purpose to go over this long list of papers, because though they contributed essentially to the progress of chemistry, yet they exhibit but few of those striking discoveries which at once alter the face of the science, by throwing a flood of light on everything around them. I shall merely notice a few of what I consider as his best papers. Number 1. He ascertained that the most common biliary calculi are composed of a substance similar to spermaceti. This substance, in consequence of a subsequent discovery which he made during the removal of the dead bodies from the burial ground of the Innocents at Paris, namely, that these bodies are converted into a fatty matter he called adipocere. It has been since distinguished by the name of cholestin, and has been shown to possess properties different from those of adipocere and spermaceti. 2. It is to him that we are indebted for the first knowledge of the fact that the salts of magnesia and ammonia have the property of uniting together and forming double salts. 3. His dissertation on the sulphate of mercury contains some good observations. The same remark applies to his paper on the action of ammonia on the sulphate, nitrate, and muriate of mercury. He first discovered the double salts which are formed. 4. The analysis of urine would have been valuable had not almost all the facts contained in it been anticipated by a paper of Dr. Wollaston, published in the Philosophical Transactions. It is to him that we are indebted for almost all the additions to our knowledge of calculi, since the publication of Scheele's original paper on the subject. 5. I may mention the process of Fourcroy and Van Cailleen for obtaining pure barytes by exposing nitrate of barytes to a red heat as a good one. They discovered the existence of phosphate of magnesia in bones, of phosphorus in the brain and in the milts of fishes, and of a considerable quantity of saccharine matter in the bulb of the common onion, which, by undergoing a kind of spontaneous fermentation, was converted into manna. In these and many other similar discoveries, which I think it is unnecessary to notice, we do not know what fell to the share of Fourcroy and what to Vauquelin, but there is one merit at least to which Fourcroy is certainly entitled, and it is no small one. He formed and brought forward Vauquelin, and proved to him ever after a most steady and indefatigable friend. This is bestowing no small panegyric on his character, for it would have been impossible to have retained such a friend through all the horrors of the French Revolution, if his own qualities had not been such as to merit so steady an attachment. Louis Bernard Guyton de Marveaux was born at Dijon on the 4th of January, 1737. His father, Anthony Guyton, was professor of civil law in the University of Dijon, and descended from an ancient and respectable family. At the age of 7, he showed an uncommon mechanical turn. Being with his father at a small village near Dijon, he there happened to meet a public officer returning from a sale, whence he brought back a clock that had remained unsold on account of its very bad condition. Morveau supplicated his father to buy it. The purchase was made for 6 francs. Young Morveau took it to pieces and cleaned it, supplied some parts that were wanting, and put it up again without any assistance. In 1799 this very clock was resold at a higher price, together with the estate and the house in which it had been originally placed, having during the whole of that time continued to go in the most satisfactory manner. When only 8 years of age, he took his mother's watch to pieces, cleaned it, and put it up again, to the satisfaction of all parties. After finishing his preliminary studies in his father's house, he went to college, and terminated his attendance on it at the age of 16. About this time he was instructed in botany by M. Michaud, a friend of his father, and a naturalist of some eminence. He now commenced law student in the University of Dijon, and after 3 years of intense application, he went to Paris to acquire a knowledge of the practice of the law. While in Paris, he not only attended to law, but cultivated at the same time several branches of political literature. In 1756, he paid a visit to Voltaire at Ferney. This seems to have inspired him with a love of poetry, particularly of the descriptive and satiric kind. About a year afterwards, when only 20, he published a poem called Le Rat Iconoclaste, ou le Jésuite Croquet. It was intended to throw ridicule on a well-known anecdote of the day, and to assist in blowing the fire that had already threatened destruction to the obnoxious order of Jesuits. The adventure alluded to was this. Some nuns who felt a strong predilection for a Jesuit, their spiritual director, were engaged in their accustomed Christmas occupation of modeling a representation of a religious mystery, decorated with several small statues representing the holy personages connected with the subject, and among them that of the ghostly father. But to mark their favorite, his statue was made of loaf sugar. The following day was destined for the triumph of the Jesuit, but meanwhile a rat had devoured the valuable puppet. The poem is written after the agreeable manner of the celebrated poem, Ververs. At the age of 24, he had already pleaded several important causes at the bar, when the office of Advocate General at the Parliament of Dijon was advertised for sale. At that time, all public situations, however important, were sold to the best bidder. His father, having ascertained that this place would be acceptable to his son, purchased it for 40,000 francs. The reputation of the young advocate and his engaging manners facilitated the bargain. In 1764 he was admitted an honorary member of the Academy of Sciences, Arts, and Belles Lettres of Dijon. 2 months after, he presented to the assembled chamber of the Parliament of Burgundy a memoir on public instruction, with a plan for a college on the principles detailed in his work. The encomiums which every public journal of the time passed on this production, and the flattering letters which he received, were unequivocal proofs of its value. In this memoir he endeavored to prove that man is bad or good according to the education which he has received. This doctrine was contrary to the creed of Diderot, who affirmed in his essay on the life of Seneca that nature makes wicked persons, and that the best institutions cannot render them good. But this mischievous opinion was successfully refuted by Morveau in a letter to an anonymous friend. The exact sciences were so ill taught and lamely cultivated at Dijon during the time of his university education that after his admission into the academy, his notions on mechanics and natural philosophy were scanty and inaccurate. Dr. Chardonnot was in the habit of reading memoirs on chemical subjects, and on one occasion Morveau thought it necessary to hazard some remarks which were ill received by the doctor, who sneeringly told him that having obtained such success in literature, he had better rest satisfied with the reputation so justly acquired, and leave chemistry to those who knew more of the matter. Provoked at this violent remark, he resolved upon taking an honorable revenge. He therefore applied himself to the study of Marquère's Theoretical and Practical Chemistry, and of the Manual of Chemistry which Baume had just published. To the last chemist he also sent an extensive order for chemical preparations and utensils, with a view of forming a small laboratory near his office. He began by repeating many of Baume's experiments, and then trying his inexperienced hand at original researches. He soon found himself strong enough to attack the doctor. The latter had just been reading a memoir on the analysis of different kinds of oil, and Morveau combated some of his opinions with so much skill and sagacity as astonished everyone present. After the meeting, Dr. Chardonnot addressed him thus: "You are born to be an honor to chemistry. So much knowledge could only have been gained by genius united with perseverance. Follow your new pursuit, and confer with me in your difficulties." But this new pursuit did not prevent Morveau from continuing to cultivate literature with success. He wrote an elegy of Charles V of France, surnamed the Wise, which had been given out as the subject of a prize by the Academy. A few months afterwards, at the opening of the session of Parliament, he delivered a discourse on the actual state of jurisprudence, on which subject, 3 years after, he composed a more extensive and complete work. No code of laws demanded reform more urgently than those of France, and none saw more clearly the necessity of such a reformation. About this time a young gentleman of Dijon had taken into his house an adept, who offered, upon being furnished with the requisite materials, to produce gold in abundance. But after 6 months of expensive and tedious operations, during which period the roguish pretender had secretly distilled many oils, etc., which he disposed of for his own profit, the gentleman, beginning to doubt the sincerity of his instructor, dismissed him from his service, and sold the whole of his apparatus and materials to Morveau for a trifling sum. Soon after he repaired to Paris to visit the scientific establishments of that metropolis, and to purchase preparations and apparatus which he still wanted to enable him to pursue with effect his favourite study. For this purpose he applied to Baume, then one of the most conspicuous of the French chemists. Pleased with his ardour, Baume inquired what courses of chemistry he had attended. "None," was the answer. "How then could you have learned to make experiments, and above all, How could you have acquired the requisite dexterity? Practice, replied the young chemist, has been my master. Melted crucibles and broken retorts, my tutors. In that case, said Baume, you have not learned, you have invented. About this time, Dr. Chardonnot read a paper before the Dijon Academy on the causes of the augmentation of weight which metals experience when calcined. He combated the different explanations which had been already advanced, and then proceeded to show that it might be accounted for in a satisfactory manner by the abstraction of phlogiston. This drew the attention of Morveau to the subject. He made a set of experiments a few months afterwards, and read a paper on the phenomena of the air during combustion. It was soon after that he made a set of experiments on the time taken by different substances to absorb or emit a given quantity of heat. These experiments, if properly followed out, would have led to the discovery of specific heat, but in his hands they seem to have been unproductive. End of section 53. Recording by Lawrence Trask, interfaceaudio.com, Mount Vernon, Ohio. Section 54 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The History of Chemistry, Volume 2, Chapter 3, The Progress of Scientific Chemistry in France, Part 2. In the year 1772, he published a collection of scientific essays under the title of Digressions Académiques. The memoirs on phlogiston, crystallization, and solution found in this book deserve particular attention and show the superiority of Morveau over most of the chemists of the time. About this time an event happened which deserves to be stated. It had been customary in one of the churches of Dijon to bury considerable numbers of dead bodies. From these an infectious exhalation had proceeded, which had brought on a malignant disorder and threatened the inhabitants of Dijon with something like the plague. All attempts to put an end to this infectious matter had failed, when Morveau tried the following method with complete success. A mixture of common salt and sulphuric acid in a wide-mouthed vessel was put upon chafing dishes in various parts of the church. The doors and windows were closed and left in this state for 24 hours. They were then thrown open, and the chafing dishes with the mixtures removed. Every remains of the bad smell was gone, and the church was rendered quite clean and free from infection. The same process was tried soon after in the prisons of Dijon, with the same success. Afterwards, chlorine gas was substituted for muriatic acid gas, and found still more efficacious. The present practice is to employ chloride of lime or chloride of soda for the purpose of fumigating infected apartments, and the process is found still more effectual than the muriatic acid gas, as originally employed by Morveau. The nitric acid fumes proposed by Dr. Carmichael Smith are also efficacious, but the application of them is much more troublesome and more expensive than of chloride of lime, which costs very little. In the year 1774, it occurred to Morveau that a course of lectures on chemistry, delivered in his native city, might be useful. Application being made to the proper authorities, the permission was obtained, and the necessary funds for supplying a laboratory granted. These lectures were begun on the 29th of April, 1776, and seem to have been of the very best kind. Everything was stated with great clearness, and illustrated by a sufficient number of experiments. His fame now began to extend, and his name to be known to men of science in every part of Europe, and in consequence he began to experience the fate of almost all eminent men, to be exposed to the attacks of the malignant and the envious. The experiments which he exhibited to determine the properties of carbonic acid gas drew upon him the animadversions of several medical men, who affirmed that this gas was nothing else than a peculiar state of sulphuric acid. Morveau answered these animadversions in 2 pamphlets, and completely refuted them. About this time he got metallic conductors erected on the house of the Academy at Dijon. On this account he was attacked violently for his presumption in disarming the hand of the Supreme Being. A multitude of fanatics assembled to pull down the conductors, and they would probably have done much mischief had it not been for the address of M. Maret, the secretary, who assured them that the astonishing virtue of the apparatus resided in the gilded point, which had purposely been sent from Rome by the Holy Father. Will it excite any surprise that within less than 20 years after this, the mass of the French people not only denounced the Christian religion and the spiritual dominion of the Pope, but declared themselves atheists? In 1777, Morveau published the first volume of a course of chemistry, which was afterwards followed by 3 other volumes, and is known by the name of Elements de Chimie de l'Académie de Dijon. This book was received with universal approbation, and must have contributed very much to increase the value of his lectures. Indeed, a textbook is essential toward a successful course of lectures. It puts it in the power of the students to understand the lecture if they be at the requisite pains, and gives them a means of clearing up their difficulties, when any such occur. I do not hesitate to say that a course of chemical lectures is twice as valuable when the students are furnished with a good textbook, as when they are left to interpret the lectures by their own unassisted exertions. Soon after, he undertook the establishment of a manufacture of saltpetre upon a large scale. For this he received the thanks of M. Necker, who was at that time Minister of Finance, in the name of the King of France. This manufactory he afterwards gave up to M. Courtois, whose son still carries it on, and is advantageously known to the public as the discoverer of iodine. His next object was to make a collection of minerals, and to make himself acquainted with the science of mineralogy. All this was soon accomplished. In 1777 he was charged to examine the slate quarries and the coal mines of Burgundy, for which purpose he performed a mineralogical tour through the province. In 1779 he discovered a lead mine in that country, and a few years afterwards, when the attention of chemists had been drawn to sulphate of barytes and its base by the Swedish chemists, he sought for it in Burgundy, and found it in considerable quantity at Thote. This enabled him to draw up a description of the mineral, and to determine the characters of the base, to which he gave the name baryte, afterwards altered to that of barytes. This paper was published in the 3rd volume of the Memoir of the Dijon Academy. In this paper he describes his method of decomposing sulphate of barytes by heating it with charcoal, a method now very frequently followed. In the year 1779 he was applied to by Pencook, who meditated the great project of the Encyclopédie Méthodique to undertake the chemical articles in that immense dictionary, and the demand was supported by a letter from Buffon, whose request he did not think he would with propriety refuse. The engagement was signed between them in September 1780. The first half-volume of the chemical part of this encyclopedia did not appear till 1786, and Morveau must have been employed during the interval in the necessary study and researches. Indeed, it is obvious, from the many of the articles, that he had spent a good deal of time in experiments of research. The state of the chemical nomenclature was at that period peculiarly barbarous and defective. He found himself stopped at every corner for want of words to express his meaning. This state of things he resolved to correct, and accordingly in 1782 published his first essay on a new chemical nomenclature. No sooner did this essay appear than it was attacked by almost all chemists of Paris, and by none more zealously than by the chemical members of the Academy. Undismayed by the violence of his antagonists, and satisfied with the rectitude of his views and the necessity of the reform, he went directly to Paris to answer the objections in person. He not only succeeded in convincing his antagonists of the necessity of reform, but a few years afterwards prevailed upon the most eminent chemical members of the Academy, Lavoisier, Berthollet, and Fourcroy, to unite with him in rendering the reform still more complete and successful. He drew up a memoir, exhibiting a plan of a methodical chemical nomenclature, which was read at a meeting of the Academy of Sciences in 1787. Morveau, then, was in reality the author of the new chemical nomenclature, if we accept a few terms, which had been already employed by Lavoisier. Had he done nothing more for the science than this, it would deservedly have immortalized his name. For everyone must be sensible how much the new nomenclature contributed to the subsequent rapid extension of chemical science. It was during the repeated conferences held with Lavoisier and the two other associates that Morveau became satisfied of the truth of Lavoisier's new doctrine, and that he was induced to abandon the phlogistic theory. We do not know the methods employed to convert him. Doubtless both reasoning and experiment were made use of for the purpose. It was during this period that Morveau published a French translation of the Opuscula of Bergman. A society of friends, under his encouragement, translated the chemical memoirs of Scheele and many other foreign books of importance, which by their means were made known to the men of science in France. In 1783, in consequence of a favorable report by Marquer, Morveau obtained permission to establish a manufactory of carbonate of soda, the first of the kind ever attempted in France. It was during the same year he published his collections of pleadings at the bar, among which we find his Discours sur le Bonhomme, delivered at the opening of the sessions at Dijon, with which he took leave of his fellow magistrates, surrendering the insignia of the office, as he had determined to quit the profession of the law. On the 25th of April, 1784, Morveau, accompanied by President Yearsley, ascended from Dijon in a balloon which he had himself constructed, and repeated the ascent on the 12th of June following, with a view of ascertaining the possibility of directing these aerostatic machines by an apparatus of his own contrivance. The capacity of the balloon was 10,498,074 French cubic feet. The effect produced by this bold undertaking by two of the most distinguished characters in the town was beyond description. Such ascents were then quite new, and looked upon with a kind of reverential awe. Though Morveau failed in his attempts to direct these aerial vessels, yet his method was ingenious and exceedingly plausible. In 1786, Dr. Murray, secretary to the Dijon Academy, having fallen a victim to an epidemic disease, which he had in vain attempted to arrest, Morveau was appointed perpetual secretary and chancellor of the institution. Soon after this, the first half-volume of the chemical part of the Encyclopædia Méthodique made its appearance, and drew the attention of every person interested in the science of chemistry. No chemical treatise had hitherto appeared worthy of being compared to it. The article acid, which occupies a considerable part, is truly admirable, and whether we consider the historical details, the completeness of the accounts, the accuracy of the description of the experiments, or the elegance of the style, constitutes a complete model of what such a work should be. I may perhaps be partial, as it was from this book that I imbibed my own first notions in chemistry, but I never perused any book with more delight, and when I compared it with the best chemical books of the time, whether German, French, or English, its superiority became still more striking. In the article Acier, Morveau had come to the very same conclusions with respect to the nature of steel as had been come to by Berthollet, Mongre, and Van der Monde in their celebrated paper on the subject, just published in the Memoirs of the Academy. His own article had been printed, though not published, before the appearance of the Memoir of the Academicians. This induced him to send an explanation to Berthollet, which was speedily published in the Journal de Physique. In September 1787, he received a visit from Lavoisier, Berthollet, Fourcroy, Monge, and Vandermonde. Dr. Beddoes, who was traveling through France at the time, and happened to be in Dijon, joined the party. The object of the meeting was to discuss several experiments explanatory of the new doctrine. In 1789, an attempt was made to get him admitted as a member of the Academy of Sciences, but it failed, notwithstanding the strenuous exertions of Berthollet and his other chemical friends. The French Revolution had now broken out, occasioned by the wants of the state on one hand, and the resolute determination of the clergy and the nobility on the other, not to submit to bear any share in the public burdens. During the early part of this revolution, Morveau took no part whatever in politics. In 1790, when France was divided into departments, he was named one of a commission by the National Assembly for the formation of the Department of the Côte d'Or. On the 25th of August, 1791, he received from the Academy of Sciences the annual prize of 2,000 francs for the most useful work published in the course of the year. This was decreed for him for his Dictionary of Chemistry in the Encyclopædia Méthodique. Aware of the pressing necessities of the state, Morveau seized the opportunity of showing his desire of contributing towards its relief by making a patriotic offering of the whole amount of his prize. When the election of the Second Constitutional Assembly took place, he was nominated a member by the Electoral College of his department. A few months before, his name had appeared among the list of members proposed by the Assembly for the election of a governor for the heir apparent. All this, together with the dignity of Solicitor General of the department, to which he had recently been raised, not permitting him to continue his chemical lectures at Dijon, of which he had already delivered 15 gratuitous courses, he resigned his chair in favor of Dr. Chaussier, afterwards a distinguished professor at the Faculty of Medicine of Paris, and, bidding adieu to his native city, proceeded to Paris. On the ever-memorable 16th of January, 1793, he voted with the majority of his deputies. He was therefore, in consequence of this vote, a regicide. During the same year he resigned, in favor of the Republic, his pension of 2,000 francs, together with the arrears of that pension. In 1794 he received from the government different commissions to act with the French armies in the Low Countries. Charged with the direction of a great aerostatic machine for warlike purposes, he superintended that one in which the chief of the staff of General Jourdan and himself ascended during the battle of Fleurus, and which so materially contributed to the success of the French arms on that day. On his return from his various missions, he received from the 3 committees of the executive government an invitation to cooperate with several learned men in the instruction of the central schools, and was named Professor of Chemistry at École Centrale des Travaux Publics, since better known under the name of the Polytechnic School. In 1795 he was re-elected member of the Council of 500 by the electoral assemblies of Sarthe and Ile-et-Vilaine. The executive government at this time decreed the formation of the National Institute, and named him one of the 48 members chosen by government to form the nucleus of that scientific body. In 1797 he resigned all his public situations, and once more attached himself exclusively to science, and to the establishments for public instruction. In 1798 he was appointed a provisional director of the Polytechnic School, to supply the place of Monge, who was then in Egypt. He continued to exercise its duties during 18 months, to the complete satisfaction of every person connected with that establishment. With much delicacy and disinterestedness, he declined accepting the salary of 2,000 francs attached to this situation, which he thought belonged to the proper director, though absent from his duties. In 1799, Bonaparte appointed him one of the administrators general of the Mint, and the year following he was made director of the Polytechnic School. In 1803 he received the Cross of the Legion of Honor, then recently instituted, and in 1805 was made an officer of the same order. These honors were intended as a reward for the advantage which had accrued from the mineral acid fumigations which he had first suggested. In 1811 he was created a baron of the French Empire. After having taught in the École Polytechnique for 16 years, he obtained leave, on applying to the proper authorities, to withdraw into the retired station of private life, crowned with years and reputation, and followed with the blessings of the numerous pupils whom he had brought up in the career of science. In this situation he continued about 3 years, during which he witnessed the downfall of Bonaparte and the restoration of the Bourbons. On the 21st of December, 1815, he was seized with a total exhaustion of strength, and after an illness of 3 days only, expired in the arms of his disconsolate wife and a few trusty friends, having nearly completed the 80th year of his age. On the 3rd of January, 1816, his remains were followed to the grave by the members of the Institute and many other distinguished men, and Berthollet, one of his colleagues, pronounced a short but impressive funeral oration on his departed friend. Morveau had married Madame Picardet, the widow of a Dijon academician, who had distinguished himself by numerous scientific translations from the Swedish, German, and English languages. The marriage took place after they were both advanced in life, and he left no children behind him. His publications on chemical subjects were exceedingly numerous, and he contributed as much as any of his contemporaries to the extension of the science. But he was not the author of any striking chemical discoveries. It would be tedious to give a catalogue of his numerous productions, which were scattered through the Dijon Memoirs, the Journal de Physique, and the Annales de Chimie. End of section 54. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com.
Section 55 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 4, Progress of Analytical Chemistry. Analysis, or the art of determining the constituents of which every compound is composed, constitutes the essence of chemistry. It was therefore attempted as soon as the science put on anything like a systematic form. At first with very little success, but as knowledge became more and more general, chemists became more expert, and something like regular analysis began to appear. Thus Brandt showed that white vitriol is a compound of sulfuric acid and oxide of zinc, and Marggraf that selenite or gypsum is a compound of sulfuric acid and lime. Dr. Black made analyses of several of the salts of magnesia, so far at least as to determine the nature of the constituents, for hardly any attempt was made in that early period of the art to determine the weight of the respective constituents. The first person who attempted to lay down rules for the regular analysis of minerals and to reduce these rules to practice was Bergman. This he did in his papers De Documentia Minerarum Humida, De Terra Gemmarum, and De Terra Tourmalini, published between the years 1777 and 1780. To analyze a mineral, or to separate it into its constituent parts, it is necessary in the first place to be able to dissolve it in an acid. Bergman showed that most minerals become soluble in muriatic acid if they be reduced to a very fine powder and then heated to redness, or fused with an alkaline carbonate. After obtaining a solution in this way, he pointed out methods by which the different constituents may be separated one after another, and their relative quantities determined. The fusion with an alkaline carbonate required a strong red heat. An earthenware crucible could not be employed, because at a fusing temperature it would be corroded by the alkaline carbonate, and thus the mineral under analysis would be contaminated by the addition of a quantity of foreign matter. Bergman employed an iron crucible. This effectually prevented the addition of any earthy matter, but at a red heat the iron crucible itself is apt to be corroded by the action of the alkali, and thus the mineral under analysis becomes contaminated with a quantity of that metal. This iron might easily be separated again by known methods, and would therefore be of comparatively small consequence, provided we were sure that the mineral under examination contained no iron. But when that happens, and it is a very frequent occurrence, an error is occasioned which we cannot obviate. Klaproth made a vast improvement in the art of analysis by substituting crucibles of fine silver for the iron crucibles of Bergman. The only difficulty attending their use was that they were apt to melt unless great caution was used in heating them. Dr. Wollaston introduced crucibles of platinum about the beginning of the present century. It is from that period that we may date the commencement of accurate analyzing. Bergman's processes, as might have been expected, were rude and imperfect. It was Klaproth who first systematized chemical analysis and brought the art to such a state that the processes followed could be imitated by others with nearly the same results, thus offering a guarantee for the accuracy of the process. Martin Henry Klaproth, to whom chemistry lies under so many and such deep obligations, was born at Wernigerode on the 1st of December, 1743. His father had the misfortune to lose his whole goods by a great fire on the 30th of June, 1751, so that he was able to do little or nothing for the education of his children. Martin was the second of three brothers, the eldest of whom became a clergyman, and the youngest private secretary at war, and keeper of the archives of the Cabinet of Berlin. Martin survived both his brothers. He procured such meager instruction in the Latin language as the school of Wernigerode afforded, and he was obliged to procure his small school fees by singing as one of the church choir. It was at first his intention to study theology, but the unmerited hard treatment with which he met at school so disinclined him to study that he determined in his 16th year to learn the trade of an apothecary. 5 years which he was forced to spend as an apprentice and 2 as an assistant in the public laboratory in Quedlinburg furnished him with but little scientific information, and gave him little else than a certain mechanical adroitness in the most common pharmaceutical preparations. He always regarded as the epoch of his scientific instruction the 2 years which he spent in the public laboratory at Hanover, from Easter 1766 till the same time in 1768. It was there that he first met with some chemical books of merit, especially those of Spielmann and Karthauser, in which a higher scientific spirit already breathed. He was now anxious to go to Berlin, of which he had formed a high idea from the works of Pott, Henkel, Rose, and Marggraf. An opportunity presenting itself about Easter 1768, he was placed as assistant in the laboratory of Wendland, at the sign of the Golden Angel, in the Street of the Moors. Here he employed all the time which a conscientious discharge of the duties of his station left him in completing his own scientific education, and as he considered a profounder acquaintance with the ancient languages than he had been able to pick up at the school of Wernigerode, indispensable for a complete scientific education, he applied himself with great zeal to the study of the Greek and Latin languages, and was assisted in his studies by Mr. Poppelborn, at that time a preacher. About Michaelmas, 1770, he went to Danzig as assistant in the public laboratory, but in March of the following year he returned to Berlin as assistant in the office of the elder Valentine Rose, who was one of the most distinguished chemists of his day. But this connection did not continue long, for Rose died in 1771. On his deathbed, he requested Klaproth to undertake the superintendence of his office. Klaproth not only superintended this office for 9 years with the most exemplary fidelity and conscientiousness, but undertook the education of the 2 sons of Rose as if he had been their father. The younger died before reaching the age of manhood. The elder became his intimate friend and the associate of all his scientific researches. For several years before the death of Rose, which happened in 1808, they wrought together, and Klaproth was seldom satisfied with the results of his experiments till they had been repeated by Rose. In the year 1780, Klaproth went through his trials for the office of apothecary with distinguished applause. His thesis on phosphorus and distilled waters was printed in the Berlin Miscellanies for 1782. Soon after this, Klaproth bought what had formerly been the Fleming Laboratory in Spandau Street, and he married Sophia Christiana Lechmann, with whom he lived till 1803, when she died, in a happy state. They had 3 daughters and a son, who survived their parents. He continued in possession of this laboratory, in which he had arranged a small workroom of his own, till the year 1800, when he purchased the room of the academical chemists, in which he was enabled, at the expense of the Academy, to furnish a better and more spacious apartment for his labors, for his mineralogical and chemical collection, and for his lectures. As soon as he had brought the first arrangements of his office to perfection, an office which, under his inspection and management, became the model of a laboratory, conducted upon the most excellent principles, and governed with the most conscientious integrity, he published in the various periodical works of Germany, such as Krell's Chemical Annals, the writings of the Society for the Promotion of Natural Knowledge, Sell's Contribution to the Science of Nature and Medicine, Kohler's Journal, etc. A multitude of papers which soon drew the attention of chemists, for example, his Essay on Copal, on the elastic stone, on Proust's sel perlé, on the green lead spar of Chopow, on the best method of preparing ammonia, on the carbonate of barytes, on the wolfram of Cornwall, on wood tin, on the violet schorl, on the celebrated Ariel gold, on apatite, etc. All these papers, which secured him a high reputation as a chemist, appeared before 1788, when he was chosen an ordinary member of the physical class of the Royal Berlin Academy of Sciences. The Royal Academy of Arts had elected him a member a year earlier. From this time, every volume of the Memoirs of the Academy, and many other periodical works besides, contain numerous papers by this accomplished chemist, and there is not one of them which does not furnish us with a more exact knowledge of some one of the productions of nature or art. He has either corrected false representations, or extended views that were before partially known, or has revealed the composition and mixture of the parts of bodies, and has made us acquainted with a variety of new elementary substances. Amidst all these labors, it is difficult to say whether we should most admire the fortunate genius, which, in all cases, readily and easily divined the point where anything of importance lay concealed, or the acuteness which enabled him to find the best means of accomplishing his object, or the unceasing labor and incomparable exactness with which he developed it, or the pure scientific feeling under which he acted, and which was removed at the utmost possible distance from every selfish, every avaricious, and every contentious purpose. In the year 1795, he began to collect his chemical works which lay scattered among so many periodical publications, and gave them to the world under the title Beiträge zur chemischen Kenntnis del Mineralkörper, Contributions to the Chemical Knowledge of Mineral Bodies. Of this work, which consists of 6 volumes, the last was published in 1815, about a year before the author's death. It contains no fewer than 207 treatises, the most valuable part of all that Klaproth has done for chemistry and mineralogy. It is a pity that the sale of this work did not permit the publication of a 7th volume, which would have included the rest of his papers, which he had not collected, and given us a good index to the whole work, which would have been of great importance to the practical chemist. There is indeed an index to the first 5 volumes, but it is meager and defective, containing little else than the names of the substances on which his experiments were made. Besides his own works, the interest which he took in the labors of others deserves to be noticed. He superintended a new edition of Gren's Manual of Chemistry, remarkable not so much for what he added as for what he took away and corrected. The part which he took in Wolff's Chemical Dictionary was of great importance. The composition of every particular treatise was by Professor Wolff, but Klaproth read over every important article before it was printed, and assisted the editor on all occasions with the treasures of his experience and knowledge. Nor was he less useful to Fischer in his translation of Berthollet on affinity and on chemical statics. These meritorious services, and the luster which his character and discoveries conferred on his country, were duly appreciated by his sovereign. In 1782, he had been made assessor in the Supreme College of Medicine and of Health, which then existed. At a more recent period, he enjoyed the same rank in the Supreme Council of Medicine and of Health, and when this college was subverted, in 1810, he became a member of the medical deputation attached to the Ministry of the Interior. He was also a member of the Perpetual Court Commission for Medicines. His lectures, too, procured for him several municipal situations. As soon as the public became acquainted with his great chemical acquirements, he was permitted to give yearly 2 private courses of lectures on chemistry, one for the officers of the Royal Artillery Corps, the other for officers not connected with the army, who wished to accomplish themselves for some practical employment. Both of these lectures assumed afterwards a municipal character. The former led to his appointment as professor of the Artillery Academy instituted at Tempelhof, and after its dissolution to his situation as professor in the Royal War School. The other lecture procured for him the professorship of chemistry in the Royal Mining Institute. On the establishment of the university, Klaproth's lectures became those of the university, and he himself was appointed ordinary professor of chemistry and member of the academical senate. From 1797 to 1810, he was an active member of a small scientific society, which met yearly during a few weeks for the purpose of discussing the more recondite mysteries of the science. In the year 1811, the King of Prussia added to all his other honors the Order of the Red Eagle of the 3rd class. Klaproth spent the whole of a long life in the most active and conscientious discharge of all the duties of his station, and in an uninterrupted course of experimental investigations. He died at Berlin on the 1st of January, 1817, in the 70th year of his age. Among the remarkable traits in his character was his incorruptible regard for everything that he believed to be true, honorable, and good, his pure love of science, with no reference whatever to any selfish, ambitious, and avaricious feeling, his rare modesty, undebased by the slightest vainglory or boasting. He was benevolently disposed toward all men, and never did a slighting or contemptuous word respecting any person fall from him. When forced to blame, he did it briefly and without bitterness, for his blame always applied to actions, not to persons. His friendship was never the result of selfish calculation, but was founded on his opinion of the personal worth of the individual. Amidst all the unpleasant accidents of his life, which were far from few, he evinced the greatest firmness of mind. In his common behavior he was pleasant and composed, and was indeed rather inclined to a joke. To all this may be added a true religious feeling, so uncommon among men of science of his day. His religion consisted not in words and forms, not in positive doctrines, nor in ecclesiastical observances, which, however, he believed to be necessary and honorable, but in a zealous and conscientious discharge of all his duties, not only of those which are imposed by the laws of men, but of those holy duties of love and charity, which no human law, but only that of God, can command, and without which the most enlightened of men is but a sounding brass or a tinkling cymbal. He early showed this religious feeling by the honorable care which he bestowed on the education of the children of Valentine Rose, nor did he show less care at an after period toward his assistants and apprentices, to whom he refused no instruction, and in whose success he took the most active concern. He took a pleasure in everything that was good and excellent, and felt a lively interest in every undertaking which he believed to be of general utility. He was equally removed from the superstition and infidelity of his age, and carried the principles of religion not on his lips, but in the inmost feelings of his heart, from whence they emanated in actions which pervaded and ennobled his whole being and conduct. End of section 55. Section number 56 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas THOMSON, Volume 2, Chapter 4, Part 2. When we take a view of the benefits which Klaproth conferred upon chemistry, we must not look so much at the new elementary substances which he discovered, though they must not be forgotten, as at the new analytical methods which he introduced, the precision and neatness and order and regularity with which his analyses were conducted, and the scrupulous fidelity with which everything was faithfully stated as he found it. 1. When a mineral is subjected to analysis, whatever care we take to collect all the constituents and to weigh them without losing any portion whatever, it is generally found that the sum of the constituents obtained fall a little short of the weight of the mineral employed in the analysis. Thus, if we take 100 grains of any mineral and analyze it, the weights of all the constituents obtained added together will rarely make up 100 grains, but generally somewhat less, perhaps only 99 or even 98 grains. But some cases occur when the analysis of 100 grains of a mineral gives us constituents that weigh, when added together, more than 100 grains, perhaps 105, or in some rare cases as much as 110. It was the custom with Bergman and other analysts of his time to consider this deficiency or surplus as owing to errors in the analysis, and therefore to slur it over in the statement of the analysis, by bringing the weight of the constituents, by calculation, to amount exactly to 100 grains. Klaproth introduced the method of stating the results exactly as he got them. He gives the weight of mineral employed in all of his analyses, and the weight of each constituent extracted. These weights, added together, generally show a loss, varying from 2% to 0.5%. This improvement may appear, at first sight, trifling, yet I am persuaded that to it we are indebted for most of the subsequent improvements introduced into analytical chemistry. If the loss sustained was too great, it was obvious either that the analysis had been badly performed, or that the mineral contains some constituent which had been overlooked and not obtained. This laid him under the necessity of repeating the analysis, and if the loss continued, he naturally looked out for some constituent which his analysis had not enabled him to obtain. It was in this way that he discovered the presence of potash in minerals, and Dr. Kennedy afterwards, by following out his processes, discovered soda as a constituent. It was in this way that water, phosphoric acid, arsenic acid, fluoric acid, boracic acid, etc., were also found to exist as constituents in various mineral bodies, which, but for the accurate mode of notation introduced by Klaproth, would have been overlooked and neglected. 2. When Klaproth first began to analyze mineral bodies, he found it extremely difficult to bring them into a state capable of being dissolved in acids, without which an accurate analysis was impossible. Accordingly, corundum, adamantine spar, and the zircon or hyacinth baffled his attempts for a considerable time, and induced him to consider the earth of corundum as of a peculiar nature. He obviated this difficulty by reducing the mineral to an extremely fine powder, and, after digesting it in caustic potash ley till all the water was dissipated, raising the temperature and bringing the whole into a state of fusion. This fusion must be performed in a silver crucible. Corundum and every other mineral which had remained insoluble after fusion with an alkaline carbonate was found to yield to this new process. This was an improvement of considerable importance. All those stony minerals which contain a notable proportion of silica, in general become soluble after having been kept for some time in a state of ignition with twice their weight of carbonate of soda. At that temperature, the silica of the mineral unites with the soda, and the carbonic acid is expelled. But when the quantity of silica is small, or when it is totally absent, heating with carbonate of soda does not answer so well. With such minerals, caustic potash or soda may be substituted with advantage, and there are some of them that cannot be analyzed without having recourse to that agent. I have succeeded in analyzing corundum and chrysoberyl, neither of which, when pure, contain any silica, by simply heating them in carbonate of soda. But the process does not succeed unless the minerals be reduced to an exceedingly minute powder. 3. When Klaproth discovered potash in the idocrase and in some other minerals, it became obvious that the old mode of rendering minerals soluble in acids by heating them with caustic potash or an alkaline carbonate could answer only for determining the quantity of silica and of earths or oxides which the mineral contained, but that it could not be used when the object was to determine its potash. This led him to substitute carbonate of barytes instead of potash or soda or their carbonates. After having ascertained the quantity of silica and of earths and metallic oxides which the mineral contained, his last process to determine the potash in it was conducted in this way. A portion of the mineral reduced to a fine powder was mixed with 4 or 5 times its weight of carbonate of barytes and kept for some time in a platinum crucible in a red heat. By this process, the whole becomes soluble in muriatic acid. The muriatic acid solution is freed from silica and afterwards from barytes and all the earths and oxides which it contains, by means of carbonate of ammonia. The liquid, thus freed from everything but the alkali, which is held in solution by the muriatic acid, and the ammonia, used as a precipitant, is evaporated to dryness, and the dry mass, cautiously heated in a platinum crucible till the ammoniacal salts are driven off. Nothing now remains but the potash, or soda, in combination with muriatic acid. The addition of muriate of platinum enables us to determine whether the alkali be potash or soda. If it be potash, it occasions a yellow precipitate, but nothing falls if the alkali be soda. This method of analyzing minerals containing potash or soda is commonly ascribed to Rose. Fescher, in his elegy of Klaproth, informs us that Klaproth said to him, more than once, that he was not quite sure whether he himself or Rose had the greatest share in bringing this method to a state of perfection. From this, I think it not unlikely that the original suggestion might have been owing to Rose, but that it was Klaproth who first put it to the test of experiment. The objection to this mode of analyzing is the high price of the carbonate of barytes. This is partially obviated by recovering the barytes in the state of carbonate, and this, in general, may be done without much loss. Berthier has proposed to substitute oxide of lead for carbonate of barytes. It answers very well, is sufficiently cheap, and does not injure the crucible, provided the oxide of lead be mixed previously with a little nitrate of lead to oxidize any fragments of metallic lead which it may happen to contain. Berthier's mode, therefore, in point of cheapness, is preferable to that of Klaproth. It is equally efficacious and equally accurate. There are some other processes which I myself prefer to either of these, because I find them equally easy and still less expensive than either carbonate of barytes or oxide of lead. Davy's method with boracic acid is exceptionable on account of the difficulty of separating the boracic acid completely again. 4. The mode of separating iron and manganese from each other employed by Bergman was so defective that no confidence whatever can be placed in his results. Even the methods suggested by Vauquelin, though better, are still defective. But the process followed by Klaproth is susceptible of very great precision. He has, we shall suppose, the mixture of iron and manganese to be separated from each other in solution in muriatic acid. The first step of the process is to convert the protoxide of iron, should it be in that state, into peroxide. For this purpose, a little nitric acid is added to the solution, and the whole heated for some time. The liquid is now to be rendered as neutral as possible, first by driving off as much of the excess of acid as possible, by concentrating the liquid, and then by completing the neutralization, by adding very dilute ammonia, till no more can be added without occasioning a permanent precipitation. Into the liquid thus neutralized, succinate or benzoate of ammonia is dropped, as long as any precipitate appears. By this means, the whole peroxide of iron is thrown down in combination with succinic or benzoic acid, while the whole manganese remains in solution. The liquid being filtered, to separate the benzoate of iron, the manganese may now, if nothing else be in the liquid, be thrown down by an alkaline carbonate, or, if the liquid contain magnesia or any other earthy matter, by hydrosulphuret of ammonia, or chloride of lime. This process was the contrivance of Galen, but it was made known to the public by Klaproth, who ever after employed it in his analyses. Galen employed succinate of ammonia, but Heisinger afterwards showed that benzoate of ammonia might be substituted without any diminution of the accuracy of the separation. This last salt, being much cheaper than succinate of ammonia, answers better in this country. In Germany, the succinic acid is the cheaper of the two, and therefore the best. 5. But it was not by new processes alone that Klaproth improved the mode of analysis, though they were numerous and important. The improvements in the apparatus contributed not less essentially to the success of his experiments. When he had to do with very hard minerals, he employed a mortar of flint, or rather of agate. This mortar he, in the first place, analyzed to determine exactly the nature of the constituents. He then weighed it. When a very hard body is pounded in such a mortar, a portion of the mortar is rubbed off and mixed with the pounded mineral. What the quantity thus abraded was, he determined by weighing the mortar at the end of the process. The loss of weight gave the portion of the mortar abraded, and this portion must be mixed with the pounded mineral. When a hard stone is pounded in an agate mortar, it is scarcely possible to avoid losing a little of it. The best method of proceeding is to mix the matter to be pounded, previously reduced to a coarse powder in a diamond mortar, with a little water. This both facilitates the trituration and prevents any of the dust from flying away, and not more than a couple of grains of the mineral should be pounded at once. Still, owing to very obvious causes, a little of the mineral is sure to be lost during the pounding. When the process is finished, the whole powder is to be exposed to a red heat in a platinum crucible and weighed. Supposing no loss, the weight should be equal to the quantity of the mineral pounded, together with the portion abraded from the mortar. But almost always the weight will be found less than this. Suppose the original weight of the mineral before pounding was A, and the quantity abraded from the mortar 1. Then if nothing were lost, the weight should be A plus 1. But we actually find it only B, a quantity less than A plus 1. To determine the weight of matter abraded from the mortar contained in this powder, we say the ratio of A plus 1 to B is proportional to the ratio of 1 to X, the quantity from the mortar in our powder, and X equal B divided by A plus 1. In performing the analysis, Klaproth attended to this quantity, which was silica, and subtracted it. Such minute attention may appear, at first sight, superfluous, but it is not so. In analyzing sapphire, chrysoberyl, and some other very hard minerals, the quantity of silica abraded from the mortar sometimes amounts to 5% of the weight of the mineral, and if we were not to attend to the way in which this silica has been introduced into the powder, we should give an erroneous view of the constitution of the mineral under analysis. All the analyses of chrysoberyl hitherto published give a considerable quantity of silica as a constituent of it. This silica, if really found by the analyst, must have been introduced from the mortar, for pure chrysoberyl contains no silica whatever, but is a definite compound of glucina, alumina, and oxide of iron. When Klaproth operated with fire, he always selected his vessels, whether of earthenware, glass, plumbago, iron, silver, or platinum, upon fixed principles, and showed more distinctly than chemists had previously been aware of what an effect the vessel frequently has upon the result. He also prepared his reagents with great care to ensure their purity, for obtaining several of which in their most perfect state, he invented several efficient methods. It is to the extreme care with which he selected his minerals for analysis, and to the purity of his reagents, and the fitness of his vessels for the objects in view, that the great accuracy of his analyses is to be, in a great measure, ascribed. He must also have possessed considerable dexterity in operating, for when he had in view to determine any particular point with accuracy, his results came, in general, exceedingly near the truth. I may notice, as an example of this, his analysis of sulfate of barytes, which was within about 1.5% of absolute correctness. When we consider the looseness of the data which chemists were then obliged to use, we cannot but be surprised at the smallness of the error. Berzelius, in possession of better data, and possessed of much dexterity and a good apparatus, when he analyzed this salt many years afterwards, committed an error of 0.5%. Klaproth, during a very laborious life, wholly devoted to analytical chemistry, entirely altered the face of mineralogy. When he began his labors, chemists were not acquainted with the true composition of a single mineral. He analyzed above 200 species, and the greater number of them with so much accuracy that his successors have, in most cases, confirmed the results which he obtained. The analyses least to be depended on are those of minerals which contain both lime and magnesia, for his process for separating lime and magnesia from each other was not a good one. Nor am I sure that he always succeeded completely in separating silica and magnesia from each other. This branch of analysis was first properly elucidated by Mr. Chenevix. 6. Analytical chemistry was, in fact, systematized by Klaproth, and it is by studying his numerous and varied analyses that modern chemists have learned this very essential but somewhat difficult art, and have been able, by means of still more accurate data than he possessed, to bring it to a still greater degree of perfection. But it must not be forgotten that Klaproth was in reality the creator of this art, and that on that account the greatest part of the credit due to the progress that has been made in it belongs to him. It would be invidious to point out the particular analyses which are least exact. Perhaps they ought rather to be ascribed to an unfortunate selection of specimens, than to any want of care or skill in the operator. But during his analytical processes, he discovered a variety of new elementary substances, which it may be proper to enumerate. In 1789, he examined a mineral called pitchblende, and found in it the oxide of a new metal, to which he gave the name of uranium. He determined its characters, reduced it to the metallic state, and described its properties. It was afterwards examined by Richter, Buchholz, Arfvedson, and Berzelius. It was in the same year, 1789, that he published his analysis of the zircon. He showed it to be a compound of silica and a new earth, to which he gave the name of zirconia. He determined the properties of this new earth, and showed how it might be separated from other bodies and obtained in a state of purity. It has been since ascertained that it is a metallic oxide, and the metallic basis of it is now distinguished by the name of zirconium. In 1795, he showed that the hyacinth is composed of the same ingredients as the zircon, and that both, in fact, constitute only one species. This last analysis was repeated by Morveau, and has been often confirmed by modern analytical chemists. It was in 1795 that he analyzed what was at that time called red schorl, and now titanite. He showed that it was the oxide of a new metallic body, to which he gave the name of titanium. He described the properties of this new body, and pointed out its distinctive characters. It must not be omitted, however, that he did not succeed in obtaining oxide of titanium, or titanic acid, as it is now called, in a state of purity. He was not able to separate a quantity of oxide of iron with which it was united, and which gave it a reddish color. It was first obtained pure by H. Rose, the son of his friend and pupil, who took so considerable a part in his scientific investigations. Titanium in the metallic state was some years ago discovered by Dr. Wollaston in the slag at the bottom of the iron furnace at Merthyr Tydvil in Wales. It is a yellow-colored, brittle, but very hard metal, possessed of considerable beauty, but not yet applied to any useful purpose. In 1797 he examined the menachanite, a black sand from Cornwall, which had been subjected to a chemical analysis by Grognor in 1791, who had extracted from it a new metallic substance, which Kirwan distinguished by the name of menachine. Klaproth ascertained that the new metal of Grognor was the very same as his own titanium, and that menachanite is a compound of titanic acid and oxide of iron. Thus Mr. Grognor had anticipated him in the discovery of titanium, though he was not aware of the circumstance till 2 years after his own experiments had been published. In the year 1793 he published a comparative set of experiments on the nature of carbonates of barytes and strontian, showing that their bases are 2 different earths, and not the same, as had been hitherto supposed in Germany. This was the first publication on strontian which appeared on the continent, and Klaproth seems to have been ignorant of what had already been done on it in Great Britain. At least, he takes no notice of it in his paper, and it was not his character to slur over the labors of other chemists, when they were known to him. Strontian was first mentioned as a peculiar earth by Dr. Crawford in his paper on the medicinal properties of the muriate of barytes, published in 1790. The experiments on which he founded his opinions were made, he informs us, by Mr. Cruikshanks. A paper on the same subject by Dr. Hope was read to the Royal Society of Edinburgh in 1793, but they had been begun in 1791. In this paper, Dr. Hope establishes the peculiar characters of strontian and describes its salts with much precision. Klaproth had been again anticipated in his experiments on strontian, but he could not have become aware of this till afterwards, for his own experiments were given to the public before those of Dr. Hope. On the 25th of January, 1798, his paper on the gold ores of Transylvania was read at a meeting of the Academy of Sciences at Berlin. During his analysis of these ores, he detected a new white metal, to which he gave the name of tellurium. Of this metal, he describes the properties and points out its distinguishing characters. These ores had been examined by Miller of Richtenstein in the year 1782, and he had extracted from them a metal which he considered as differing from every other. Not putting full confidence in his own skill, he sent a specimen of his new metal to Bergman, requesting him to examine it and give his opinion respecting its nature. All that Bergman did was to show that the metallic body which he had got was not antimony, to which alone of all known metals it bore any resemblance. It might be inferred from this that Miller's metal was new, but the subject was lost sight of till the publication of Klaproth's experiments in 1802 recalled it to the recollection of chemists. Indeed, Klaproth relates all that Miller had done with the most perfect fairness. In the year 1804, he published the analysis of a red-colored mineral from Bosnas in Sweden, which had been at one time confounded with tungsten, but which the Elwarts had shown to contain none of that metal. Klaproth showed that it contained a new substance as one of its constituents, which he considered as a new earth, and which he called ochroita, because it forms colored salts with acids. 2 years after, another analysis of the same mineral was published by Berzelius and Heisinger. They considered the new substance which the mineral contained as a metallic oxide, and to the unknown metallic base they gave the name of cerium, which has been adopted by chemists in preference to Klaproth's name. The characters of oxide of cerium given by Berzelius and Heisinger agree with those given by Klaproth to ochroita in all the essential circumstances. Of course, Klaproth must be considered as the discoverer of this new body. The distinction between earth and metallic oxide is now known to be an imaginary one. All the substances formerly called earths are, in fact, metallic oxides. Besides these new substances, which he detected by his own labors, He repeated the analyses of others, and confirmed and extended the discoveries they had made. Thus, when Vauquelin discovered the new earth glucina in the emerald and beryl, he repeated the analysis of these minerals, confirmed the discovery of Vauquelin, and gave a detailed account of the characters and properties of glucina. Gadolin had discovered another new earth in the mineral called gadolinite. This discovery was confirmed by the analysis of Ekberg, who distinguished the new earth by the name of yttria. Klaproth immediately repeated the analysis of the gadolinite, confirmed the results of Ekberg's analysis, and examined and described the properties of yttria. End of section 56. Section 57 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas THOMSON. Volume 2, Chapter 4, Part 3. When Dr. Kennedy discovered soda in basalt, Klaproth repeated the analysis of this mineral and confirmed the results obtained by the Edinburgh analyst. But it would occupy too much room if I were to enumerate every example of such conduct. Whoever will take the trouble to examine the different volumes of the Beiträge will find several others not less striking or less useful. The service which Klaproth performed for mineralogy in Germany was performed equally in France by the important labors of M. Vauquelin. It was in France, in consequence of the exertions of Romain de Lisle and the mathematical investigations of the Abbé Hauy respecting the structure of crystals, which were gradually extended over the whole mineral kingdom, that the reform in mineralogy, which has now become in some measure general, originated. Hauy laid it down as a first principle that every mineral species is composed of the same constituents, united in the same proportion. He therefore considered it as an object of great importance to procure an exact chemical analysis of every mineral species. Hitherto no exact analysis of minerals had been performed by French chemists, for Sage, who was the chemical mineralogist connected with the Academy, satisfied himself with ascertaining the nature of the constituents of minerals without determining their proportions. But Vauquelin soon displayed a knowledge of the mode of analysis and a dexterity in the use of the apparatus which he employed, little less remarkable than that of Klaproth himself. Of Vauquelin's history I can give but a very imperfect account, as I have not yet had an opportunity of seeing any particulars of his life. He was a peasant boy of Normandy, with whom Fourcroy accidentally met. He was pleased with his quickness and parts, and delighted with the honesty and integrity of his character. He took him with him to Paris, and gave him the superintendence of his laboratory. His chemical knowledge speedily became great, and his practice in experimenting gave him skill and dexterity. He seems to have performed all the analytical experiments which Fourcroy was in the habit of publishing. He speedily became known by his publications and discoveries. When the scientific institutions were restored or established after the death of Robespierre, Vauquelin became a member of the Institute and chemist to the School of Mines. He was made also assay master of the Mint. He was a professor of chemistry in Paris, and delivered likewise private lectures, and took in practical pupils into his laboratory. His laboratory was of considerable size, and he was in the habit of preparing both medicines and chemical reagents for sale. It was he chiefly that supplied the French chemists with phosphorus, etc., which cannot be conveniently prepared in a laboratory fitted up solely for scientific purposes. Vauquelin was by far the most industrious of all the French chemists, and has published more papers, consisting of mineral, vegetable, and animal analyses, than any other chemist without exception. When he had the charge of the laboratory of the School of Mines, Hauy was in the habit of giving him specimens of all the different minerals which he wished analyzed. The analyses were conducted with consummate skill, and we owe to him a great number of improvements in the methods of analysis. He is not entitled to the same credit as Klaproth, because he had the advantage of many analyses of Klaproth to serve him as a guide, but he had no model before him in France, and both the apparatus used by him and the reagents which he employed were of his own contrivance and preparation. I have sometimes suspected that his reagents were not always very pure, but I believe the true reason of the unsatisfactory nature of many of his analyses is the bad choice made of the specimens selected for analysis. It is obvious from his papers that Vauquelin was not a mineralogist, for he never attempts a description of the mineral which he subjects to analysis, satisfying himself with the specimen put into his hands by Availle. Where that specimen was pure, as was the case with emerald and beryl, his analysis is very good. But when the specimen was impure or ill-chosen, then the result obtained could not convey a just notion of the constituents of the mineral. That Availle would not be very difficult to please in his selection of specimens, I think myself entitled to infer from the specimens of minerals contained in his own cabinet, many of which were by no means well selected. I think, therefore, that the numerous analyses published by Vauquelin, in which the constituents assigned by him are not those, or at least not in the same proportions as have been found by succeeding analysts, are to be ascribed not to errors in the analysis, which, on the contrary, he always performed carefully and with the requisite attention to precision, but to the bad selection of specimens put into his hand by Availle, or those other individuals who furnished him with the specimens which he employed in his analyses. This circumstance is very much to be deplored, because it puts it out of our power to confide in the analysis of Vauquelin, till it has been repeated and confirmed by somebody else. Vauquelin not only improved the analytical methods and reduced the art to a greater degree of simplicity and precision, but he discovered likewise new elementary bodies. The red lead ore of Siberia had early drawn the attention of chemists on account of its beauty, and various attempts had been made to analyze it. Among others, Vauquelin tried his skill upon it in 1789 in concert with M. Marquardt, who had brought specimens of it from Siberia, but at that time he did not succeed in determining the nature of the acid with which the oxide of lead was combined in it. He examined it again in 1797, and now succeeded in separating an acid to which, from the beautiful colored salts which it forms, he gave the name of chromic. He determined the properties of this acid, and showed that its basis was a new metal to which he gave the name of chromium. He succeeded in obtaining this metal in a separate state, and showed that its protoxide is an exceedingly beautiful green powder. This discovery has been of great importance to the different branches of manufacture in this country. The green oxide is used pretty extensively in painting green on porcelain. It constitutes an exceedingly beautiful green pigment, very permanent and easily applied. The chromic acid, when combined with oxide of lead, forms either a yellow or an orange color upon cotton cloth, both very fixed and exceedingly beautiful colors. In that way, it is extensively used by the calico printers, and the bichromate of potash is prepared, in a crystalline form, to a very considerable amount, both in Glasgow and Lancashire, and doubtless in other places. Vauquelin was requested by Availle to analyze the beryl, a beautiful light green mineral, crystallized in six-sided prisms, which occurs not unfrequently in granite rocks, especially in Siberia. He found it to consist chiefly of silica, united to alumina, and to another earthly body, very like alumina in many of its properties, but differing in others. To this new earth he gave the name of glucina, on account of the sweet taste of its salts, a name not very appropriate, as alumina, yttria, lead, protoxide of chromium, and even protoxide of iron form salts which are distinguished by a sweet taste likewise. This discovery of glucina confers honor on Vauquelin, as it shows the care with which his analysis must have been conducted. A careless experimenter might easily have confounded glucina with alumina, Vauquelin's mode of distinguishing them was to add sulfate of potash to their solution in sulfuric acid. If the earth in solution was alumina, crystals of alum would form in the course of a short time, but if the earth was glucina, no such crystals would make their appearance, alumina being the basis of alum and not glucina. He showed, too, that glucina is easily dissolved in a solution of carbonate of ammonia, while alumina is not sensibly taken up by that solution. Vauquelin died in 1829 after having reached a good old age. His character was of the very best kind, and his conduct had always been most exemplary. He never interfered with politics, and steered his way through the bloody period of the Revolution, uncontaminated by the vices or violence of any party, and respected and esteemed by every person. Mr. Chenevix deserves also to be mentioned as an improver of analytical chemistry. He was an Irish gentleman who happened to be in Paris during the Reign of Terror, and was thrown into prison and put into the same apartment with several French chemists, whose whole conversation turned upon chemical subjects. He caught the infection, and, after getting out of prison, began to study the subject with much energy and success, and soon distinguished himself as an analytical chemist. His analysis of corundum and sapphire, and his observations on the affinity between magnesia and silica are valuable, and led to considerable improvements in the method of analysis. His analyses of the arseniates of copper, though he demonstrated that several species exist, are not so much to be depended on, because his method of separating and estimating the quantity of arsenic acid is not good. This difficult branch of analysis was not fully understood till afterwards. Chenevix was, for several years, a most laborious and meritorious chemical experimenter. It is much to be regretted that he should have been induced, in consequence of the mistake into which he fell respecting palladium, to abandon chemistry altogether. Palladium was originally made known to the public by an anonymous handbill which was circulated in London, announcing that palladium, or new silver, was on sale at Mrs. Forster's, and describing its properties. Chenevix, in consequence of the unusual way in which the discovery was announced, naturally considered it as an imposition on the public. He went to Mrs. Forster's and purchased the whole palladium in her possession, and set about examining it, prepossessed with the idea that it was an alloy of some 2 known metals. After a laborious set of experiments, he considered that he had ascertained it to be a compound of platinum and mercury, or an amalgam of platinum, made in a peculiar way, which he describes. This paper was read at a meeting of the Royal Society by Dr. Wollaston, who was secretary, and afterwards published in their Transactions. Soon after this publication, another anonymous handbill was circulated, offering a considerable price for every grain of palladium made by Mr. Chenevix's process, or by any other process whatever. No person appearing to claim the money thus offered, Dr. Wollaston, about a year after, in a paper read to the Royal Society, acknowledged himself to have been the discoverer of palladium, and related the process by which he had obtained it from the solution of crude platina in aqua regia. There could be no doubt after this that palladium was a peculiar metal, and that Chenevix, in his experiments, had fallen into some mistake, probably by inadvertently employing a solution of palladium instead of a solution of his amalgam of platinum, and thus giving the properties of the one solution to the other. It is very much to be regretted that Dr. Wollaston allowed Mr. Chenevix's paper to be printed without informing him in the first place of the true history of palladium, and I think that if he had been aware of the bad consequences that were to follow, and that it would ultimately occasion the loss of Mr. Chenevix to the science, he would have acted in a different manner. I have more than once conversed with Dr. Wollaston on the subject, and he assured me that he did everything he could do, short of betraying his secret, to prevent Mr. Chenevix from publishing his paper, that he had called upon and assured him that he himself had attempted his process without being able to succeed, and that he was satisfied that he had fallen into some mistake. As Mr. Chenevix still persisted in his conviction of the accuracy of his own experiments after repeated warnings, perhaps it is not very surprising that Dr. Wollaston allowed him to publish his paper, though. Had he been aware of the consequences to their full extent, I am persuaded that he would not have done so. It comes to be a question whether, had Dr. Wollaston informed him of the whole secret, Mr. Chenevix would have been convinced. Another chemist to whom the art of analyzing minerals lies under great obligations is Dr. Frederick Stromeyer, professor of chemistry and pharmacy in the University of Göttingen. He was originally a botanist, and only turned his attention to chemistry when he had the offer of the chemical chair at Göttingen. Then he went to Paris and studied practical chemistry for some years in Vauquelin's laboratory. He has devoted most of his attention to the analysis of minerals, and in the year 1821 published a volume of analyses under the title of Untersuchungen über die Mischung der Mineralkörper und anderer damit verwandten Substanzen. It contains 30 analyses which constitute perfect models of analytical sagacity and accuracy. After Klaproth's Betrage, no book can be named more highly deserving the study of the analytical chemist than Stromeyer's Untersuchungen. The first paper in this work contains the analysis of aragonite. Chemists had not been able to discover any difference in the chemical constitution of aragonite and calcareous spar, both being compounds of lime, 3.5, and carbonic acid, 2.75. Yet the minerals differ from each other in their hardness, specific gravity, and in the shape of their crystals. Many attempts had been made to account for this difference in characters between these two minerals, but in vain. Mr. Holmes showed that aragonite contained about 1% of water, which is wanting in calcareous spar, and that when aragonite is heated, it crumbles into powder, which is not the case with calcareous spar. But it is not easy to conceive how the addition of 1% of water should increase the specific gravity and the hardness, and quite alter the shape of the crystals of calcareous spar. Stromeyer made a vast number of experiments upon aragonite with very great care, and the result was that the aragonite from Bastines near Dax in the department of Landes, and likewise that from Molina in Aragon, was a compound of 96 carbonate of lime, 4 carbonate of strontian. This amounts to about 35 atoms of carbonate of lime and 1 atom of carbonate of strontian. Now, as the hardness and specific gravity of carbonate of strontian is greater than that of carbonate of lime, we can see a reason why aragonite should be heavier and harder than calcareous spar. More late researches upon different varieties of aragonite enabled him to ascertain that this mineral exists with different proportions of carbonate of strontian. Some varieties contain only 2%, some only 1%, and some only 0.75 or even 0.5%. But he found no specimen among the great number which he analyzed totally destitute of carbonate of strontian. It is true that Vauquelin afterwards examined several varieties in which he could detect no strontian whatever, but as Vauquelin's mineralogical knowledge was very deficient, it comes to be a question whether the minerals analyzed by him were really aragonites or only varieties of the calcareous spar. To Professor Stromeyer we are likewise indebted for the discovery of the new metal called cadmium, and the discovery does great credit to his sagacity and analytical skill. He is Inspector General of the Apothecaries for the Kingdom of Hanover. While discharging the duties of his office at Hildesheim in the year 1817, he found that the carbonate of zinc had been substituted for the oxide of zinc, ordered in the Hanoverian Pharmacopoeia. This carbonate of zinc was manufactured at Salzgitter. On inquiry, he learned from Mr. Jost, who managed that manufactory, that they had been obliged to substitute the carbonate for the oxide of zinc, because the oxide had a yellow color which rendered it unsaleable. On examining this oxide, Stromeyer found that it owed its yellow color to the presence of a small quantity of the oxide of a new metal, which he separated, reduced, and examined, and to which he gave the name of cadmium, because it occurs usually associated with zinc. The quantity of cadmium which he was able to obtain from this oxide of zinc was but small. A fortunate circumstance, however, supplied him with an additional quantity, and enabled him to carry his examination of cadmium to a still greater length. During the apothecary's visitation in the state of Magdeburg, there was found, in the possession of several apothecaries, a preparation of zinc from Silesia, made in Hermann's laboratory at Schönebeck, which was confiscated on the supposition that it contained arsenic, because its solution gave a yellow precipitate with sulphuretted hydrogen, which was considered an orpiment. This statement could not be indifferent to Mr. Hermann, as it affected the credit of his manufactory, especially as the medicinal counselor, Roloff, who had assisted at the visitation, had drawn up a statement of the circumstances which occasioned the confiscation and caused it to be published in Holofen's medical journal. He subjected the suspected oxide to a careful examination, but he could not succeed in detecting any arsenic in it. He then requested Roloff to repeat his experiments. This he did, and now perceived that the precipitate, which he had taken for an orpiment, was not so in reality, but owed its existence to the presence of another metallic oxide, different from arsenic, and probably new. Specimens of this oxide of zinc and of the yellow precipitate were sent to Strohmeyer for examination, who readily recognized the presence of cadmium, and was able to extract from it a considerable quantity of that metal. End of section 57. Section number 58 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 4, Part 4. It is now 9 years since the first volume of the Untersuchungen was published. All those who are interested in analytical chemistry are anxious for the continuance of that admirable work. By this time, he must have collected ample materials for an additional volume, and it could not but add considerably to a reputation already deservedly high. There is no living chemist to whom analytical chemistry lies under greater obligations than to Berzelius, whether we consider the number or the exactness of the analyses which he has made. Jacob Berzelius was educated at Uppsala, when Professor Afzelius, a nephew of Bergman, filled the chemical chair, and Ekberg was magister docens in chemistry. Afzelius began his chemical career with considerable éclat, his paper on sulfate of barytes being possessed of very considerable merit. But he is said to have soon lost his health, and to have sunk, in consequence, into listless inactivity. Andrew Gustavus Ekberg was born in Stockholm on the 16th of January, 1767. His father was a captain in the Swedish Navy. He was educated at Kalmar, and in 1784 went to Uppsala, where he devoted himself chiefly to the study of mathematics. He took his degree in 1788, when he wrote a thesis De Olieis Seminum Expressis. In 1789 he went to Berlin, and on his return in 1790 he gave a specimen of his poetical talents by publishing a poem entitled Tal over Freden emellan Sverige och Ryssland, Discourse about the peace between Sweden and Russia. After this he turned his attention to chemistry, and in 1794 was made chemiae docens. In this situation he continued till 1813, when he died on the 11th of February. He had been in such bad health for some time before his death as to be quite unable to discharge the duties of his situation. He published but little, and that little consisted almost entirely of chemical analyses. His first attempt was on phosphate of lime. Then he wrote a paper on the analysis of the topaz, the object of which was to explain Klaproth's method of dissolving hard stony bodies. He made an analysis of gadolinite, and determined the chemical properties of yttria. During these experiments, he discovered the new metal to which he gave the name of tantalum, and which Dr. Wollaston afterwards showed to be the same with the columbium of Mr. Hatchett. He also published an analysis of the automolite, of an ore of titanium, and of the mineral water of Medivh. In this last analysis, he was assisted by Berzelius, who was then quite unknown to the chemical world. Berzelius has been much more industrious than his chemical contemporaries at Uppsala. His first publication was a work in 2 volumes on animal chemistry, chiefly a compilation, with the exception of his experiments on the analysis of blood, which constitute an introduction to the second volume. This book was published in 1806 and 1808. In the year 1806, he and Heisinger began a periodical work entitled Afhandlinger i Fysik, Chemie och Mineralogie, of which 6 volumes in all were published, the last in 1818. In this work there occur 47 papers by Berzelius, some of them of great length and importance, which will be noticed afterwards, but by far the greatest part of them consist of mineral analyses. We have the analysis of cerium by Heisinger and Berzelius, together with an account of the chemical characters of the 2 oxides of cerium. In the 4th volume, he gives us a new chemical arrangement of minerals, founded on the supposition that they are all chemical compounds in definite proportions. Mr. Smithson had thrown out the opinion that silica is an acid, which opinion was taken up by Berzelius, who showed, by decisive experiments, that it enters into definite combinations with most of the bases. This happy idea enabled him to show that most of the stony minerals are definite compounds of silica, with certain earths or metallic oxides. This system has undergone several modifications since he first gave it to the world, and I think it more than doubtful whether his last correction of it, published in the Memoirs of the Stockholm Academy for 1824, be quite as good as the first, which he published in 1815. The first arrangement was founded on the bases, the last upon the acids with which the bases are united. He was induced to alter his arrangement in consequence of Mitscherlich's doctrine of isomorphism. But I conceive that the alterations which exist in the constitution of pyroxene, amphibole, garnet, and a few other minerals might be explained in a very simple way without admitting this doctrine of isomorphism, which, if it do not, like Berthollet's hypothesis of indefinite combinations, overturn the whole principles of chemistry, seems scarcely consistent with what we know respecting chemical combination. In the same volume, we have a set of experiments on columbium and its characters when reduced to the metallic state, together with an analysis of all the minerals containing columbium that were known in the year 1815. We have also a new examination of the properties of yttria, together with the analysis of a number of minerals containing both cerium and yttria, and the mode of separating these 2 substances from each other by means of sulfate of potash. In the 6th volume, we have his discovery of selenium, with an account of selenic acid and the different compounds which it forms. Since the year 1818, his papers have been all published in the Memoirs of the Stockholm Academy, but he has taken care to have translations of them inserted into Pogensdorf's Annalen and the Annales de Chimie et de Physique. In the Stockholm Memoirs for 1819, we have his analysis of wavellite, showing that this mineral is a hydrous phosphate of alumina. The same analysis and discovery had been made by Fuchs, who published his results in 1818, but probably Berzelius had not seen the paper. At least he takes no notice of it. We have also in the same volume his analysis of euclase, of silicate of zinc, and his paper on the prussiates. In the Memoirs for 1820, we have, besides 3 others, his paper on the mode of analyzing the ores of nickel. In the Memoirs for 1821, we have his paper on the alkaline sulfurates, and his analysis of achmite. The specimen selected for this analysis was probably impure, for 2 successive analyses of it, made in my laboratory by Captain LeHunt, gave a considerable difference in the proportion of the constituents, and a different formula for the composition than that resulting from the constituents found by Berzelius. In the Memoirs for 1822, we have his analysis of the mineral waters of Carlsbad. In 1823, he published his experiments on uranium, which were meant as a confirmation and extension of the examination of this substance previously made by Arvidsson. In the same year appeared his experiments on fluoric acid and its combinations, constituting one of the most curious and important of all the numerous additions which he has made to analytical chemistry. In 1824, we have his analysis of phosphate of yttria, a mineral found in Norway; of poligmonite, a mineral from the neighborhood of Christiania, where it occurs in the zircon syenite, and remarkable for the great number of bases which it contains united to titanic acid, namely zirconia, oxide of iron, lime, oxide of manganese, oxide of cerium, and yttria. We have also his analysis of arseniate of iron, from Brazil and from Cornwall, and of chabasite from Ferro. In this last analysis he mentions chabasites from Scotland, containing soda instead of lime. The only chabasites in Scotland that I know of occur in the neighborhood of Glasgow, and in none of these have I found any soda. But I have found soda instead of lime in chabasites from the north of Ireland, always crystallized in the form to which Hauy has given the name of trirhomboidal. I think, therefore, that the chabasites analyzed by Arvidsson, to which Berzelius refers, must have been from Ireland and not from Scotland, and I think it may be a question whether this form of crystal, if it should always be found to contain soda instead of lime, ought not to constitute a peculiar species. In 1826, we have his very elaborate and valuable paper on sulfur salts. In this paper, he shows that sulfur is capable of combining with bodies in the same way as oxygen, and of converting the acidifiable bases into acids and the alkalifiable bases into alkalis. These sulfur acids and alkalis unite with each other and form a new class of saline bodies, which may be distinguished by the name of sulfur salts. This subject has been since carried a good deal further by M.H. Rose, who has by means of it thrown much light on some mineral species hitherto quite inexplicable. Thus, what is called nickel glance is a sulfur salt of nickel. The acid is a compound of sulfur and arsenic, the base a compound of sulfur and nickel. Its composition may be represented thus: 1 atom disulfide of arsenic, 1 atom disulfide of nickel. In like manner, glance cobalt is 1 atom disulfide of arsenic, 1 atom disulfide of nickel. Zinconite is composed of 3 atoms sulfide of antimony, 1 atom sulfide of lead, and jamesonite of 2½ atoms sulfide of antimony, 1 atom sulfide of lead. Feather ore of antimony, hitherto confounded with sulphuret of antimony, is a compound of 5 atoms sulfide of antimony, 3 atoms sulfide of lead. Gray copper ore, which has hitherto appeared so difficult to be reduced to anything like regularity, is composed of 1 atom sulfide of antimony or arsenic, 2 atoms sulfide of copper or silver. Dark red silver ore is composed of 1 atom sulfide of antimony, 1 atom sulfide of silver, and light red silver ore of 2 atoms sesquisulfide of arsenic, 3 atoms sulfide of silver. These specimens show how much light the doctrine of sulfur salts has thrown on the mineral kingdom. In 1828, he published his experimental investigation of the characters and compounds of palladium, rhodium, osmium, and iridium, and upon the mode of analyzing the different ores of platinum. One of the greatest improvements which Berzelius has introduced into analytical chemistry is his mode of separating those bodies which become acid when united to oxygen, as sulfur, selenium, arsenic, etc., from those that become alkaline, as copper, lead, silver, etc. His method is to put the alloy or ore to be analyzed into a glass tube and to pass over it a current of dry chlorine gas, while the powder in the tube is heated by lamp. The acidifiable bodies are volatile and pass over along the tube into a vessel of water placed to receive them, while the alkalifiable bodies remain fixed in the tube. This mode of analysis has been considerably improved by Rose, who availed himself of it in his analysis of gray copper ore and other similar compounds. Analytical chemistry lies under obligations to Berzelius, not merely for what he has done himself, but for what has been done by those pupils who were educated in his laboratory. Bonsdorf, Nordenskjöld, C.G. Gmelin, Rose, Wohler, Arvidsson have given us some of the finest examples of analytical investigations with which the science is furnished. P.A. von Bonsdorf was a professor of Abo, and after that university was burnt down, he moved to the new locality in which it was planted by the Russian government. His analysis of the minerals which crystallize in the form of the amphibole constitutes a model for the young analyst to study. Whether we consider the precision of the analyses or the methods by which the different constituents were separated and estimated. His analysis of red silver ore first demonstrated that the metals in it were not in the state of oxides. The nature of the combination was first completely explained by Rose after Berzelius's paper on the sulfur salts had made its appearance. His paper on the acid properties of several of the chlorides has served considerably to extend and to rectify the views first proposed by Berzelius respecting the different classes of salts. Niels Nordenskjöld is superintendent of the mines in Finland. His Bidrag till närmare kännedom of Finlands mineralia och geonosi was published in 1820. It contains a description and analysis of 14 species of Lapland minerals, several of them new and all of them interesting. The analyses were conducted in Berzelius's laboratory and are excellent. In 1827, he published a tabular view of the mineral species, arranged chemically, in which he gives the crystalline form, hardness, and specific gravity, together with the chemical formulas for the composition. C.G. Gmelin is professor of chemistry at Tübingen. He has devoted the whole of his attention to chemical analysis and has published a great number of excellent ones, particularly in Schweiger's journal. His analysis of helvine and of the tourmaline may be specified as particularly valuable. In this last mineral, he demonstrated the presence of boracic acid. Leopold Gmelin, professor of chemistry at Heidelberg, has also distinguished himself as an analytical chemist. His System of Chemistry, which is at present publishing, promises to be the best and most perfect which Germany has produced. Henry Rose, of Berlin, is the son of that M. Rose who was educated by Klaproth, and afterwards became the intimate friend and fellow laborer of that illustrious chemist. He has devoted himself to analytical chemistry with indefatigable zeal, and has favored us with a prodigious number of new and admirably conducted analyses. His analyses of pyroxenes, of the ores of titanium, of gray copper ore, of silver glance, of red silver ore, miragerite, polybasite, etc., may be mentioned as examples. In 1829, he published a volume on analytical chemistry, which is by far the most complete and valuable work of the kind that has hitherto appeared, and ought to be carefully studied by all those who wish to make themselves masters of the difficult but necessary art of analyzing compound bodies. Wohler is professor of chemistry in the Polytechnic School of Berlin. He does not appear to have turned his attention to analytical chemistry, but rather towards extending our knowledge of the compounds which the different simple bodies are capable of forming with each other. His discovery of cyanic acid may be mentioned as a specimen. He is active and young, Much, therefore, may be expected from him. Augustus Arvidsson has distinguished himself by the discovery of the new fixed alkali, lithia, in petalite and spodumene. It has been lately ascertained at Moscow by M.R. Hermann, and the experiments have been repeated and confirmed by Berzelius, that lithia is a much lighter substance than it was found to be by Arvidsson, its atomic weight being only 1.75. We have from Arvidsson an important set of experiments on uranium and its oxides, and on the action of hydrogen on the metallic sulfurets. He has likewise analyzed a considerable number of minerals with great care, but of late years he seems to have lost his activity. His analysis of chrysoberyl does not possess the accuracy of the rest. By some inadvertence, he has taken a compound of glucina and alumina for silica. I ought to have included Walmstedt and Trolle Walkmeister among the Swedish chemists who have contributed important papers towards the progress of analytical chemistry, the memoirs of the former on chrysolite and of the latter on the garnets being peculiarly valuable. But it would extend this work to an almost interminable length if I were to particularize every meritorious experimenter. This must plead my excuse for having omitted the names of Buchholz, Galen, Fuchs, Dumasnil, Dobreiner, Kupfer, and various other meritorious chemists who have contributed so much to the perfecting of the chemical analysis of the mineral kingdom. But it would be unpardonable to leave out the name of M. Mechterlich, professor of chemistry in Berlin, and successor of Klaproth, who was also a pupil of Berzelius. He has opened a new branch of chemistry to our consideration. His papers on isomorphous bodies, on the crystalline forms of various sets of salts, on the artificial formation of various minerals, do him immortal honor, and will hand him down to posterity as a fit successor of his illustrious predecessors in the chemical chair of Berlin, a city in which an uninterrupted series of first-rate chemists have followed each other for more than a century, and where, thanks to the fostering care of the Prussian government, the number was never greater than at the present moment. The most eminent analytical chemists at present in France are Laugier, a nephew and successor of Fourcroy, as professor of chemistry in the Jardin du Roi, and Berthier, who has long had the superintendence of the laboratory of the School of Mines. Laugier has not published many analyses to the world, but those with which he has favored us appear to have been made with great care, and are in general very accurate. Berthier is a much more active man, and has not merely given us many analyses, but has made various important improvements in the analytical processes. His mode of separating arsenic acid and determining its weight is now generally followed, and I can state from experience that his method of fusing minerals with oxide of lead when the object is to detect an alkali is both accurate and easy. Berthier is young and active and zealous. We may therefore expect a great deal from him hereafter. End of section 58. Section 59 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 4, Part 5. The chemists in Great Britain have never hitherto distinguished themselves much in analytical chemistry. This I conceive is owing to the mode of education which has been hitherto unhappily followed. Till within these very few years, practical chemistry has been nowhere taught. The consequence has been that every chemist must discover processes for himself, and a long time elapses before he acquires the requisite dexterity and skill. About the beginning of the present century, Dr. Kennedy of Edinburgh was an enthusiastic and dexterous analyst, but unfortunately he was lost to the science by a premature death after giving a very few, but these masterly, analyses to the public. About the same time, Charles Hatchett, Esquire, was an active chemist, and published not a very few excellent analyses, but unfortunately this most amiable and accomplished man has been lost to science for more than a quarter of a century, the baneful effects of wealth and the cares of a lucrative and extensive business having completely weaned him from scientific pursuits. Mr. Gregor of Cornwall was an accurate man, and attended only to analytical chemistry. His analyses were not numerous, but they were in general excellent. Unfortunately, the science was deprived of his services by a premature death. The same observation applies equally to Mr. Edward Howard, whose analyses of meteoric stones form an era in this branch of chemistry. He was not only a skillful chemist, but was possessed of a persevering industry which peculiarly fitted him for making a figure as a practical chemist. Of modern British analytical chemists, undoubtedly the first is Mr. Richard Phillips, to whom we are indebted for not a few analyses, conducted with great chemical skill and performed with great accuracy. Unfortunately, of late years he has done little, having been withdrawn from science by the necessity of providing for a large family, which can hardly be done, in this country, except by turning one's attention to trade or manufactures. The same remark applies to Dr. Henry, who has contributed so much to our knowledge of gaseous bodies, and whose analytical skill, had it been wholly devoted to scientific investigations, would have raised his reputation as a discoverer much higher than it has attained, although the celebrity of Dr. Henry, even under the disadvantages of being a manufacturing chemist, is deservedly very high. Of the young chemists who have but recently started in the path of analytical investigation, we expect the most from Dr. Turner of the London University. His analyses of the ores of manganese are admirable specimens of skill and accuracy, and have completely elucidated a branch of mineralogy which, before his experiments and the descriptions of Heidinger appeared, was buried in impenetrable darkness. No man that Great Britain has produced was better fitted to have figured as an analytical chemist, both by his uncommon chemical skill and the powers of his mind, which were of the highest order, than Mr. Smithson Tennant, had he not been in some measure prevented by a delicate frame of body, which produced in him a state of indolence somewhat similar to that of Dr. Black. His discovery of osmium and iridium, and his analysis of emery and magnesian limestone, may be mentioned as proofs of what he could have accomplished had his health allowed him a greater degree of exertion. His experiments on the diamond first demonstrated that it was composed of pure carbon, while his discovery of phosphoret of lime has furnished lecturers on chemistry with one of the most brilliant and beautiful of those exhibitions which they are in the habit of making to attract the attention of their students. Smithson Tennant was the only child of the Reverend Calvert Tennant, youngest son of a respectable family in Wensleydale, near Richmond, in Yorkshire, and vicar of Selby in that county. He was born on the 30th of November, 1761. He had the misfortune to lose his father when he was only 9 years of age, and before he attained the age of manhood, he was deprived likewise of his mother by a very unfortunate accident. She was thrown from her horse while riding with her son, and killed on the spot. His education, after his father's death, was irregular and apparently neglected. He was sent successively to different schools in Yorkshire, at Scorton, Tadcaster, and Beverley. He gave many proofs while young of a particular turn for chemistry and natural philosophy, both by reading all books of that description which fell in his way, and by making various little experiments which the perusal of these books suggested. His first experiment was made at 9 years of age, when he prepared a quantity of gunpowder for fireworks, according to directions contained in some scientific book to which he had access. In the choice of a profession, his attention was naturally directed towards medicine, as being more nearly allied to his philosophical pursuits. He went accordingly to Edinburgh about the year 1781, where he laid the foundation of his chemical knowledge under Dr. Black. In 1782, he was entered a member of Christ's College, Cambridge, where he began from that time to reside. He was first entered as a pensioner, but disliking the ordinary discipline and routine of an academical life, he obtained an exemption from those restraints by becoming a fellow commoner. During his residence at Cambridge, his chief attention was bestowed on chemistry and botany, though he made himself also acquainted with the elementary parts of mathematics, and had mastered the most important parts of Newton's Principia. In 1784, he traveled into Denmark and Sweden, chiefly with the view of becoming personally acquainted with Scheele, for whom he had imbibed a high admiration. He was much gratified by what he saw of this extraordinary man, and was particularly struck with the simplicity of the apparatus with which his great experiments had been performed. On his return to England, he took great pleasure in showing his friends at Cambridge various mineralogical specimens, which had been presented to him by Scheele, and in exhibiting several interesting experiments which he had learned from that great chemist. A year or two afterwards, he went to France, to become personally acquainted with the most eminent of the French chemists. Thence he went to Holland and the Netherlands, at that time in a state of insurrection against Joseph II. In 1786, he left Christ's College along with Professor Hermann, and removed with him to Emmanuel College. In 1788, he took his first degree as Bachelor of Physic, and soon after quitted Cambridge and came to reside in London. In 1791, he made his celebrated analysis of carbonic acid, which fully confirmed the opinions previously stated by Lavoisier respecting the constituents of this substance. His mode was to pass phosphorus through red-hot carbonate of lime. The phosphorus was acidified and charcoal deposited. It was during these experiments that he discovered phosphoret of lime. In 1792, he again visited Paris, but from circumstances, being afraid of a convulsion, he was fortunate enough to leave that city the day before the memorable 10th of August. He traveled through Italy and then passed through part of Germany. On his return to Paris in the beginning of 1793, he was deeply impressed with the gloom and desolation arising from the system of terror then beginning to prevail in that capital. On calling in the house of M. Delametherie, of whose simplicity and moderation he had a high opinion, he found the doors and windows closed, as if the owner were absent. Being at length admitted, he found his friend sitting in a back room, by candlelight, with the shutters closed in the middle of the day. On his departure, after a hurried and anxious conversation, his friend conjured him not to come again, as the knowledge of his being there might be attended with serious consequences to them both. To the honor of Delametherie, it deserves to be stated that through all the inquisitions of the Revolution, he preserved for his friend property of considerable value, which Mr. Tennant had entrusted to his care. On his return from the Continent, he took lodgings in the Temple, where he continued to reside during the rest of his life. He still continued the study of medicine, and attended the hospitals, but became more indifferent about entering into practice. He took, however, a doctor's degree at Cambridge in 1796, but resolved, as his fortune was independent, to relinquish all idea of practice, as not likely to contribute to his happiness. Exquisite sensibility was a striking feature in his character, and it would, as he very properly conceived, have made him peculiarly unfit for the exercise of the medical profession. It may be worthwhile to relate an example of his practical benevolence which happened about this time. He had a steward in the country, in whom he had long placed implicit confidence, and who was considerably indebted to him. In consequence of this man's becoming embarrassed in his circumstances, Mr. Tennant went into the country to examine his accounts. A time and place were appointed for him to produce his books and show the extent of the deficiency, but the unfortunate steward felt himself unequal to the task of such an explanation, and in a fit of despair put an end to his existence. Touched by this melancholy event, Mr. Tennant used his utmost exertions for the relief and protection of the family whom he had left, and not only forgave them the debt, but afforded them pecuniary assistance, and continued ever afterwards to be their friend and benefactor. During the year 1796, he made his experiments to prove that the diamond is pure carbon. His method was to heat it in a gold tube with saltpeter. The diamond was converted into carbonic acid gas, which combined with the potash from the saltpeter, and by the evolution of which the quantity of carbon in a given weight of diamond might be estimated. A characteristic trait of Mr. Tennant occurred during the course of this experiment, which I relate on the authority of Dr. Wollaston, who was present as an assistant and who related the fact to me. Mr. Tennant was in the habit of taking a ride on horseback every day at a certain hour. The tube containing the diamond and saltpeter were actually heating, and the experiment considerably advanced, when, suddenly recollecting that his hour for riding was come, he left the completion of the process to Dr. Wollaston, and went out as usual to take his ride. In the year 1797, in consequence of a visit to a friend in Lincolnshire, where he witnessed the activity with which improvements in farming operations were at that time going on, he was induced to purchase some land in that country in order to commence farming operations. In 1799, he bought a considerable tract of waste land in Somersetshire, near the village of Cheddar, where he built a small house, in which, during the remainder of his life, he was in the habit of spending some months every summer, besides occasional visits at other times of the year. These farming speculations, as might have been anticipated from the indolent and careless habits of Mr. Tennant, were not very successful. Yet it appears from the papers which he left behind him that he paid considerable attention to agriculture, that he had read the best books on the subject, and collected many facts on it during his different journeys through various parts of England. In the course of these inquiries, he had discovered that there were two kinds of limestone known in the Midland countries of England, one of which yielded a lime injurious to vegetation. He showed in 1799 that the presence of carbonate of magnesia is the cause of the bad qualities of this latter kind of limestone. He found that the Magnesian limestone forms an extensive stratum in the Midland counties, and that it occurs also in primitive districts under the name of dolomite. He infers from the slow solubility of this limestone in acids that it is a double salt composed of carbonate of lime and carbonate of magnesia in chemical combination. He found that grain would scarcely germinate, and that it soon perished in moistened carbonate of magnesia. Hence he concluded that magnesia is really injurious to vegetation. Upon this principle he accounted for the injurious effects of the Magnesian limestone when employed as a manure. In 1802, he showed that emery is merely a variety of corundum, or of the precious stone known by the name of sapphire. During the same year, while endeavoring to make an alloy of lead with the powder which remains after treating crude platinum with aqua regia, he observed remarkable properties in this powder, and found that it contained a new metal. While he was engaged in the investigation, Descoutils had turned his attention to the same powder, and had discovered that it contained a metal which gives a red color to the ammoniacal precipitate of platinum. Soon after, Vauquelin, having treated the powder with alkali, obtained a volatile metallic oxide, which he considered as the same metal that had been observed by Descoutils. In 1804, Mr. Tennant showed that this powder contains two new metals, to which he gave the name of osmium and iridium. Mr. Tennant's health by this time had become delicate, and he seldom went to bed without a certain quantity of fever, which often obliged him to get up during the night and expose himself to the cold air. To keep himself in any degree in health, he found it necessary to take a great deal of exercise on horseback. He was always an awkward and a bad horseman, so that these rides were sometimes a little hazardous, and I have more than once heard him say that a fall from his horse would some day prove fatal to him. In 1809, he was thrown from his horse near Brighton and had his collarbone broken. In the year 1812, he was prevailed upon to deliver a few lectures on the principles of mineralogy to a number of his friends, among whom were many ladies, and a considerable number of men of science and information. These lectures were completely successful, and raised his reputation very much among his friends as a lecturer. He particularly excelled in the investigation of minerals by the blowpipe, and I have heard him repeatedly say that he was indebted for the first knowledge of the mode of using that valuable instrument to Assessor Gagne Fallon. In 1813, a vacancy occurring in the chemical professorship at Cambridge, he was solicited to become a candidate. His friends exerted themselves in his favor with unexampled energy, and all opposition being withdrawn, he was elected professor in May 1813. After the general pacification in 1814, he went to France and repaired to the southern provinces of that kingdom. He visited Lyon, Nîmes, Avignon, Marseille, and Montpellier. He returned to Paris in November, much gratified by his southern tour. He was to have returned to England about the latter end of the year, but he continued to linger on till the February following. On the 15th of that month he went to Calais, but the wind blew directly into Calais harbor and continued unfavorable for several days. After waiting till the 20th, he went to Boulogne in order to take the chance of a better passage from that port. He embarked on board a vessel on the 22nd, but the wind was still adverse, and blew so violently that the vessel was obliged to put back. When Mr. Tennant came ashore, he said that it was in vain to struggle with the elements, and that he was not yet tired of life. It was determined, in case the wind should abate, to make another trial in the evening. During the interval, Mr. Tennant proposed to his fellow traveler, Baron Bülow, that they should hire horses and take a ride. They rode at first along the seaside, but on Mr. Tennant's suggestion they went afterwards to Bonaparte's Pillar, which stands on an eminence about a league from the seashore, and which, having been to see it the day before, he was desirous of showing to Baron Bülow. On their return from thence, they deviated a little from the road, in order to look at a small fort near the Pillar, the entrance to which was over a fosse 20 feet deep. On the side toward them there was a standing bridge for some way, till it joined a drawbridge, which turned on a pivot. The end next the fort rested on the ground. On the side next to them it was usually fastened by a bolt, but the bolt had been stolen about a fortnight before, and was not replaced. As the bridge was too narrow for them to go abreast, the Baron said he would go first, and attempted to ride over it, but perceiving that it was beginning to sink, he made an effort to pass the center, and called out to warn his companion of his danger. But it was too late. They were both precipitated into the trench. The Baron, though much stunned, fortunately escaped without any serious hurt, but on recovering his senses, and looking round for Mr. Tennant, he found him lying under his horse, nearly lifeless. He was taken, however, to the civil hospital, as the nearest place ready to receive him. After a short interval, he seemed in some slight degree to recover his senses, and made an effort to speak, but without effect, and died within the hour. His remains were interred a few days after in the public cemetery at Boulogne, being attended to the grave by most of the English residents. End of section 59. Section 60 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas THOMSON, Volume 2, Chapter 4, Part 6. There is another branch of investigation intimately connected with analytical chemistry, the improvements in which have been attended with great advantage, both to mineralogists and chemists. I mean the use of the blowpipe to make a kind of miniature analysis of minerals in the dry way, so far, at least, as to determine the nature of the constituents of the mineral under examination. This is attended with many advantages, as a preliminary to a rigid analysis by solution. By informing us of the nature of the constituents, it enables us to form a plan of the analysis beforehand, which, in many cases, saves the trouble and the tediousness of two separate analytical investigations. For when we set about analyzing a mineral, of the nature of which we are entirely ignorant, two separate sets of experiments are in most cases indispensable. We must examine the mineral in the first place to determine the nature of its constituents. These being known, we can form a plan of an analysis, by means of which we can separate and estimate in succession the amount of each constituent of the mineral. Now, a judicious use of the blowpipe often enables us to determine the nature of the constituents in a few minutes, and thus saves the trouble of the preliminary analysis. The blowpipe is a tube employed by goldsmiths in soldering. By means of it, they force the flame of a candle or lamp against any particular point which they wish to heat. This enables them to solder trinkets of various kinds, without affecting any other part, except the portion which is required to be heated. Cronstedt and Angstrom first thought of applying this little instrument to the examination of minerals. A small fragment of the mineral to be examined, not nearly so large as the head of a pin, was put upon a piece of charcoal, and the flame of a candle was made to play upon it by means of a blowpipe, so as to raise it to a white heat. They observed whether it decrepitated, or was dissipated, or melted, and whatever the effect produced was, they were enabled from it to draw consequences respecting the nature of the mineral under examination. The importance of this instrument struck Bergman, and induced him to wish for a complete examination of the action of the heat of the blowpipe upon all different minerals, either tried per se upon charcoal, or mixed with various fluxes. For 3 different substances had been chosen as fluxes, namely carbonate of soda, borax, and biphosphate of soda, or at least what was in fact an equivalent for this last substance, ammonium-phosphate of soda, or microcosmic alt, at that time extracted from urine. This salt is a compound of 1 integrant particle of phosphate of soda and 1 integrant particle of phosphate of ammonia. When heated before the blowpipe, it fuses, and the water of crystallization, together with the ammonia, are gradually dissipated, so that at last nothing remains but biphosphate of soda. These fluxes have been found to act with considerable energy on most minerals. The carbonate of soda readily fuses with those that contain much silica, while the borax and biphosphate of soda act most powerfully on the bases, not sensibly affecting the silica, which remains unaltered in the fused bead. A mixture of borax and carbonate of soda upon charcoal, in general, enables us to reduce the metallic oxides to the state of metals, provided we understand the way of applying the flame properly. Bergman employed Gahn, who was at that time his pupil, and whose skill he was well acquainted with, to make the requisite experiments. The result of these experiments was drawn up into a paper which Bergman sent to Baron Born in 1777, and they were published by him at Vienna in 1779. This valuable publication threw a new light upon the application of the blowpipe to the assaying of minerals, and for everything new which it contained, Bergman was indebted to Gahn, who had made the experiments. John Gottlieb Gahn, the intimate friend of Bergman and of Scheele, was one of the best informed men, and one whose manners were the most simple, unaffected, and pleasing of all the men of science with whom I ever came in contact. I spent a few days with him at Fallon in 1812, and they were some of the most delightful days that I ever passed in my life. His fund of information was inexhaustible, and was only excelled by the charming simplicity of his manners, and by the benevolence and goodness of heart which beamed in his countenance. He was born on the 17th of August, 1745, at the Waxna Iron Works in South Helsingland, where his father, Hans Jacob Gahn, was treasurer to the government of Stora Kopparberg. His grandfather, or great-grandfather, he told me, had emigrated from Scotland, and he mentioned several families in Scotland to which he was related. After completing his school education at Westeros, he went in the year 1760 to the University of Uppsala. He had already shown a decided bias toward the study of chemistry, mineralogy, and natural philosophy, and like most men of science in Sweden, where philosophical instrument makers are scarcely to be found, he had accustomed himself to handle the different tools, and to supply himself in that manner with all the different pieces of apparatus which he required for his investigations. He seems to have spent nearly 10 years at Uppsala, during which time he acquired a very profound knowledge in chemistry, and made various important discoveries which his modesty or his indifference to fame made him allow others to pass as their own. The discovery of the rhomboidal nucleus of carbonate of lime in a 6-sided prism of that mineral, which he let fall and which was accidentally broken, constitutes the foundation of Hauey's system of crystallization. He communicated the fact to Bergman, who published it as his own in the 2nd volume of his Opuscula, without any mention of Gahn's name. The earth of bones had been considered as a peculiar simple earth, but Gahn ascertained by analysis that it was a compound of phosphoric acid and lime, and this discovery he communicated to Scheele, who, in his paper on fluorspar, published in 1771, observed, in the 17th section in which he is describing the effect of phosphoric acid on fluorspar, "It has lately been discovered that the earth of bones or of horns is calcareous earth combined with phosphoric acid." In consequence of this remark, in which the name of Gahn does not appear, it was long supposed that Scheele and not Gahn was the author of this important discovery. It was during this period that he demonstrated the metallic nature of manganese and examined the properties of the metal. This discovery was announced as his, at the time, by Bergman, and was almost the only one of the immense number of new facts which he had ascertained that was publicly known to be his. On the death of his father, he was left in rather narrow circumstances, which obliged him to turn his immediate attention to mining and metallurgy. To acquire a practical knowledge of mining, he associated with the common miners and continued to work like them till he had acquired all the practical dexterity and knowledge which actual labor could give. In 1770, he was commissioned by the College of Mines to institute a course of experiments with a view to improve the method of smelting copper at Falun. The consequence of this investigation was a complete regeneration of the whole system, so as to save a great deal both of time and fuel. Some time after, he became a partner in some extensive works at Stora Kopparberg, where he settled as a superintendent. From 1770, when he first settled at Falun, down to 1785, he took a deep interest in the improvement of the chemical works in that place and neighborhood. He established manufactories of sulfur, sulfuric acid, and red ochre. In 1780, the Royal College of Mines, as a testimony of their sense of the value of Gahn's improvements, presented him with a gold medal of merit. In 1782, he received a royal patent as mining master. In 1784, he was appointed assessor in the Royal College of Mines, in which capacity he officiated as often as his other vocations permitted him to reside in Stockholm. The same year he married Anna Maria Bergström, with whom he enjoyed for 31 years a life of uninterrupted happiness. By his wife he had a son and 2 daughters. In the year 1773, he had been elected chemical stipendiary to the Royal College of Mines, and he continued to hold this appointment till the year 1814. During the whole of this period, the solution of almost every difficult problem remitted to the college devolved upon him. In 1795, he was chosen a member of the committee for directing the general affairs of the kingdom. In 1810, he was made one of the committee for the general maintenance of the poor. In 1812, he was elected an active associate of the Royal Academy for Agriculture, and in 1816, he became a member of the committee for organizing the plan of a mining institute. In 1818, he was chosen a member of the Committee of the Mint, but from this situation he was shortly after, at his own request, permitted to withdraw. His wife died in 1815, and from that period his health, which had never been robust, visibly declined. Nature occasionally made an effort to shake off the disease, but it constantly returned with increasing strength, until, in the autumn of 1818, the decay became more rapid in its progress and more decided in its character. He became gradually weaker, and on the 8th of December, 1818, died without a struggle and seemingly without pain. Ever after the experiments on the blowpipe which Gahn performed at the request of Bergman, his attention had been turned to that piece of apparatus, and during the course of a long life he had introduced so many improvements that he was enabled, by means of the blowpipe, to determine in a few minutes the constituents of almost any mineral. He had gone over almost all the mineral kingdom and determined the behavior of almost every mineral before the blowpipe, both by itself and when mixed with the different fluxes and reagents which he had invented for the purpose of detecting the different constituents. But from his characteristic unwillingness to commit his observations and experiments to writing, or to draw them up into a regular memoir, had not Berzelius offered himself as an assistant, they would probably have been lost. By his means, a short treatise on the blowpipe, with minute directions how to use the different contrivances which he had invented, was drawn up and inserted into the second volume of Berzelius's Chemistry. Berzelius and he afterwards examined all the minerals known, or at least which they could procure, before the blowpipe, and the result of the whole constituted the materials of Berzelius's treatise on the blowpipe, which has been translated into German, French, and English. It may be considered as containing the sum of all the improvements which Gahn had made on the use of the blowpipe, together with all the facts that he had collected respecting the phenomena exhibited by minerals before the blowpipe. It constitutes an exceedingly useful and valuable book, and ought to make a part of the library of every analytical chemist. Dr. Wollaston had paid as much attention to the blowpipe as Gahn, and had introduced so many improvements into its use that he was able, by means of it, to determine the nature of the constituents of any mineral in the course of a few minutes. He was fond of such analytical experiments, and was generally applied to by every person who thought himself possessed of a new mineral, in order to be enabled to state what its constituents were. The London mineralogist, if the race be not extinct, must sorely feel the want of the man to whom they were in the habit of applying on all occasions, and to whom they never applied in vain. Dr. William Hyde Wollaston was the son of the Reverend Dr. Wollaston, a clergyman of some rank in the Church of England, and possessed of a competent fortune. He was a man of abilities, and rather eminent as an astronomer. His grandfather was the celebrated author of The Religion of Nature Delineated. Dr. William Hyde Wollaston was born about the year 1767, and was one of 15 children who all reached the age of manhood. His constitution was naturally feeble, but by leading a life of the strictest sobriety and abstemiousness, he kept himself in a state fit for mental exertion. He was educated at Cambridge, where he was at one time a fellow. After studying medicine, by attending the hospitals and lectures in London, and taking his degree of doctor at Cambridge, he settled at Bury St. Edmunds, where he practiced as a physician for some years. He then went to London, became a Fellow of the Royal College of Physicians, and commenced practitioner in the metropolis. A vacancy occurring in St. George's Hospital, he offered himself for the place of physician to that institution, but another individual, whom he considered his inferior in knowledge and science, having been preferred before him, he threw up the profession of medicine altogether, and devoted the rest of his life to scientific pursuits. His income, in consequence of the large family of his father, was of necessity small. In order to improve it, he turned his thoughts to the manufacture of platinum, in which he succeeded so well that he must have, by means of it, realized considerable sums. It was he who first succeeded in reducing it into ingots in a state of purity and fit for every kind of use. It was employed, in consequence, for making vessels for chemical purposes, and it is to its introduction that we are to ascribe the present accuracy of chemical investigations. It has been gradually introduced into the sulfuric acid manufactories as a substitute for glass retorts. Dr. Wollaston had a particular turn for contriving pieces of apparatus for scientific purposes. His reflecting goniometer was a most valuable present to mineralogists, and it is by its means that crystallography has acquired the great degree of perfection which it has recently exhibited. He contrived a very simple apparatus for ascertaining the power of various bodies to refract light. His camera lucida furnished those who were ignorant of drawing with a convenient method of delineating natural objects. His periscopic glasses must have been found useful, for they sold rather extensively, and his sliding rule for chemical equivalents furnished a ready method for calculating the proportions of one substance necessary to decompose a given weight of another. Dr. Wollaston's knowledge was more varied and his taste less exclusive than any other philosopher of his time, except Mr. Cavendish. But optics and chemistry are the two sciences which lie under the greatest obligations to him. His first chemical paper on urinary calculi at once added a vast deal to what had been previously known. He first pointed out the constituents of the mulberry calculi, showing them to be composed of oxalate of lime and animal matter. He first distinguished the nature of the triple phosphates. It was he who first ascertained the nature of the cystic oxides and of the chalk stones, which appear occasionally in the joints of gouty patients. To him we owe the first demonstration of the identity of galvanism and common electricity, and the first explanation of the cause of the different phenomena exhibited by galvanic and common electricity. To him we are indebted for the discovery of palladium and rhodium, and the first account of the properties and characters of these two metals. He first showed that oxalic acid and potash unite in 3 different proportions, constituting oxalate, binoxalate, and quadroxalate of potash. Many other chemical facts, first ascertained by him, are to be found in the numerous papers of his scattered over the last 40 volumes of the Philosophical Transactions, and perhaps not the least valuable of them is his description of the mode of reducing platinum from the raw state and bringing it into the state of an ingot. Dr. Wollaston died in the month of January, 1829, in consequence of a tumor formed in the brain near, if I remember right, the thalami nervosum opticorum. There is reason to suspect that this tumor had been some time in forming. He had, without exception, the sharpest eye that I have ever seen. He could write with a diamond upon glass in a character so small that nothing could be distinguished by the naked eye but a ragged line. Yet when the letters were viewed through a microscope, they were beautifully regular and quite legible. He retained his senses to almost the last moment of his life. When he lay apparently senseless, and his friends were anxiously solicitous whether he still retained his understanding, he informed them, by writing, that his senses were still perfectly entire. Few individuals ever enjoyed a greater share of general respect and confidence, or had fewer enemies, than Dr. Wollaston. He was at first shy and distant, and remarkably circumspect, but he grew insensibly more and more agreeable as you got better acquainted with him, till at last you formed for him the most sincere friendship, and your acquaintance ended in the warmest and closest attachment. End of section 60.
Section 61 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 5, of Electro-Chemistry, Part 1. Electricity, like chemistry, is a modern science, for it can scarcely claim an older origin than the termination of the first quarter of the preceding century. And during the last half of that century, and a small portion of the present, it participated with chemistry in the zeal and activity with which it was cultivated by the philosophers of Europe and America. For many years, it was not suspected that any connection existed between chemistry and electricity, though some of the meteorological phenomena, especially the production of clouds and the formation of rain, which are obviously connected with chemistry, seem likewise to claim some connection with the agency of electricity. The discovery of the intimate relation between chemistry and electricity was one of the consequences of a controversy carried on about the year 1790 between Galvani and Volta, two Italian philosophers, whose discoveries will render their names immortal. Galvani, who was a professor of anatomy, was engaged in speculations respecting muscular motion. He was of opinion that a peculiar fluid was secreted in the brain, which was sent along the nerves to all the different parts of the body. This nervous fluid possessed many characters analogous to those of electricity. The muscles were capable of being charged with it, somewhat like a Leyden vial, and it was by the discharge of this accumulation, by the voluntary power of the nerves, that muscular motion was produced. He accidentally discovered that if the crural nerve going into the muscles of a frog, and the crural muscles, be laid bare immediately after death, and a piece of zinc be placed in contact with the nerve, and a piece of silver or copper with the muscle, when these two pieces of metal are made to touch each other, violent convulsions are produced in the muscle, which cause the limb to move. He conceived that these convulsions were produced by the discharge of the nervous energy from the muscles, in consequence of the conducting power of the metals. Volta, who repeated these experiments, explained them in a different manner. According to him, the convulsions were produced by the passage of a current of common electricity through the limb of the frog, which was thrown into a state of convulsion merely in consequence of its irritability. This irritability vanishes after the death of the muscle. Accordingly, it is only while the principle of life remains that the convulsions can be produced. Every metallic conductor, according to him, possesses a certain electricity which is peculiar to it, either positive or negative, though the quantity is so small as to be imperceptible in the common state of the metal. But if a metal, naturally positive, be placed in contact, while insulated, with a metal naturally negative, the charge of electricity in both is increased by induction, and becomes perceptible when the two metals are separated and presented to a sufficiently delicate electrometer. Thus zinc is naturally positive, and copper and silver naturally negative. If we take two discs of copper and zinc, to the center of each of which a varnished glass handle is cemented, and after keeping them for a short time in contact, separate them by the handles, and apply each to a sufficiently delicate electrometer, we shall find that the zinc is positive and the silver or copper disc negative. When the silver and copper are placed in contact while lying on the nerve and muscles of the leg of a frog, the zinc becomes positive and the silver negative by induction. But as the animal substance is a conductor, this state cannot continue. The two electricities pass through the conducting muscles and nerve, and neutralize one another, and it is this current which occasions the convulsions. Such was Volta's simple explanation of the convulsions produced in galvanic experiments in the limb of a frog. Galvani was far from allowing the accuracy of it, and, in order to obviate the objection to his reasoning advanced by Volta from the necessity of employing two metals, he showed that the convulsions might, in certain cases, be produced by one metal. Volta showed that a very small quantity of one metal, either alloyed with or merely in contact with another, were capable of inducing the two electricities. But in order to prove in the most unanswerable manner that the two electricities were induced when two different metals were placed in contact, he contrived the following piece of apparatus. He procured a number, say 50, of pieces of zinc, about the size of a crown piece, and as many pieces of copper, and thirdly, the same number of pieces of card of the same size. The cards were steeped in a solution of salt, so as to be moist. He lays upon the table a piece of zinc, places over it a piece of copper, and then a piece of moist card. Over the card is placed a second piece of zinc, then a piece of copper, then a piece of wet card. In this way, all the pieces are piled upon each other in exactly the same order, namely, zinc, copper, card, zinc, copper, card, zinc, copper, card, so that the lowest plate is zinc and the uppermost is copper, for the last wet card may be omitted. In this way, there are 50 pairs of zinc and copper plates in contact, each separated by a piece of wet card, which is a conductor of electricity. If you now moisten a finger of each hand with water, and apply one wet finger to the lowest zinc plate, and the other to the highest copper plate, the moment the fingers come in contact with the plates, an electric shock is felt, the intensity of which increases with the number of pairs of plates in the pile. This is what is called the galvanic, or rather the voltaic pile. It was made known to the public in a paper by Volta, inserted in the Philosophical Transactions for 1800. This pile was gradually improved by substituting troughs, first of baked wood, and afterwards of porcelain, divided into as many cells as there were pairs of plates. The size of the plates was increased, they were made square, and instead of all being in contact, it was found sufficient if they were soldered together by means of metallic slips rising from one side of each square. The two plates thus soldered were slipped over the diaphragm separating the contiguous cells, so that the zinc plate was in one cell, and the copper in the other. Care was taken that the pairs were introduced all looking one way, so that a copper plate had always a zinc plate immediately opposite to it. The cells were filled with conducting liquid, brine, or a solution of salt and vinegar, or dilute muriatic, sulfuric, or nitric acid might be employed. But dilute nitric acid was found to answer best, and the energy of the battery is directly proportional to the strength of the nitric acid employed. Messrs. Nicholson and Carlisle were the first persons who repeated Volta's experiments with this apparatus, which speedily drew the attention of all Europe. They ascertained that the zinc end of the pile was positive, and the copper end negative. Happening to put a drop of water on the uppermost plate, and to put into it the extremity of a gold wire connected with the undermost plate, they observed an extrication of air bubbles from the wire. This led them to suspect that the water was decomposed. To determine the point, they collected a little of the gas extricated and found it hydrogen. They then attached a gold wire to the zinc end of the pile, and another gold wire to the copper end, and plunged the two wires into a glass of water, taking care not to allow them to touch each other. Gas was extricated from both wires. On collecting that from the wire attached to the zinc end, it was found to be oxygen gas, while that from the copper end was hydrogen gas. The volume of hydrogen gas extricated was just double that of the oxygen gas, and the two gases being mixed, and an electric spark passed through them, they burnt with an explosion and were completely converted into water. Thus it was demonstrated that water was decomposed by the action of the pile, and that the oxygen was extricated from the positive pile and the hydrogen from the negative. This held when the communicating wires were gold or platinum, but if they were of copper, silver, iron, lead, tin, or zinc, then only hydrogen gas was extricated from the negative wire. The positive wire extricated little or no gas, but it was rapidly oxidized. Thus, the connection between chemical decompositions and electrical currents was first established. It was soon after observed by Henry, Haldane, Davy, and other experimenters that other chemical compounds were decomposed by the electrical currents as well as water. Ammonia, for example, nitric acid, and various salts were decomposed by it. In the year 1803, an important set of experiments was published by Berzelius and Hisinger. They decomposed 11 different salts by exposing them to the action of a current of electricity. The salts were dissolved in water, and iron or silver wires from the two poles of the pile were plunged into the solution. In every one of these decompositions, the acid was deposited round the positive wire, and the base of the salt round the negative wire. When ammonia was decomposed by the action of galvanic electricity, the azotic gas separated from the positive wire, and the hydrogen gas from the negative. But it was Davy that first completely elucidated the chemical decompositions produced by galvanic electricity, who first explained the laws by which these decompositions were regulated, and who employed galvanism as an instrument for decomposing various compounds, which had hitherto resisted all the efforts of chemists to reduce them to their elements. These discoveries threw a blaze of light upon the obscurest parts of chemistry, and secured for the author of them an immortal reputation. Humphrey Davy, to whom these splendid discoveries were owing, was born at Penzance in Cornwall in the year 1778. He displayed from his very infancy a spirit of research, and a brilliancy of fancy, which augured, even at that early period, what he was one day to be. When very young, he was bound apprentice to an apothecary in his native town. Even at that time, his scientific acquirements were so great that they drew the attention of Mr. Davis Gilbert, the late distinguished president of the Royal Society. It was by his advice that he resolved to devote himself to chemistry, as the pursuit best calculated to procure him celebrity. About this time, Mr. Gregory Watt, youngest son of the celebrated improver of the steam engine, happening to be at Penzance, met with young Davy, and was delighted with the uncommon knowledge which he displayed, at the brilliancy of his fancy, and the great dexterity and ardor with which, under circumstances the most unfavourable, he was prosecuting his scientific investigations. These circumstances made an indelible impression on his mind, and led him to recommend Davy as the best person to superintend the Bristol institution for trying the medicinal effects of the gases. After the discovery of the different gases, and the investigation of their properties by Dr. Priestley, it occurred to various individuals, nearly about the same time, that the employment of certain gases, or at least of mixtures of certain gases, with common air in respiration instead of common air, might be powerful means of curing diseases. Dr. Beddoes, at that time professor of chemistry at Oxford, was one of the keenest supporters of these opinions. Mr. Watt of Birmingham and Mr. Wedgwood entertained similar sentiments. About the beginning of the present century, a sum of money was raised by subscription to put these opinions to the test of experiment, and as Dr. Beddoes had settled as a physician in Bristol, it was agreed upon that the experimental investigation should take place at Bristol. But Dr. Beddoes was not qualified to superintend an institution of the kind, it was necessary to procure a young man of zeal and genius, who would take such an interest in the investigation as would compensate for the badness of the apparatus and the defects of the arrangements. The greatest part of the money had been subscribed by Mr. Wedgwood and Mr. Watt. Their influence, of course, would be greatest in recommending a proper superintendent. Gregory Watt thought of Mr. Davy, whom he had lately been so highly pleased with, and recommended him with much zeal to superintend the undertaking. This recommendation being seconded by that of Mr. Davis Gilbert, who was so well acquainted with the scientific acquirements and genius of Davy, proved successful, and Davy accordingly got the appointment. At Bristol he was employed about a year in investigating the effects of the gases when employed in respiration. But he did not by any means confine himself to this, which was the primary object of the institution, but investigated the properties and determined the composition of nitric acid, ammonia, protoxide of azote, and deutoxide of azote. The fruit of his investigations was published in 1800, in a volume entitled Researches, Chemical and Philosophical, chiefly concerning nitrous oxide, or dephlogisticated nitrous air, and its respiration. This work gave him at once a high reputation as a chemist, and was really a wonderful performance, when the circumstances under which it was produced are taken into consideration. He had discovered the intoxicating effects which protoxide of azote, nitrous oxide, produces when breathed, and had tried their effects upon a great number of individuals. This fortunate discovery perhaps contributed more to his celebrity, and to his subsequent success, than all the sterling merit of the rest of his researches. So great is the effect of display upon the greater part of mankind. End of section 61.